Whoa, sweet lady, you've got it all in the right spots. Amazingly beautiful, and your heart. I love your style and your attitude. You're always loving, baby, and never. You make my life sunny and bright. I'll never let you go now, out of my sight. I'm gonna be my whole world around you, because you're the love, yes, of my life. I'll be there in times of need. I'll be your king and you my queen. Like an eagle protects his nest, my lady, baby, I'll do my best. Yeah, you're the love of my life. Oh, you're the love of my life, my sweet baby, love of my life. Whoa, sweet lady, you've got it all in the right spots. Amazingly beautiful, and your heart. I love your style and your attitude. You're always loving, baby, and never. You make my life sunny and bright. I'll never let you go now, out of my sight. I'm gonna be my whole world around you, because you're the love, yes, of my life. I'll be there in times of need. I'll be your king and you my queen. Like an eagle protects his nest, my lady, baby, I'll do my best.
Yeah, you see this data lake all around here? This used to be a data swamp. It was disgusting. Thankfully, they've been doing a lot of work on the data governance side to clean things up. There used to be crocs in here, almost 10 feet long. Oh, wait. Look at this. We've got a leftover artifact years in the past. I don't think that guy's gonna make it much longer, sadly. This water's practically clean enough to snorkel in it. Little fella, you all right? Oh, it's definitely a croc, all right?
Africa, here I go. Africa, here I go. Ain't turning back. Got to be there. Yes, I want to go. Yes, over Africa. Yes, I want to go. Yes, over Africa. Our foreparents come here in slaves.
Good people of Earth, welcome to OpenXdata. I am so stoked to be here with you today. We have a jam-packed lineup. We've got some incredible fun things to do in between different speakers, and we are going to just rock and roll all day. I'm going to threaten you now with a little ukulele, but that's going to come later, so you got to stick around. I've been seeing folks in the chat saying that they are from all over the globe. This is so cool to see how many people are tuning in right now. I think we've got over 1,000 people with us from Europe to India to Australia to South America, and of course, the good old USA. Well, folks, there's a few things I want to tell you before we actually bring on our first keynote, and that is all of these talks are going to be recorded and you can come back and watch them. We have 2 different stages going on. Right now for the keynote, there's only one because it's a keynote. But as soon as we get done with that first keynote, we're going to break out into not 1, not 2, but actually 3 different sessions. So if you want to join track 2, or if you want to join a workshop that is specifically on track 3, you can do that by hitting that little back button in your top left-hand corner right around here and jumping into the next spot. All right, so that's the first thing. 2 tracks, whole lot of fun. What's the next thing I got to say? Well, we're going to be doing a few giveaways just because we like you all. And there's some of the most advanced data platform folks in the world on this call. So why not
show our appreciation. That's right. We're going to be having some fun, doing some giveaways on different pieces of this journey. We also are going to be asking some quiz questions. So, sharpen up your little pencils and get ready. And lastly, we are going to be asking some poll questions because I personally want to know what you all are doing and how you're getting work done these days in this world of complete flux. I've spoken enough. Let's get into the first talk of the day, our keynote from the man himself. Vinod, where are you at, dude? Let me bring you onto the stage. And there he is. Oh, you got to turn on your camera so we can all see you. Where is he at? I like how people are giving the clapping emoji. Where are you at, Mr. Vinod? Are you here? You're on mute and you are.
I am here now.
There he is. I like this background. Look at that. That's a cool background you got. Okay, well, man, I don't want to keep you waiting. I don't want to keep the people of the chat waiting. So I am very excited to present you as our first keynote. Let's get your talk rocking and rolling.
All right, early start. Awesome. Let me bring up the slides. Just a minute. All right. Are we ready
Yeah,
to
we
go?
see him.
All right.
Let's go.
Cool. All right, let's roll. Hey everyone. Welcome to this year's OpenXdata Summit, and good morning. And today I want to talk to you about a shift that is going to, in my opinion, redefine data platforms over the next decade. I've been working on data platforms from 2016, incidentally, to 2026. So I'm really looking forward to the next decade here. So spent the last decade, like I mentioned, building lakehosts, open formats, file formats, table formats, query engines, pipelines, streaming systems, but all for human users, right? And analysts, engineers, data scientists, applications with fairly predictable access patterns. But the next major user of the data platform, surprise, surprise, is not human, right? It's going to be autonomous software. This sounds like a small change, but it's not. It changes the workload, it changes the failure mode, it changes the cost model, it changes a lot of things. So let me maybe get into it by briefly explaining why I care about this. Right, I spent most of my career working on open data systems, writing from data ingestion to incremental processing to ETL to table formats, query engines, Lakehouse infrastructure. I helped create, along with my team at Uber, the first data lakehouse, and we branded at production scale way before the term was even coined later on in the market. We solved some very forward-looking problems that power to this day very large data lakehouses at like Amazon or JD or Walmart and thousands of other companies. At one house, I founded one house 4 years ago or change. We're trying to build beyond that, like a single project. We built one house as the most open flexible data platform that supports any table format, data format, any engine, any catalog, any cloud. We are the only platform in the market that can actually say this. And our engines can meaningfully cut your cloud bills while keeping data open, right? But I'm not here to give you a pitch, so I'm just trying to tell you that this talk is from a perspective of somebody who's not looking at AI and the shift from the outside. It's from the perspective of somebody who spent a lot of time building these data substrate or these various data systems. And I see what these new AI agents are going to do to the data platform, and the opportunities and the challenges within that, right? So the very simple reason is the data platform that we built over the last decade or so is about to break. Not because we built it wrong, not because it's bad, right? The lakehouse, the warehouse, the query engines, the pipeline systems, all of it is still very crucial. It's going to remain critical to thousands and thousands of companies out there. It's going to break because the user of the platform is changing, right? Most of our assumptions in the current stack are human assumptions. Somebody asks a question, waits for an answer, interprets it, then decides what to do next, right? We kind of rely on the patience of human beings here. That assumption is changing. The human to machine movement is growing way faster than most data platforms are prepared for. And over the last 2 years, we've seen that, right? A massive shift in terms of the amount of queries that are being generated to these systems from software versus like people typing these into a white SQL text box, right? So AI initially showed up as copilots, chat interfaces, right? Is meaning very meaningful. It still looked human centric, right? It was still a text box where you type something in and then the model tells you something, right? But now we are moving into agents, right? Full steam ahead this year, and systems that these systems plan, call tools being like any database or API or anything that you do, write code, inspect results. They run in a loop until they accomplish a goal. So that's actually a popular social post from our VP of product, Kyle Weller, where he's referencing how the Matrix, the movie, warned us about agents 25 years ago. And, you know, the uncomfortable truth is they're going to do some bad things to your data systems and data infrastructure, not because they're malicious, but because the access patterns they create are fundamentally different. Right? So, by the way, if you like more of that content, you should catch a stock on Spark and performance. I think you'll find a lot more sharp points like this there. So, we need to remind ourselves what the data stack was originally designed for, right? So it was designed for humans, as in we build dashboards so we can look at what's changed. It's largely static, right? Notebooks or interactive exploration environments where you can write code and explore data, still again kind of static, right? um, and batch pipelines are built around some scheduled human timelines where you can operate the pipeline, things like that. Interactive query engines to ad hoc questions, right? See, like for all of these things, if you imagine the user to be a machine, then it changes a lot of things, right? Most analytical engines, for example, they can bottleneck with mere hundreds of QPS. So the whole stack kind of right now assumes that the user is relatively slow, bounded, and very intentional about what they're doing. All those three assumptions are gone. Right? Before, the loop was pretty simple. A human formulated a question, submitted a query, waited for results, interpreted the output, decided what to do next. Now that loop is slow, right? I mean, it has natural limits. We, like humans, we sleep, we get bored, we go browse something, we take breaks. But if you want to have agents and machines operating continuously on the data, they don't wait, they don't have to sleep. They think for themselves, right? You're now you have like two parallel brains, and decide what to do. You only know about what they did after the fact, right? So the question no longer is, can my data platform answer more queries, right? That is not the question. The question is, can my data platform, how can it adapt and survive when the primary consumer is software, not a human, right? That is why if you simply treat AI agents as just faster humans, that's like a pretty dangerous mistake, because like I said, they run continuously, right? You can't schedule some warehouse maintenance over a weekend anymore because nobody's in the office, right? You can do things like that. They generate queries autonomously. Nobody's sitting there writing SQL in advance. The agent, based on a human language query, is going to decide, oh, for this I need to generate these kinds of SQL queries against these systems, right? And how to ask for it. They act on results immediately. There may be like no human review step in between too, right? I mean, this is the whole point of having AI agents, is to not have humans be the bottleneck in between, right? So they can scale unpredictably, right? Like you've already seen this. If you're using Claude, Codex, or any of these tools, the one agent can become 10 because it'll do a lot of sub agents, like do some scatter gather, these kinds of things. So a workflow can trigger a whole cascade of queries and tool calls that no capacity planner anticipated, right? This is not just some workload increase, it's also a workload change because now they can kind of ask arbitrary things, right? So humans ask questions, but agents are trying to operate a system. That is at least the north star for where these agentic platforms are headed. So this means the data platform is no longer just supporting like analysis or data science or like something like that. It's becoming a part of the runtime for autonomous software. And if your data platform is slow, stale, fragmented, the agent is not just inconvenience like a human, right? I mean, the warehouse queries are slow, somebody complains, right? It's not that. It's actually can act on the wrong world, and and the wrong kind of context, right? So that brings us actually now to the central world word in this whole discussion: context, right? Context and data are the hottest words around right now, given where the foundation models are. So agents live or die by context, right? An agent without context is just not like an optional thing. It's actually dangerous, right? They can you're granting an agent to do things and at machine speed, and these wrong decisions can compound very quickly. I will not name them, but like we've seen this year how a very popular major cloud provider has had several outages attributed to kind of like lots of autonomous decisions being made by AI agents, right? So this is like definitely the direction that we need to go, but it is, you need to get a lot of things right. So when I say context, I mean the data an agent needs to reason about the world. This can include facts, history, what happened before, what decisions were made, what outcomes occurred, current state, past state, relationships, everything, right? So many AI projects today fail because of AI ready, like data, right? AI readiness is a data problem. It's not a can I get a better model problem alone. Of course, you need a better model. That is like we're making phenomenal progress there. But your data is poor, then the model is no longer the bottleneck, right? So let's make this term concrete, right? What does context mean for data systems? Context is fresh, joinable, cheap to query runtime data for AI systems, right? This is very practical, intentionally very practical definition. Basically, you want a bunch of data about various things that I talked about, which are in this kind of like it's very fresh, it's pumping in all the time. You can correlate them very cheaply, right? If your data is stale, then your agent can be wrong completely. If your joins are slow, then your agent is going to lag, right? That response that you get from your inference is going to take a while. If your pipelines break, right, your agent is acting on a past and can hallucinate and bad things can happen, right? So this is no longer about analytics. We are not building data sets so that humans can look at the data, right? Building and serving this context, I think, is the new workload that is going to now sit on top of data platforms. And the problem is this context is today like super fragmented in any enterprise, right? Like how data generally is. Um, for humans, maybe that was manageable. We can ask around, right? You can be like, oh, where is the data? Oh, it's in low. I'll go ask this person in Slack. Oh, check the warehouse. So maybe that thing has it, this thing has it. So agents cannot operate like that, right? You need to tell it precisely what data is where, what it means, all of that. And you have to connect the dots for the agent for you to be able to have the agent operate autonomously. So the agent cannot afford slow manual stitching. It needs context while it's deciding. Right? But the thing is, history of database design means you may have like many different databases, data warehouses, any different data storage systems in your company, right? OLTP systems are great for point lookups. OLAP systems are great for aggregations and scans. Data lakes are cheap, durable storage that you can do a lot of transformations and ETL on. Vector databases recently emerged to do these kinds of like similarity searches during inference time. So but they're all optimizing for a specific workload. But agents, they don't really understand this, right? Like they don't respect these system specializations. They're gonna, if you tell them, they think this particular system has this piece of data, it's going to try to go generate a query against it. So agents can generate all query shapes at once on against this context data that can live in everywhere. It can generate narrow queries for point lookups, like knowing what is the state of this order, right? Generate wide queries, scans and aggregations, trying to understand more deeply where the patterns are, things like that. They can do search queries for semantic relevance. They can do join heavy queries for relationship traversal across entities. They need all of this at once. If you block that loop, then your inference is going to be slow. If you're self-hosting your model, you're going to waste a bunch of GPU, very expensive resources. So the thing is, not a single system so far has been designed to handle all of these access patterns simultaneously, right? But agents, kind of the way they operate right now, they don't really care. They just need the data when they need it, and they will decide at runtime what kind of data they need. Right? This mismatch between what the agents demand and what our infrastructure was built to deliver is the underlying tension that we need to solve. And if this sounds familiar, it is kind of pattern you have seen before. This, what they're doing is not really very new, right? It's basically what federated querying was. So agents have these notions of tools, meaning, like a database, a Postgres is a tool, Snowflake, or a data via OneHouse, Databricks. All of these lakehouse warehouses are tools that have data. They make requests across different, all of these, like, data sources. They stitch the results together, then making decisions on top. This is basically federated querying. Systems like Presto, Trino, like all these query engines have had multiples of connectors. If we've tried this before, uh, it was slow, unreliable at best, and it did not scale, right? Most companies end up not doing this at even moderate scale, because you run a SQL query, it will hit like two microservices, a OLTP database and a OLAP database. It's very hard to reason about performance or any kind of, like, operational characteristics on these systems. I It's kind of worse now with agents, because of the agents can do many things, right? And then they can decide what to do. Face this personally every day. I have all of our company systems connected to, like, Claude and all these tools, and every morning I ask it to brief something for me, and it times out every morning, right? So I should be able to kind of get all the context of my company in a single place without worrying about rate limits, API rate limits, and things like that. Be able to reliably get, let's say, a report or a AI brief every morning, right? So this is basically where we are. And this pattern, like I said, never worked. I don't think it'll work now either, right? And then it's any slow tool will add a lot of cost to your system. So what actually happens now? Take one step further. Let's say, okay, I don't let's see, tell me what actually happens, right? So what actually happens if you let your agents loose on any operational system that you find, or any database you find, is it can bypass the data platform, hit operational databases directly, create spikes on production databases that were never designed for this kind of autonomous query generation. Take any OLTP or RDBMS, and try to mix scans and kind of point lookups, it won't scale well, right? On the flip side, it can also query warehouses very unpredictably. These access patterns are not ones that query planners expect, right? And cost become harder to bound, because it'll scan, if you ask for a single record, it'll scan the entire um, warehouse, right? So I mean, vendors could like market this as AI explosion, but it's like extremely inefficient, and it'll, like, really balloon your cost if you just let a AI agent loose on your uh, warehouse without supervision. So they can stitch APIs dynamically, and every API has a rate limit, right? So this will create invisible dependencies. What if this API times out? What do I do? Right? You need to hint the agent on, like, you need to really, like, how handle cascading failure modes in all of these things. So the result is kind of predictable. You cost explosions, because it's unbounded query cost with no circuit breakers here. You lose control over how data is accessed, how often it's accessed, and what decision was being made. So if you want, like, reliable AI agents, you need to make sure that the context can be served at very large scale without kind of frictions like this. So the bottleneck isn't like compute, right? I mean, it's not like we need a bigger compute engine or something. We spent a decade scaling compute. We made Spark and warehouses and all Flink and all these things faster. We made warehouses faster. We built better query engines. We optimized storage formats. We've scaled auto scaling, all of that. But for agents, the compute is not the constraint anymore. The bottleneck is access to scalable context, getting the right information into the model's context window at the right moment, right? So that organizing your data and, like, everything around that is going to be the fundamental challenge that we're going to solve for the foreseeable future, I think. So can the agent reach the data it needs? Can it get that context fast enough to act? Is the context coherent, or is it scattered with no unified view? These are the core infrastructure questions, and this is where the old model is kind of breaking, right? If you like, so far, if you just summarize what we've looked at so far, the traditional systems worked because the workloads are predictable to large degree, right? You know what queries a user would run, what tables to build. You go ask your data analyst or your data scientist, hey, what do you need? Or you need to model this, I'll ingest this data for you in this way, right? So that's not true anymore, right? Agents break that model. They generate these queries dynamically. They can do so. You have to watch what they actually do, and then combine those access patterns and, like, back that into the kind of pipelines and the tables that you will build. So you cannot pre-compute everything that an agent might need. You can do some extent, but definitely not a good vast majority of it. So the context has to be built and served on demand, and this creates, I think, the points out the missing capability that we have, right? The lake house or the data lake, whatever you choose to call it by, is the right foundation. Pretty much every Fortune 500 company, or any like large and small, like there's thousands of companies have those systems, right? But it cannot serve context at agent speed yet, right? And agents kind of need a serving layer that needs this context fresh, consistent, and cheap, without copying everything into another system. I mean, you can always do that, but we always end up regretting that too, right? So you need low latency because context is needed when the agent is deciding, not minutes later. This is the difference between a human and a machine. They need high concurrency because, like I said, one workflow can turn into thousands of autonomous queries. You need to handle mixes access patterns, like what we've kind of have a stock trading agent who's doing both, is trying to understand Nvidia performance by looking at a narrow query for last 200 trades, as well as doing a scan and aggregate over 6 months or something to see how the semiconductor industry performed, right? So you need to be able to do these kind of mixed access patterns on right on top of the lakehouse, right? And you need consistent data freshness into the lakehouse. Like I mentioned, this becomes extremely key now in this new world, because agents cannot afford to act on stale data. So this is where the lakehouse has to evolve. We already centralized the data into lakehouse, but every pipeline, every ingestion flow, every transformation increasingly ends there. Data pipelines are an area that I've been directly working with on. Some of the lakehouse tech out there offers unmatched transformation efficiency already, right? It's a great place for you to store and cook your context and build your context, if you will, right? And you cannot, again, like, build this context by stitching many systems together. Like we see, federated querying has never really worked at model scale. So the lakehouse has to evolve and become the system that serves the context. From a system that simply stores the data, system of record, it needs to move to a system that can now actively serve context. And this is the real shift that we are talking about, right? Let's give it a name, right? This has to evolve into a context serving layer, which is a system that lets agents query all your data as if they were one in real time. And it can replace any kind of federated querying that you need from your AI agents with a single system with governance attached that actually works. Not a pile of tool calls, but you just like hit the like a single endpoint, and then it has all of your data in open formats, governed by open standards, served to you at very low latency and high QPS. So the system like this can make context queryable, fresh, and accessible at agent speed. The important thing is no longer theoretical, right? Recent advantages in storage formats, table abstractions, indexing have changed what lakehouses can do. And for the first time, the lakehouse is no longer a system of record. It can actually behave like a real-time system for agents, right? So it can support both narrow queries, wide queries. You can see in the benchmark, it can achieve lower latency than typical interactive queries while being faster than popular lakehouses on point lookups and doing joins, right? And all of this while achieving really good data freshness. So this changes what a role of a lakehouse can be for AI, right? Because the lakehouse already has unmatched kind of transformation efficiency, storage efficiency, right? So if you now combine that with serving speed, like you get a pretty good system that can hold us and serve us well for the next decade, for this AI era. So what's more is when more teams start to leverage this pattern, data engineers' role is going to see a massive increase in scope. Context engineering is what data engineering will become. And if you want to know more about this, I have a panel later on around the same topic. Tune in and love to see you there. So essentially, the context engineering again needs some context infrastructure with a lakehouse at its heart, like we talked about. It's not, again, I'm throwing words and terms here. It's not, important point is not the label, call it context infrastructure, context engineering, data serving for agents, the next lakehouse. The system requirement is the same, right? The whole stack now has to satisfy these constraints together. These are not new layers, but you need to have storage that can do store most of what you want. You need to attach semantics to be encoded alongside the data, so that agents already know the meaning of all different pieces of data. They need to be able to retrieve it pretty quickly, as we looked at length, and kind of like serve it at low latency, right? This is the architectural pressure the agent workload kind of now generates on top of your data platforms. If this feels like a big climb, just look around the conference. This stack rebuild that I'm talking about is already in motion, right? Across storage, tables, compute, and many different layers that you would see, right? So storage is evolving from just storing structured data to unstructured, semi-structured context. Tables are evolving from being collections of files to context containers, if you will. Compute is evolving from like right, running pipelines to just like having more AI collaboration, to building and operating pipelines. File formats, both bold and new, are becoming more capable at storing the kind of things that AI systems need, right? Like blob types, semi-structured data, efficient encoding of vectors, right? So catch these three talks later in the day, while they're all addressing different problems around storage for data on the Lakehouse, for the AI world. Tables are evolving too. Tables have been pretty fundamental abstraction for data platforms for decades. In this new world, table cannot be simply a grid of type values. It has to manage documents, images, embeddings, records, metadata, indexes, all of those things, right? So the role of a table has now become probably 10x. Your thin, like kind of like a table formats, we just track some collection of files with some metadata, are no longer going to be like sufficient, right? So hoodies extending beyond structured records into unstructured data, embedding, building vector search inside tables is a part of this shift. We're still like yearly, but it's part of the shift, right? So the goal here is to make the table itself capable of access patterns, serving the access patterns the agents need without bolting on another system downstream, right? So catch is exciting talk to go deeper if it's interesting to you. Once storage and tables evolve, compute has to evolve as well, right? So historically, engineers wrote ETLs, Spark jobs, by hand. You have to write and tune and optimize everything for the table by hand. This is changing. AI is already increasingly writing a lot of these pipelines, right? And where I think we'll go is to optimize and operate and troubleshoot these pipelines. This is not just code generation. This changes how engineers interact with compute systems, right? So if you're very curious into about what does the future of pipelines look like, we have a hands-on session for that. It's 25 minutes workshop where you can work with Quanton, which is a fast Spark engine. It's faster than every Spark engine out there, most Spark engines out there. And the idea with AI is very simple: bring AI assistance right into the Spark UI, right? So that it can like kind of be your co-pilot, debugging the Spark job and kind of like getting the pipeline right and kind of getting it optimized with the right context at runtime. Just if you want to try it, bring a laptop with Docker install. The two slots, so pick whichever works your schedule. So stepping back a bit, all of this points to the same bigger architecture emerging right on top of the lake. which is file formats are evolving to store all kinds of data, any shape, any size. The table formats and the storage engines are adding indexing, vector search, any other similarity, ranking, even I think we need to go as far as autonomous table management and on these open formats to really make it super easy for people to build context and serve context. And the context serving layer, the low latency layer, which we discussed at length, and finally, pipelines are becoming AI generated, AI operated, and AI optimized. I think this is the new Lake stack. And the takeaway is pretty simple. The last decade was about infrastructure for analytics, data science, machine learning, like for humans. The next decade is about same infrastructure for agents. That doesn't mean analytics goes away. That doesn't mean like, we are going to vanish. That's not true. But I'm saying this is a new workload. Just like how we added data science on top of analytics on the same piece of data, we're now adding this as a new workload. Uh, autonomous software consuming context continuously, and this changes the nature of data platform. It's going to change the nature of data engineers and what their role looks like, right? Um, so the data platforms used to just produce answers. Now they must continuously serve context to autonomous software. This is a big shift, right, for data and data lakehouses and agent infrastructure. Thank you for joining us today. Happy to chat more during the conference, and looks like we have a bunch of questions. So,
Dude, talk about a bunch of questions. Yes. So the probably the most upvoted, well, besides the one, is this being recorded? Which yes, it is. So that's nice. Second one is from Mark asking, why can't you set up an event-driven architecture for agents? This would allow agents to only focus on what it cares about, and the data schema can be built with a consistent context after you provide the schema CPN tent. There's probably a way to say that I do not know. Definition to the agent.
you could, and I think I do. That's a great question actually, and I do imagine a lot of agent um, tech, agents to be built this way. But let's also remember that having event-driven architectures doesn't fundamentally change the fact that you need also other pieces of context that are historical, and even for event-driven systems, you need like to do event replay and kind of like all of that, right? So what we talked about doesn't really replace that, but definitely it's a very reasonable way to build an agent as a event-driven system that is reacting and responding to events, right? And hitting a big context store like what we talked about, a serving layer to do everything else.
Dude, awesome. All right. So I've got my own question that I'm going to selfishly ask. Forgive me,
Okay.
everyone, but ask a question in the Q&A section and then get up votes from people if you want me to ask it live. Should data be stored in a different way now for agents?
Yes, absolutely. Because like I mentioned, agents are so previously, right? If you have an analyst, you know what the kind of queries an analyst is going to write. They're typically nice to the warehouse, right? And the way the data is stored and laid out. Now agents can do arbitrary things based on what you ask them to do. So yeah, you need to fundamentally rethink how you lay out the data. Maybe you store multiple copies in different formats, or like index data a lot more. All of those are going to fundamentally change.
Nice. All right. Just as a reminder, I'm looking in the QA section, not the chat. I don't have my chat open. So if people are asking things in the chat, I'm not seeing it. Ask in the QA section. Most of the discussion around context engineering focuses on real-time retrieval. Have you looked at the context construction phase itself, designing and organizing context ahead of time? Do you see advantages in that approach?
Uh, Absolutely right. That is where I think this is a really good question as well. Right now, we're just scratching the surface. Even this talk focused a lot on the serving layer for the context, right? But if even going back to our workshop and everything, I think data pipelines are a big part of that context construction, and and they are also going to change in a fundamental way. For example, today ahead of time you need to build some fact dimension tables or something like that, some data modeling to serve data, right? But in the future, I think we'll have to have context, these data pipelines be dynamically generated as well. For example, if you notice an agent typically wants this kind of data, you may want to materialize that into a table using a pipeline. So I think that is how it's going to, like, kind of reverse, I think, the current flow. Today we, humans query, like the analysts and data scientists query the data that you put out in data engineering. I think in the future you need to look at what context an agent actually needs, and then bake those contexts ahead of time using these pipelines, right? That is a shift that is going to happen. We are yearly there. I think I see some teams starting to do it, but not as much as what the, the person who asked the question pointed to.
That awesome. There's a few more that I want to do as follow-ups to those, but I will also say that we're going to have a whole panel session, I think, in a few hours that you're going to lead. You're coming back on here to talk to us
Right.
about context engineering is really just feature engineering and all that fun stuff. So stay tuned for that if you're out there and you really are enjoying the context engineering piece. The one that I know you can answer quickly, Vinod, is, does One House offer a community edition?
Oh, yeah. So today we actually, not the whole thing, but we announced something called quantum.dev. You can go to quantum.dev to just, like, try out our Spark engine. We'll be making rapid changes there, including the AI assist is going to be part of that community edition. We've not called it a community edition, but it's in spirit that is what we're doing.
All right. So it's community edition without the name community edition. There are some awesome questions that I'm reading through right now, so keep them coming, folks. Let's see this one. Why can't we store the context in AgentMD or similar files? Why do we need storage for this? Is it the size of the context?
Yes, absolutely, right. It's so agent.md and these things can be like skills. For example, just using standard agent terminology, you can write skills and tell the agent how to go about doing its job. But fundamentally, you need to connect it to tools, and tools just, hit typically places where you need to pull context from, right? It's not practical to, for example, let's imagine a company like Walmart or like an Amazon. Like, how do you export all your orders into a .md file for an agent to know about them? Right? It's just not possible.
All right. This wouldn't be a real talk if we didn't have a security question. So thank you, Jyoti, for asking about that. What is the best approach for new data schemas to inherit security as new data is being produced by agents?
Interesting. So I'm not sure if I fully kind of distill that, but at a high level, for new data schemas to inherit security, meaning I think a lot of like agents should just like work with existing data catalogs and governance systems to generate these new schemas, right? That's what most people do today. That said, I do think the agents also increase the security and governance surface area a little bit more. This is a topic for another day, where I think you need to now also worry about what an agent can reason about with from the access that you're giving to data, not just verbatim what columns you're exposing, but also what a smart AI agent can automatically interpret, right? This was not a problem before. So those are the new challenges that I'm seeing, but the kind that should be solved by existing systems, I think.
I've got a few more for you, and they just keep coming, huh? So I love seeing this. The chat is uh, they're off the hook. Let's be honest. You all are asking questions that are
Nice.
really good. So next up, I've got, why should we be focusing heavily on query performance since many projects just end up throwing compute at every problem?
Because compute's very expensive, I would say, right? If you, for example, like I mentioned, right? Like, so the slides that I showed you on, let's say, the point lookup query performance, where I compared against Databricks, right? We built a system that can achieve probably 1/4 of the latency, the that means lower compute bills, right? But also it means your agent is now actually waiting less amount of time to return the result back to an user, right? So that I think is critical. So you can actually, yeah, you can throw compute at it, and it will scan the entire table or like do things like that. You can make it functionally work, but is that efficient? Is this going to give you the kind of the latency that you would expect from your for at the agent layer? That those are the real challenges to me. If you don't solve this, let's put two questions together, right? Somebody asked, why do you need context? Why can't this be in an MD file? So we established context has to be in a context store. It's like context is big, right? Now if you now marry that with I need fast responses from the agent, then you need to fundamentally solve this problem of how do I serve large amounts of context very, very fast, right? Otherwise, your entire agent experience will be at risk.
And the other thing is certain workloads require very, very fast and other workloads don't, right? So if you're a voice agent, for example, you have to have super fast workloads. If it's a deep research agent, then people are a little more forgiving on that. So I think there's like looking at the workloads.
Yeah, there's a subtle point here. Let's say you're using, depending on whether you're using hosted models or self-hosting your own model. Let's say you're self-hosting your own model, then your GPU is basically your inference is stalled while it's waiting for tool output, right? So, I mean, this actually wasted. Slowness wastes more money elsewhere for your
Yeah.
company, right? Maybe Anthropic or like OpenAI would amortize that like somehow across the thing. I don't know what they're doing around it, right? But that fundamentally the point is you're stalling, like you're passing the agent's thinking while it's waiting for responses from a tool. That is a problem that we need to solve head on.
Yeah. All right. So here's a great one from Tiger. I'm not sure if that's how you say your name or pronounce your name, but if it's not, forgive me. As lake houses evolve into agent infrastructure, what do you see as the minimum metadata provenance contract an AI agent should emit before its generated query, job, or action is trusted in production, especially for those scenarios where you need replayability, rollback, and audits?
Yeah. So to be honest, this is not my like really my deep strong suit. I would like look at things like Langfuse, other things where they're
Mm,
working on what maybe the agent is doing at like inference or runtime. But from a prominent standpoint, I think, like I said, mostly this is now getting bolted on top of existing data catalogs. It hasn't broken in a very fundamental way yet. Not to say that it won't break, right? But I don't have a
excellent.
deeper answer here.
Well, Vinod, there's a ton more questions in the chat, and I know that you have a few minutes to hang out, so hopefully you can answer a
Yeah.
few of these in
Yes.
the Q&A section, typing them. We're going to keep moving because I have one job today, and that one job is to keep us on time. So, in the meantime, I'm going to send you off the stage. Give it up, everyone, for Vinod. Thank you for coming. I really appreciate that keynote. I learned a ton, man. And now we will see you later. Hasta luego. Moving on to our next speaker. Where they at? Satish, where you at? Can I move you to the stage now? Hey, there you are. Surprise, surprise. You're on the stage and you're ready to rock and roll. We want to hear from you, Mr. Satish. Where you at? Hey, there he is. So, how you doing?
Hey, hi Demetrius. How are you doing? I'm doing
Uh,
good. Thank you.
yeah, I'm great, man. I'm excited for your talk. I'm going to let you rock and roll because we are keeping pace with the schedule. Before you do say anything, feel free to start sharing your screen and I will make a few announcements while you're getting that pulled up. Everyone, so you know, this is now the point in the session where we can have two different tracks going. And if you want to know about more about what Vinod was just talking about in one house, there is a workshop that is happening right now too. So you just can pop on out of this session by hitting the little bar, the little back button, and you can jump into one of the other sessions. But if you want to hang out here with us, let's keep on rocking and let's hear what guardrails for agentic AI look like. It's all yours, Satish.
Thank you so much, Demetrius. Um, I hope everyone is having a good time so far. So today, I'm going to talk about guardrails for agentic AI, more in the context of governing auto-generated SQL and Spark jobs before you do anything in the production environment. So, just a brief disclaimer before I proceed that some of these opinions and ideas which I expressed are solely my own and are not reflective of my position or policies of my employer, etc. So before I start, the whole idea is about the generative AI nature of large language models. So giving you a quick insight here, nowadays you have very popular large language models. You can consider some of these are very generic large language models which are proficient in a lot of things. There are also SQL or programming language based large language models which are trained specifically on the schematics of how a SQL language is based upon. So you can think about this particular where I'm asking a chat assistant what were total sales by region last quarter, and it gives me back a response which is select region, and it looks semantically and formatically very clear and looks perfect to me, which I can then, as a stakeholder, the product manager, use this to actually associate it with one of the tools. So the tool could be a Postgres server, it could be uh, your Spark engine, and you can associate it and run it and get the response out. You can think very similar to what some of these different engines right now are doing. One comparable example could be the Database Genie perspective, where you write ask a question, and you get back a response from Database Genie. The key question here comes is how appropriate is this SQL query in the context of the question which is asked, and is it performant? Is it efficient? How much cost is it taking? How frequently can one rely upon this? So this is where we can think about one particular sequence of events which happens, where you can see in this slide that the user asks a data question. It could be an LLM or an agent planner, and it has all the schema and context because that's where the prompt or the context engineering part of it comes here. So it has access to the tables, columns, and whatever indexes and specific examples and documents which it could have it in context, and then it generates a SQL query for you. And not only does the SQL query generate it, but you also need some contextual data around it. So it runs it in the Postgres or the Spark engine of your choice, and the result is then returned here. Now, one good question is what goes wrong in this direct path? So one of the cause could be an inefficient query. It could be the right query, but maybe it's not perfect enough to execute in that particular engine of choice. The second is the access challenges, whether you're allowed to run a particular query for a particular column. So, does the access capability allow you to let your conditions or access policies be transferred through the agent to the end engine? And the third could be the unintended inference, which is kind of deriving disallowed sensitive outputs which you're not allowed to. One example could be, let's say you're given access to two tables, and from a general perspective, to query it makes sense. But how about agentic and LLM interfaces give you those inference capability to join certain data sets and garner those inferences which are not supposed to be your role specific information? So how do you guard against that? And Similarly, you have other challenges too, like the timeliness gaps in terms of what could be the wrong business answer to the question. And the fifth is the intent mismatch. So the sequel could be valid, but is the result and the sequel answer the question which is put forward by a data engineer, analyst, or a product manager? So the second context here is which we talked about a bit, that is the data model documentation is where the first guardrail happens. So you can think about the data model as to whether you have primary foreign keys, you have fact and dimension joins and how to connect them. Similarly, indexes, schema comments, and example values goes a long way because that also interprets in terms of the statistical nature of how some of these large language models perform with example queries to help you. So this definitely takes it to another level where the LLM with the schema and business context generates SQL but with fewer blind spots here. And this could then be executed through a query engine. Now, the third part comes here is the contextual environment around which the execution happens. So instead of the LLM inventing or running joins and metrics directly, a semantic layer of the tool helps here even before the execution happens. So if you think about this particular sequence where the user asks a business question, the agent or the LLM interprets the intent, and even before the engine executes it, a semantic layer very similar to, you can think about the metric style which kind of is exposed on Databricks, has the wrapper because it gives you another engine which is meant around a very specific guardrail. So you cannot go beyond the guardrail. The challenge here becomes the open source nature of it. But eventually, I think Databricks recently, I think they open source the semantic layer in which it can be implemented in other sources. So I think this brings another opportunity for this pipeline to be integrated in very custom pipelines where your flow is constrained within the wrapping layer. So this could have, we can think about what are the current rules which the database engine metrics has, but this can be extended to customize it against your rules and more specific constraints to be precise. The next part to it is one of the relations is when you run a SQL query, one can validate the context behind the SQL results. So when you run a SQL query, you get the output here. How do we validate the graphic nature of it? Because graphs really help you in terms of joining the relation, finding out the more informations which are correlated. So you get a secondary nature to how the joins happen. So this gives you another layer at which this check could happen. One of the important parts when, let's say, creating a prompt is the benchmarking part of it. So one needs an evaluation set of like a bank question set with the relevant SQL examples, both good and bad, because they help to train the knowledge of the large language model. And in this context, it also helps not only to run against one large language model, but a candidate of large language models to be run in parallel so that to find the right prompt, the right large language model for the right context in terms of different engines which you're running against. And the score outputs the correctness, the policy cost, and the different latency which is expected. One of the other aspect, when you're fine tuning your prompt, is not to do it based on some changes, but to do it based on the metrics. This is where I think the optimizer in the DSPY framework helps in, because what it does is it changes your prompt based on the usage of a particular tool, and this tool in our case could be the Postgres database or a Spark engine, and it runs variances of your prompt against the tool of choice, and it compares the result with your expected. So through a metric enabled automation, you can definitely do it on a fine tuned basis, on a reiterative basis to compare it. So here you have the evaluation set along with your context tools to help you build this fine tuned prompt. One of the perspectives, if you think about, when you run from a SQL query and you want to validate it, we have to see the signals in benchmarks, because when you think about the sequence of tasks which happen in the flow, from executing the large language model to generating the query to validating it against an explain class. So all of these add to the latency and also to the measurement phase. This is where adding the traces enable us to make it more efficient, because we can consider the different parts where we can improve the process in an incremental manner. And at the same time, we talked about the evaluation, the DSP prompt optimization. We also need a human in the loop, because we have to validate how this particular SQL is adding value in terms of the question which has been asked. This is where the business domain, the data engineers, and analysts can definitely help by giving feedback on these responses on an iterative basis for testing. Now, in the previous section, we saw a very simple sequence where the user query went through a large language model, and then we generated a model, a SQL from that particular model. Now, one of the other aspects which we can do here is to improve it through a parallelization. That is, we run the query through different large language models by passing it through a central orchestrator agent, and the SQL which is outputted can be then compared in the final analysis, so that you have a comparative average out but better performing SQL, which is more contextual in the context of the question which has been asked. So some of the side effects of this is the higher model plus the engine cost, because you're choosing different models to experiment here, because you are doing it in a parallelized manner. And the end-to-end latency also increases, because the large language model at the end has to process all of this together. And eventually your audit surface is increasing, because you have now different tools which are being orchestrated in a linear fashion. With this in consideration, now the next flow which we talked about is the execution of that tool. So you see the natural language intent here with the agentic planner, and the agent planner now executes the SQL query on the Spark artifact, and this could then run in the distributed environment with the result back to the user. Some of the challenges here, as we talked about, is the correctness. So it could result in incorrect results to propagate, and the policy effect, which is how do we put the governance layer to act before executing the SQL on the uh, final data set. And eventually you have the cost aspect because of the performance. We do not in exactness know whether the SQL which has been generated is a perfect SQL query to be run in a performance environment. So these are some of the failure modes which one has to govern before the runtime execution. That is, check for the hallucinated relationships, unbounded execution, that is selecting star over a very huge table. So how do you factor that in? Silent Cartesian products, which is you're simply doing a cross join and exploding the row counts and shuffling in a very highly distributed environment like Spark. Fourth is policy bypassing, that is sensitive columns are being referenced by your centralized SQL engine, and also like Spark anti-patterns like doing a collect or writing a UDF, etc. So if you think about all these different factors or the patterns, one constraint cannot help us here. We have to use different methodologies to tackle all of these issues. So, in first, you can think about hallucinated relationship. How do we factor that in? So, one is that we can use a analyst or a the optimizer part to verify whether the keys are matching or the right set of schema is verified. Unbounded execution by checking for these factors. This could also be done with something like an analyzer like Apache Site, where you're running through it and you're measuring the effect of it, whether the predicates are used, whether there is a column filtering. So all of these can be done through different levels of guardrails which can be established. But these guardrails are not established by the large language model, but these are more established by the predictive determined nature of the optimizer and different analyzing SQL or Spark engines. One example, to be more specific, is Apache Site, where you can pass the SQL query through it, verify the nature of it in terms of what it executes against. One of the challenges which I see is it's not about the right or wrong path to it. It's more about how do we evolve the system going ahead. So you can think about a business user asking a particular question. The There are two ways to think about whether the question was asked more as a learning experience or more from a search for an answer to it. How do we choose the best iterative manner to help different use cases when it comes to this? So this is where a an assistant can restate what is the intent plus the assumptions it is taking so that it can be in a reiterative manner conformed by the business or another analyst as to what it is actually trying to do. So with this confirmation of scope, that's where the context engineering part comes in, because one of the factors which results in a huge hallucination is a single static prompt which you're feeding out to the large language model. Rather than it, there needs to be a context engineered index from which different contexts can be searched based on the flow and the task level at which the operation is performing at. So you can think about having different modes of operation, like a quick mode based on needing a quick example, quick solution or an explanation to it, while an explainable mode where you need more detailed performance graded solution. So you're not only using tools like just running it across a Spark engine, but you're also getting the plan of it, running an explain on it, and different other contexts by getting more data around it, which is more in the descriptive mode. So the business correlation really helps you to find the smooth path ahead in an incremental journey to do this. One of the important factors is to establish governance, and these are very well established in different platforms, which are both open source and also some of which are closed proprietary. But the governance layer is very important, and this is where checking if one has access to the particular data set is really important because these are non-negotiable rules and should be blocked immediately even before executing them on an engine of choice. And all of this are eventually logged, but this is where we can save some of the efficiency and the cost in the process by keeping this guardrail check in the very starting of this process. So three governance patterns, um, and you can start as we have seen some of the patterns as AI with AI, where you get a response, but you can pass it to another large language model and get a uh, judgment on it based on an LLM judge. But it's fast, good for semantic hints, but it's still it's an audit alone factor and still is sensitive to your prompts and could be a failure mechanism. The second is a human in the loop, where strong accountability and domain judgment is there, but again, it acts as a bottleneck because of the slow path. The third choice is the hybrid, where the deterministic controls first, with different checks which are available, and the LLMs assist with humans only on the low confidence or high impact paths. And it brings the best balance if you see speed with the measurable safety. But it also needs different policy ownership, telemetry, and all the setup which is needed. This is one of the pre-flight architectures which should happen even before your execution engine starts, where you have the intent validator. This is where you compare the request, plan it using a basic calcite or the engine from Spark, and determine the input artifacts and the target outputs by checking the schema, etc. The second is the metadata resolver. This also comes to the lineage part, the ownership, and all the different tables and columns. Some of these can also be used through the optimizer part. The third is the policy and the access gate, along with the cost performance. This can be done through the explain, getting the stats, partitions, and all of this, if you see, are helping you resolve your queries. And this information really helps your large language model and agents to derive better sequels and in a reiterative manner.
What was that?
Now,
Sorry, man. I don't know what happened there, but go ahead, keep going. I had to kick somebody off. Somebody went rogue on me.
no worries.
Sorry. We'll
Okay.
keep rocking.
So now, if you think about from a technical architecture, how do we build this? So here, if you think about the user query, you have an LLM agent. Now the SQL is generated from the system. This SQL is then passed by Apache Calcite, where you pass the SQL and you generate the AST syntax plus the dialect, and we resolve the catalog and the schema map, then the entity graphs, tables, columns, and the joins. This is more in the specific of the SQL language, but it can also be leveraged on the Spark engine by using the explain for Postgres and explain for Spark. These generate different plan signals, and these could act as the pre-flight guardrail service, where we are checking for the fast access verification, also doing the static SQL risk checks, and the planning, which is the most important part in terms of generating a performant query. And this is how the flow looks like, with passing the AST to resolving the catalog, analyzing lineage. And this not only has to be done on the Apache side or the optimizer level, but also as a policy or scores, because one wrapper engine could also be set up with checks for these values and maps it as to how many bytes it is parsing, whether it should block it, because it could have different guardrails based on a dev sandbox environment versus your production as to how much information should get passed and what. So this is one way as to how you can use bounded LLM judges, but they should not be acting as the root of your trust. They should be more policy oriented, as we talked about here, through the execution of the policy engine. Now, another approval workflow, if you think about the confidence versus the impact, is where do you have the auto approval process at different environments and based on the confidence. You block or rewrite it while in a warning play in the sandbox environment because it all depends upon your use case, whether it's an exploratory environment where you want the learning for your stakeholders, or you are in the very production oriented environment where you want a very strict approval process based on your bottlenecks and the fastness in terms of what you want to approach. One of the things which usually gets talked about is how do you compare cost versus speed? Because if you run across multiple models, if you run a single query in a Spark engine and it fails, you have to rewrite it or retry it again. There's a cost to Spark because it runs on a very parallelized engine. So one advantage or one pattern I've seen here is you can do the static checks, but run it against a SQLite maybe. So you are checking, you're verifying your SQL for syntax and the correctness because there are two parts to SQL. One is whether you are running the right SQL, which is performant, and whether the value which is received as response matches the expectation. So a lot of iteration happens at this stage. So I think a sample data which is put in SQLite or Postgres, which can be run against, reduces your cost a lot. And once this core idea is verified, this can be run on a Spark dry run and then with a full Spark run. So this gives you the confidence gate before the expensive run, but at the same time, you reduce the cost and gain more confidence in the sandbox environment. And this is
Just
how,
a quick time check, dude. Sorry. And we've got a ton of questions. So if you wanted to answer Q&A, it would probably be good to get that started soon.
yes, I think we are good to do that. Yeah, we can take the question.
All right, cool. Well, let me jump in on the questions. There are a few in here in the Q&A section. Just as a reminder to folks, if you want to get your question answered, throw it in the Q&A section. And if you want to have a specific question be asked by me, upvote the other questions. We've got one coming in here that is a single query generated of all relevant queries set generated? For example, when we get total sales of first quarter, then may need to total sales for Jan, Feb, March also. Does that make sense to you?
So is a single query generated or all relevant queries set generated? So it again depends on the context in which you are putting the question. And this is where also some of the React patterns where you are saying a reason about it and then answer it also validates. And some of these large language models could be resulting in the very first where you're just giving a single query and not focusing on the Jan, Feb, and March part. But this could also be explained by giving it more reasoning capabilities by using a better large language model or a bigger one, but at the same time giving it more context around to think around different areas because it again depends on what the stakeholder is requesting to. So I think some iteration here really helps you to find the right choice.
All right. Next one up. I'm just going to start rapid firing them for you because there's a few awesome questions in here. Did you experiment with things like interview phase where the agent has access to metadata tools and goes back and forth with the business user to validate the request?
That's a good question. So uh, it's again when I talked about the sandbox environment. So it has access to the metadata, and at the same point, It can give you those flexible answers of choice. Uh, and Demetrius, can you also put back the question? Sorry, where did
Oh shoot, I dropped it as answered, but it was
okay.
if you experiment with the interview phase where you go back and forth, it has access to the metadata, and then you go back and forth with the user to validate the query.
Yes. So I think this is also based on the iterative phase where you show the answer and you get some more feedback, because you have to think about how we human beings have performed in the past by interacting with analysts in a true, to and fro manner. And this is where we can start in a simple phase, because this gives them the confidence that they are comfortable with this process already, and then start improving upon it.
Cool. So, what if the schema and the values changes? How do you resolve that?
So this is one of the interesting factors. That is, what if if the schema changes? This is where you can think about the dynamic layer, because you have feature engineering and you can fetch these schemas dynamically on the run. So you always have a schema fetching from, let's say, a Spark engine. You can fetch it on the run on the context engineering part. So there are two parts to it. One is the static prompt, while you can do a context engineered SPA. So let's say when you want to validate your schema, you don't feed it the entire prompt, but you know that in this context, you just need the schema. So at that time, you fetch the schema through a tool and feed it in the context to the large.
Last one for you, man, and then we're gonna get rocking and rolling to the next talk. Lynn is asking, how do you avoid creating another data silo with AI platforms?
So if you think about this, mm, we are not trying to create here a data environment, but more of a platform to practice your data exploration as a starting phase. So your data is still there in your data lake, which is the source of the answers or the solutions which the large language model will execute upon. But this is more kind of a phase where you're empowering your product managers or your leaders to answer these questions through self exploration as the very first step, and then incrementally take it to, let's say, empowering them to create new data sets from this through different other varieties of transformational queries as the next step.
All right, man. Well, this has been awesome. I see that folks did not upvote my question, so I'm not going to hold a grudge on you all, but that's uh that's not what I was hoping for. I wanted to ask my own question, but I also want to ask your question. Thank you all for joining this one and asking the question. Satish, I'm going to kick you off now. This was great. We got the next speaker coming up right now, so I will see you soon. Thank you, sir.
Thank you so
Next
much.
up, we're going to be grabbing our speaker. Where are they? This one's coming. We've got, let me tell you exactly, Feihan, Director of Real Time Data Platforms at JD.com. And this is a talk about the latest architecture evolution of Apache Hoodie. Where let's bring it onto the stage and get this rocking. And in the meantime, while we are doing that, for you all to know, as a quick aside and a reminder, we've got two different tracks going. So hit it. Let's go.
Hello, everyone. It's my great honor to speak at OpenXdata, and I'm Hanfei, Technical Director of JD Real-Time Data Platform. And today, I'd like to share our latest architecture evolution of Apache Hoodie at JD.com. In today's session, I'll cover four key parts. First, JD's enterprise data lake architecture and our latest in-house Hoodie features, and real-world business practices, and our future technical roadmap. JD has built a mutual enterprise-grade data lake architecture based on Apache Hoodie, and Beyond Hoodie's native capabilities, including, for example, ACID transactions and incremental data pipelines, we've deeply optimized the framework to fit our unique business needs and developed a series of in-house features. To give you some examples here, binary copy enables fast and large-scale data migration, and partition level bucket index brings flexibility to the number of bucket setting. And we also support partial column updates for multi-time-step scenarios. And on top of these features, we'll build a native I/O, hybrid storage, and our customized LSM tree based MR table format. All of this tailored optimization allow Hoodie to perfectly adapt to JD's high concurrency and massive scale business scenarios. Let's start with our overall ecosystem coverage. And first, for data ingestion, we support mainstream sources, including MySQL, Kafka, Flux, and Hive, and as well as Hoodie itself. And this enables seamless data ingestion across relational databases, message queues, and data warehouses. For compute and query engines, we fully support streaming with Flink, and batch processing with Spark and Hive, and ad hoc analytics with Doris and Presto. This full stack engine coverage meets diverse analytical requirements across all of our business teams. At the storage layer, we primarily rely on HDFS from Hadoop system, paired with our self-developed distributed file system, TrueBelFS. Together, they delivered stable, reliable, and cost-effective storage for our entire data lake system. To date, our Hoodie-based data lake has reached nearly 400 petabytes physical storage and with over 5,000 production tables running stably. Next, let's dive deeper into our core in-house Hoodie optimizations. First up, our LSM tree-based MR table format. This is one of our largest and most impactful features. And the native MR table came with three major challenges in our high-scale production environment: and performance bottlenecks, stability risks, and concurrency limitations. Before I walk through the challenges, and a quick clarification, all our custom features are built on top of Apache Hoodie Community version 0.13.1. So all pain points I'll mention here are specific to this baseline version. Back to the challenges, and on performance, under high throughput write workloads, native MR write and update throughput could not meet our production SLA. And when using bucket indexes with large bucket counts, log file writing triggered expensive list operations. Additionally, row-based Avro storage forced the full row reads for partial column queries, which results in poor I/O efficiency and slow query. Stability, the original compaction process loaded all updated data into memory at once, which frequently caused out-of-memory errors. And meanwhile, streaming compaction competed for resources with Flink streaming jobs, and leading to recurring task failures. So to alleviate this, teams had to deploy independent compaction tasks manually, often a dedicated Spark job, which greatly increased development and operational overhead. On concurrency, native MR table lacked robust concurrent update support. Whenever we run data backfills or data repair, real-time streaming job had to be paused. Moreover, multiple jobs writing to the same table could only run sequentially, which significantly increased the end-to-end data latency. So to solve these pain points, we designed and implemented a custom LSM tree structure for Hoodie. This core in-house capability follows clear and production-oriented design principles. And first, let's talk about file group organizations. Our LSM tree solution is fully built on the bucket index with a two-layer file group structure. The LO layer stores all incremental updated data. Data here is continuously sorted and merged via minor compaction. The L1 layer consists of fully compacted and stable data files generated either through full compaction or during table initialization. This layer design ensures low write latency and efficient compaction and faster queries. We also made two critical upgrades to data transfer and storage. At first, we adopted native compute engine data formats to eliminate redundant data convention overhead. And second, we replaced the original error log format with Parquet. We know Parquet enables native sorting and deduplication while supporting column pruning and predicate pushdown, which delivers massive query efficiency gains. Now let's take a look at the optimized LSM tree architecture for Flink streaming rights, which powers our low latency and high concurrency real-time data ingestion. As you can see on the slide, here's how the pipeline works. Upstream data flows into Flink in native raw data format. After repartitioning, data enters the disruptor ring buffer in each subtask, then flows into corresponding bucket sort buffers for in-memory sorting and deduplication. Finally, sorted data is written to Parquet files and persisted to the storage. We optimized nearly every key stage of this pipeline, which maybe can be summarized into 5 major improvements. First, zero data format convention. The entire pipeline uses Flink's native raw data directly with no extra serialization and deserialization, and maximizing transmission efficiency. And second, we call balanced partition assignment. The original hash partitioning led to severe workload skew. In production, we found some subtasks proceed far more buckets while others stayed idle. To fix this, we built a global view we call remote partitioner that achieves even workload distribution across all subtasks. And the third one, we call decoupled data production and consumption. We leveraged the disruptor ring buffer to implement async processing, separating data reception from downstream write logic. This design improves throughput significantly, even during data backlogs. And also optimize the memory management. We unified the memory allocation via memory segment pool, which effectively reduce JVM GC pressure and stabilize long-running streaming jobs. And the last one, lightweight in-memory sorting. We introduced the binary in-memory sort buffer, which stores data in binary format to cut memory usage. It performs a pointer-based sorting and removes unnecessary object copy overhead entirely. Reading LSM tree data is also an important aspect. We use sort merge reader to complete multi-way merge sorting, merging records with the same primary key from multiple data stream efficiently. And there are two common multi-way merge algorithms, min heap and loser tree. The key difference is that the number of the comparison operations during tree adjustment. When merging a large number of file paths, the loser tree requires only half of the comparisons of a min heap and offering much better performance. And let me briefly explain the mechanism as shown on the right. Green nodes represent leaf nodes, which fetch records from data files and compare values with their parent blue nodes. The smaller record moves upward while the larger one is marked as a loser and retained in the parent node. This iteration continues until the top red node outputs the smallest global record. However, hoodie ML scenarios introduce extra challenges. A single data file may contain multiple records with the same primary key, which requires additional merging while merge function. The original loser tree implementation reuses hoodie record objects, causing data conflicts. So to avoid conflicts, we have to perform deep copies for all output records, which brings huge performance overhead. So to solve this bottleneck, we then designed we call the state machine-based loser tree. We added custom states for all tree nodes and triggered state transitions during each comparison. We also record the leaf nodes indexes corresponding to duplicate primary keys. So with node state management and index tracking, we can quickly locate all records with identical primary keys in one pass. And this avoids repeated tree adjustments and redundant comparisons and completely removes expensive deep copy operations. And overall, this optimization brings a 15% read performance improvement. We ran benchmark tests using TBCDS and Nextmark datasets to compare our customized MR LSM tree solution with the original Avro-based MLR implementation. And all test environments are identical with job execution time and data processing latency as core metrics. The results speak for themselves, and our LSM tree implementation delivers 2 to 4x better write performance and 4 to 6x faster reads than the native Avro-based ML format. Next, I'd like to talk about our hybrid storage optimization. By default, Hoodie's metadata design binds one table to a single file system and a fixed storage path. This means storage clusters load and network bandwidth directly determine job performance. In large-scale real-time ingestion scenarios, this often leads to job stalls and slow file writes and even sometimes checkpoint timeouts. These issues increase data latency and undermine streaming job stability. To address these I/O bottlenecks, we referenced Hoodie Community RFC 60 and implemented the custom Hoodie storage strategy interface. This interface standardizes file storage policies and exposes universal APIs to resolve physical file paths. Built on top of unified Hoodie storage abstraction, our Hoodie hybrid storage can automatically route file operations to different storage systems. So with this design, one single Hoodie table is no longer limited to one storage system. Data can be distributed across multiple clusters, which balances storage load and fundamentally solves single cluster I/O bottlenecks. Let me explain how this works in production. We maintain two types of HDF clusters, and first, we call shared HDF clusters with a large capacity and low cost, but performance fluctuates heavily during offline computing peak hours and often causing job congestion. Second, the high performance HDFS clusters with smaller capacity and higher cost, but extremely stable read and write performance with negligible fluctuate. I think perfectly suited for real-time workloads. Based on their respective strengths, we designed a we call cache layer hybrid storage strategy. All real-time written data first lands on high performance HDFS classes to guarantee stable write throughput. Then async compaction and clustering services merge small files and migrate consolidated data to low-cost shared HDFS clusters. This strategy preserves high-performance cluster resources for critical real-time workloads and reduces the overall storage costs. And during queries, we built a unified cross-storage file view to ensure consistent and accurate query results. Thanks to hybrid storage, the stability of our large-scale real-time ingestion jobs has improved dramatically, and compared with the traditional single storage architecture, our write performance and job stability have nearly doubled. Finally, moving on to our native I/O capability, we developed the Hoodie native I/O SDK to enable AI training engines to read the data lake tables directly. The native I/O solution consists of 4 core models: data invocation layer and cross-language transformation layer, and Hoodie view management layer, and high performance query layer. As shown in the slide, here's the core workflow. Users send requests from the data invocation layer, and the request pass through cross-language convention, and the Hoodie view management layer fetches qualified file slices with partition pruning enabled. And after parsing and shuffling file splits, we can effectively reduce model overfitting and improve generalization capability. And then core parameters are passed to our REST-based high-performance query layer. We customized data fusion physical planes and developed key operators, including Packerator and Submerge and Union, and powered by the data fusion engine and the arrow memory formats. We support efficient file reading, multi merging, and full capability with our customized Hoodie algorithm tree format table. A benchmark results show that our data fusion and arrow-based packet rating is 2x faster than Spark vectorized packet rating and 7.5x faster than the original arrow-based rating. This completely resolve I/O bottlenecks for AI sample engines. Now let's move to the third part of business practices. We upgraded our traffic data warehouse to a Hoodie data lake architecture, where we faced 3 tough technical challenges. And the first one, extreme partition data skew in traffic scenarios, and with a maximum skew ratio of up to 1 million times. And second, massive data scale. Our daily incremental exposure logs reached the 100 billion level, while click and browse logs hit 10 billion per day. which putting extremely high demands on read and write performance, throughput, and compaction efficiency. And third is the original arrow-based MR tables did not support concurrent updates, just as we mentioned before. So any offline backfill or field repair would block real-time write streams. With our customized 2D capabilities, we successfully completed the architecture upgrade for the traffic common layer. We unified separate real-time and offline pipelines into one single data lake architecture, stably supporting 100 billion level daily updates with high throughput and low latency. Leveraging Hoodie partial column updates, one single Flink job can consume multiple Kafka topics simultaneously and write streaming data to Hoodie tables in real time. And combined with our asymmetry story format, overall read and write performance improved by over 2x. And besides periodic Spark job support concurrent data repair and backfill, and to fix extreme partitions skew and unbalanced bucket allocation, we built a partition level customized bucket strategy. And we also developed a timeline service-based remote partitioner and completely eliminating subtask level bucket skew and improving cluster resource utilization at the same time. Underlying hybrid storage further guarantees stable ingestion throughput and enabling reliable near real-time processing for 100 billion scale traffic data. Finally, let's walk through our future Hoodie roadmap. We'll continue to invest heavily in the research and development of Apache Hoodie. And in fact, we have already made some progress in the following directions. At first, we plan to upgrade our internal JD Hoodie version to Community Edition 1.1.x or higher. And second, we'll iterate on native I/O and achieve full seamless integration with Spark and Flink engines. And we'll expand Hoodie's CDC functionality, including decoupling CDC data generation from a compaction service and enabling, we call the input CDC mode. And also we'll integrate the lens format into our system to support multimodal data scenarios. And last one, we'll continue exploring the Flux plus Hoodie combined architecture to build a unified lake stream system. And okay, that's all for today. And thank you all for listening. Thank you.
Excellent. We're going to keep it rocking and rolling. I know there were some questions coming through in the chat, but we're going to move along because I am not doing my job properly. I have not been keeping time, folks, and we've got another talk for you. Let me bring Basak to the stage. Let me see. Where are you, Basak? Hey, there you are. And I am excited to see you again, as always, and very excited for your talk that you're going to be talking about some feature serving, huh?
That is true. Thank you for the introduction. Does everybody see my screen?
Yeah, we see it.
Okay, one second. I love these virtual conferences. You get to connect from anywhere, from any time zone, and you get to keep your sweatpants on.
Yeah.
Like here up is full glam camera.
Nobody would have known.
Down there, no questions. All right. I don't have much time, so I'll kick it off. I'm Bashak from Booking. I work as a machine learning engineer, and today I will talk about online feature stores, which is a critical building block in modern ML systems. But let's start with a simple question first. Why do we even need an online feature store? Every interaction every traveler makes, searches, clicks, bookings, creates a signal. The real challenge is how do we turn those signals into ML-ready features fast enough to actually use them in real time? Because in any user-facing application platform, speed is a competitive advantage. And the faster you actually deliver these features, these signals as features to ML models, the better, the faster you make the predictions. Let's also look at what a feature store is in general to bring all of you on the same page. At a high level, it's a centralized system to compute, store, discover, and serve features consistently across both training and production. One really important dimension here is speed. In modern ML systems, features aren't only static anymore. They are driven by real user interactions, just like how I mentioned in clicks, searches, bookings, happening all the time. And those signals need to be available almost immediately. In our case, for example, real-time features are updated and served within milliseconds to seconds. So that's what enables truly real-time ML use cases. Another key idea behind feature store is the training and serving consistency. The exact same feature values used during training are also used during inference, so no skew, no surprises there. And finally, it brings governance. You have a searchable catalog with clear ownership, lineage, access control, and versioning built in. So the feature store, in essence, provides us these capabilities. And if we zoom out, we see a similar pattern in most ML systems. They all follow this flow. There are data sources, there are feature pipelines processing these data, raw data into features, and those features are fed into machine learning models. And the feature store sits right in the middle, making sure this flow is reliable, reusable, and consistent. It is basically solving the duplicate effort, inconsistent feature values, and governance nightmares. This was a very short introduction to give you an idea on feature stores. Now I'll dive into the feature platform that we have at Booking. But before, let me mention my company. If you're not familiar with Booking.com, I'm hoping you all are users. It's a large-scale platform, travel platform with more than 28 million listings, operating in more than 200 countries, and it is available in many languages. The reason why I'm giving you these numbers is to help you imagine the scale we are operating at. I am from AI platform team. We provide different tools and services to our internal AI and ML applications, and feature platform is one of the products that we provide. But how did we even decide to have a centralized feature platform or feature store? It actually started with a very common request from different teams. I just want to ingest my features and serve. Why does it have to be so complicated? At the time, before we have a centralized feature platform, teams were building their own solutions, custom pipelines, in-memory lookups, just to get low latency. They were working fine, but some of them didn't scale well. Some of them were hard to maintain or hard to standardize. So then we realized we needed a centralized feature platform that provides simplicity so that teams could focus on models and not the infra part. Ease of use, so it would take minimal effort to onboard features to the system, and it eventually allows faster iteration, which gives shorter feedback loops to the end users. Over time, these capabilities evolved into a platform with a centralized repository, which acts as a single source of truth for features, simplified data ingestion from multiple resources, and of course, we also extended our support for embeddings, enabling use cases like similarity search, rec within GenAI ecosystem. But it doesn't go without any challenges. One of the biggest challenges we faced was latency. When you serve features in real time, every millisecond matters, especially for user-facing applications. Think about it. When you're browsing Booking.com, you don't want to wait for pages to load. So delivering features fast is crucial, but speed alone isn't enough. We also operate at a huge scale, hundreds of thousands of requests per second. So we need to also accommodate this throughput needs. And then there is cost. No matter how good your system is, if it is too expensive, it is no longer sustainable. So we are constantly balancing the three things: speed, scale, and cost. And that's exactly what shaped the architecture you will see now. This is our end-to-end architecture. We have ingestion pipelines from both real-time and batch sources. And then we have the storage layer, which consists of both online and offline store and also a vector database to serve embeddings. And then we have serving layer, which allows these features and servings for users to fetch. On top of everything, we have a feature catalog, which handles the governance. I'm going to zoom into each part in a second, but the important capability in this architecture we see is a signal produced by a Kafka event, a signal in real time produced by a Kafka event, becomes available in the online store in milliseconds to seconds, thanks to this architecture. So this brings that huge capability. Let's zoom into each component, starting with the feature catalog. This is how we discover, share, and govern features at scale. You can see different feature details registered. Could be a data type, could be version, could be data source, and we're able to search features by name, type, team, or tag. We can register descriptions, schemas, lineage. So it's not just the storage, the feature platform, but it also brings visibility and control. And the next component is the ingestion layer. As you've seen in the architecture, we support two paths, real-time and batch. For real-time ingestion, we use the well-known technology Kafka. So these Kafka streams capture events and updates feature within milliseconds. And this is very suitable for dynamic features, the features that can change anytime. You can think of the first click of a user, the last bookings of a user. So these are likely to change anytime user is interacting in our platform. But there are also static features. There we use the batch ingestions. We run scheduled pipelines to compute these features in advance. You can think of features like, a good example, the distance between airport and hotel. It's less likely to change, or the property level features, which are more static. So we provide templates for users to basically configure any type of pipeline to start ingesting to our feature store. The next is the storage layer. We use a dual storage setup, online store for real-time serving, offline store for training and historical data. We opt for Amazon Elasticache for our online store, which is Redis, and it is known to be a database for quick key value lookup. It stores features under 50 milliseconds. The offline store is Snowflake. This is our data warehouse, which acts as a source of truth for training and backfills. So we wanted to separate the low latency serving from heavy analytic workloads. And we also have some best practices that we applied to scale efficiently. We implemented multi-cluster design, where feature groups are mapped to the dedicated Redis clusters. This allows each group to scale independently without impacting other workloads, improving the performance and reliability. To ensure our platform remains flexible and efficient, we manage everything using Infra as a code. This way, the deployments are reproducible, which minimizes the risk when we want to scale or update our platform. We chose the self-managed Elasticache solution over Redis serverless because it gave us better control over cost and performance. And of course, we're following cloud best practices using read replicas to distribute query traffic and multi-region replications for resilience. Nothing surprising here, but definitely essential. And last, I'll briefly talk about some use cases we onboarded. We have many teams and use cases utilizing our feature store. These are just some handpicked ones. We have marketing rewards fraud team. They have 6 feature groups to power their fraud detection models. These features now have the highest feature importance, and thanks to our feature store API, they query in parallel with no impact on the latency. We have flight funnel team. They integrated their last seen features to our feature platform, and they use it in their prediction models. We have payment fraud team. They are using first seen dimension features to track their first recorded transactions. And last but not least, we have completed a performance test for ranking team to onboard their large-scale feature group, which contains more than 400 million records. And we tested under a very high throughput, and we were able to keep the latency below 50 milliseconds. So these success stories show how our feature store isn't just a platform, but it's actually a critical piece in several use cases. I'm happy to see that I didn't go over time. In case you want to deep dive into this architectural details and how we implement it, we published a blog. It's on AWS. You can scan the QR code and see the blog for more deep dive explanation.
Awesome. Thank you very much. I am going to keep things moving because I've done a horrible job at keeping us on time. But I think you're available to stick around and answer questions in the chat, right? So
yes,
there's
for sure.
a question that came through in the Q&A. Anybody else that has questions about this feature store, feel free to throw them in the chat. And I'm going to bring on our next speaker now. Bashak, thank you. Adios. I will see you later. And I will also be moving us along. And while I move us along, let's bring Andre to the stage. Where is he? There he is.
Hi,
There
everyone.
he is. How's it going, dude? How you doing?
Good. Good. How are you?
While you are sharing your screen, I'm going to do a first for today, and I'm going to launch one of our poll questions. So, folks, you should be able to see on the right-hand chat area, we've got a poll for you. It's all about your data platform architecture. How would you describe your current architecture? What is it? Let us know. This is fun in a way that we can get you all engaged and interactive. Andre's he's even putting stuff in there too. So we've got some votes coming through. We've got some votes. We'll take it one step at a time. Maybe I will leave that open for your talk, Andre. I'll let your talk get rocking and rolling, and we'll reassess this poll afterwards. All right?
Okay, thanks. Do you see my screen? Yeah.
I do.
Okay, let me start. Yeah, it's nice to see all those nice conversations and great architectural ideas in this conference. And today I'm happy to share our journey, how we transformed our data layer, and share some best practices, what we learned when we added Apache Hudi and Starox, and we used OneHouse for our system in Conductor. So a couple of words about our company. Conductor is the leading enterprise platform for agentic engine optimization, for answer engine optimization, and for traditional search engine optimization. And we provide different capabilities for our customers to understand their brand visibility in digital landscape in different AI engines, like ChatGPT or Gemini or Perplexity, etc. And building the unified data platform helped us to bring together the content data, the search data, the technical signals about your website, and build wonderful product that we serve to our customers. But when it started some years ago, we just had this classic microservices architecture where like the customer sees our product as a single website, but under the hood, it consists of different set of features where each team separately owns the whole pipeline powering those features, from data ingestion, storing the data in the database, then exporting this data via API, and this API can power the features for the other teams, power different backend front-end services. And like we had a lot of cross-team communication and dependencies with this architecture. Like some teams had to literally ingest the data from the APIs another team serves into their own storage, and then expose it as a feature in the final product. So this architecture, we could not really develop and ship our new features really fast, especially at the features that join data from different databases from that comes from different teams, and it included external, like a lot of delays because of communication, because of dependencies between the teams. Our interaction between the services quickly became messy. We had a lot of contract tests covering all those interactions to make sure that changes in one service do not fail the whole product. And we had a lot of like data duplication. Sometimes some data sets were duplicated more than 3 times and stored in different storages, and this approach was driving the costs up. So we started thinking about unifying the data, building the data lakehouse architecture, and so that allow all the teams to access the same data like in the same way and ship features much faster. So here I will show you one example of our pipelines, how it looked before the transformation. We had the data coming from external vendors ingested into the Kafka topic. Then we had some post-processing steps, which included like data, some cleanup, normalization. Then this data was passing data quality checks to reject some corrupted data. And finally, when this data was cleaned, then we had to merge this data that we collected externally with our customers' configurations, information about their websites, some configuration within inside our product. And later, this enriched with customers information data, it was coming into a big database that was serving for multiple features and multiple teams. One more problem you can notice here is that customer configuration is quite dynamic. It can change many times during the day, and we had to recompute this state in this database frequently, which added some like maintenance overhead, and like it wasn't like too optimal way to do the thing. So we started adding the layers of the data lake. We started with the raw data layer, where we just saved all the data as it was coming from our vendors on S3 in the data lake, and it allowed us to, for example, reprocess this data if any component in this pipeline was changing. We could easily take this historical raw data and reprocess it in the pipeline, or we could troubleshoot. Given some problem, we could go back and see like what raw data was coming from the vendors. Next, we built the processed data layer, where it's clean, normalized data, passed all the data quality checks, but it's still customer agnostic data. We used Apache Huri for this step because at that time we did deep evaluation of different technologies that could fit our needs, and Apache Huri won this competition because it was trusted by many companies. It had the most number of integrations with different query engines, and we really wanted to experiment to find the engine that works better for us. And Apache Huri provided transaction guarantees and also like open table formats. Yeah, again, it was able to provide us this flexibility with query engines. We also solved this problem with updates with customer configuration, as we again used Apache Huri to store this customer configuration in separate tables. So in this layer, we kept like customer agnostic data separately, customer configs, which were frequently changing, we kept that separately. And then we also added Starops for our most intensive features that required really fast queries. We really experimented hard with all the optimizations for this processed layer in the data lake. but still for some features we required like sub-second latency, and for this purpose we chose Starox with internal storage using SSDs. While for some other features like scheduled reports, machine learning pipelines, or ad hoc analytical queries, this process layer with Apache Hudi, it's perfectly fine for us, and it serves its purpose. So at the high level, like those changes, they look pretty simple, but when you start implementing them, you immediately get a lot of questions and a lot of options how you should exactly do one step or another. Talking about data ingestion, we ingest the data from different data sources like S3 buckets, Kafka topics, MySQL databases, and even in other Hudi tables. And yeah, sharing the best practices which we learned. Yeah, there are multiple questions that you should answer. You should make those decisions when you build the data ingestion. First is whether your data is mutable or immutable. If you go with mutable data, it can lead to huge write amplifications if you have a lot of data updates, and you can come up with, you can get Spark out of memory errors, and we saw such errors. If your business model allows append-only data, where you can just ingest new data as completely new records not related to the previous records, then it's great to go with that because it makes the ingestion lightweight. Then you can choose whether you go with merge and read tables or copy and write tables in Hudi. And we use both of these table types in our system. We use merge and read tables for some lightweight tables like config data, which is frequently changing. And we use copy and write for heavy pipelines. Together with append only, like immutable mode, let's say. Yeah, then when you decide how to build your system, you should think about what you care about, like fast ingestion of the data or fast performance of your queries. And typically you want to have both, but it comes with some compromises. In our case, we could achieve fast ingestion by switching to merge and read tables, where just new data arrives, it's stored as log files separately. Then we have a synchronous compaction process that does compaction into base files on the background, like every hour, for example. And in this case, the queries that read your data, they actually read from the read optimized layer from the base Parquet files. And so we allow some delay of the data updates before they are merged by compaction. In terms of architecture, so what we got eventually, so we were targeting the medallion architecture. Typically, it's like bronze, silver, and gold layer. If you look at our architecture, it's kind of hybrid. We have raw layer, we have processed data layer, it's like silver layer, but the gold layer goes to Starox for very demanding features, use cases. And regarding partitioning and clustering, I will talk about it in the next slides. Those are also very useful techniques to optimize your data layout in Apache Hudi and achieve even better query performance. So partitioning is a fundamental technique where you partition your data. Typically, you partition it by the date-related fields, like by date or by month. Then when you ingest new data, you normally update the latest partitions. So at some point, partitions become immutable because you don't make updates to older partitions. Partitioning schemas, Hudi benefits from it because it uses partition pruning when you submit a query, and you use partition key in your query parameter. Hudi knows exactly where to go and skip a lot of data. Partitioning is also very useful for data management, for example, data expiration. When you say that we store the last 2 years of data, for example, and anything beyond that we just expire, and it is as simple as just drop partition by partition. Also, you can set access control using partitions, like some of your departments access specific prefixes of the data. What to avoid here? Partitions should not be too granular. They should have just the right size so that the navigation to the exact partitions happens very quickly. They shouldn't be skewed. We had an issue when some partitioning schemas were unbalanced, and the same query had different execution times based on which parameters you apply, which filters you apply in your query. So ideally, those partitions should be balanced and not skewed. Yeah, some link to follow up on this partitioning schemas. Another technique is data clustering. It's basically sorting of your data either globally or locally within those files, within Parquet files where Hudi stores your data. And it gives huge query performance benefits. It reduces the amount of data to be scanned because Hudi knows exactly like which range of data to skip and where your data sits based on your parameters in the query and based on your clustering schema. And normally it's hard to come up with a clustering schema that meets all the use cases. So typically we try to choose such a clustering schema that covers 90%, let's say, of your queries. And we would normally pick from 1 to 3 columns that are most frequently used in the where clause in your SQL query. And this will give the most of benefit with this setup. Yeah, what to avoid here is the file size. When you cluster the data, the file size shouldn't be too big or too small. It should be just the right amount. And you should always try to include the clustering columns in your queries. A couple of words about open table formats. As I mentioned earlier, we experimented with different query engines. We were trying to find something that meets better our purpose. And thanks to the open table format that Hudi provides, it was really easy to plug different query engines or just downstream the data into Kafka or query it with Redshift, Spectrum, or Athena. Yeah, Stark's query engine was our best bet, but for some use cases, yeah, we had to just switch to Stark's internal storage. As of now, we have more than 100 terabytes of data, and it's constantly growing. We have more than 250 tables and flows running, and we run many table services like compaction and clustering on our different tables. And we are very grateful to our partner OneHouse. They helped us with all the experiments, all the setup, and to come up with like the best strategy that works for our business. Yeah, that's all from my side. Thank you.
Dude, good stuff. Well done. We've got some time for some questions and answers. So while folks are typing out their questions, I asked one a second ago, but also as a reminder, we have this poll. So, folks, there's 90 votes so far. There's more than 450 people in this call right now on this stage, particularly. There's another 500 on the other stage. Give us some votes. Come on, it takes one click. That's all I'm asking for. Get involved. Tell us what is it? What's your architecture? Andre, what's yours? Just joking. I
Mine
saw your
is
talk. Trick
house. Yeah.
question. I'm kidding. So let me ask my question that I threw in the Q&A tab. I appreciate in your slides how you gave basically the things to note, like do's and don'ts type of columns. Knowing what you know now in this whole migration, in this whole overhaul process, what would you have done differently?
I think at this moment, some technologies evolved further, and we could try to experiment more with different query engines. Like Starrock's query engine sounds promising for us, so maybe we'll get back to that experiment. We'll see.
Okay, cool. So now another question from Barbosa asking, how do you handle compaction clustering? Do you pause ingestion or do you do it in parallel?
Yeah, actually we pause. In that specific case, we pause because for that pipeline, we don't have very frequent ingestion. So we have these intervals between the ingestions where we can freely run compaction and clustering without impacting our business.
Excellent. Well played. Well played. Well, it is time to keep on rocking and rolling, Andre. I appreciate you doing this. We are going to keep on moving because now we've got a fancy little break. You've been awesome, man. Your talk was great. I appreciate all of it. I'm going to kick you off the stage, and we have got we've got some fun stuff coming up here, folks. I don't know if you have ever been to one of these, but let me see if I can explain what we can do right now. For the next 5 to 7 minutes, I'm going to ask you to, in the chat, drop in what you want me to sing about. I'm going to be your own personal jukebox. And I have a little ukulele right here that will be accompanying me on this. We are going to make some music and make a little noise about what we've been seeing in this. All right. So I'll be watching the chat right now, and just go ahead, throw in the chat what you want me to sing about. Not the Q&A, the chat. And by the way, the poll, it looks like the poll is closed. Let's show this on stage. Let's see what we got. The poll has been closed, and it was that there's hybrid. Most folks are doing hybrids. Yeah, let me throw that on the stage real fast so you can all see the results from the poll. The hybrid one. Okay, now that I've given you oh, I see some good stuff in the chat already. Which key? And just confirm here, folks. Confirm that you can see, that you can hear this. Let me know. Let me know if you can hear this. Yes, okay, so I appreciate how people are talking about data aggregation and a little clustering. Data aggregation and clustering. Scalability on my data platforms. Aggregating all that data's a headache, but there's liquid clustering. Metadata's helping those agents on all my clustering. Analytics does nothing without the monitoring. OLAP layers, data ingestion, data modeling, and of course, how could we forget about the sovereign data? We've got the ETL and the LT. It's the past and the future. Listen to me, my friend. Governance is how we're gonna spell it again. It's the data spills. Those data spills were leaking. Oh, so much data spills. I don't want to think about it, cause the security folks are on my ass. We've got data spills. Folks, I hired a data governance person, and then sadly they said it was just too much for them, so they left. About a week into the job, it kinda threw my data spills for a ride. Parquet and polka keep me alive. Parquet's got me keeping it right. But I wanna know, where's the RBAC hiding in my database? We're leveraging that C++. We're leveraging that. It is those data ingestion pipelines that we gotta handle. Cause we're hitting a scale that's just a little too high. The scale is more than I could handle. Our jobs have changed, we've migrated, and so has the data, but can we trust it? No, we can't. We can't trust our data that's coming from the data lake house. Why, oh why did we ever think this was possible? It's so dirty, I need to deduplicate all this data and clean it, oh so much cleaning. I see a lot of tokens in our future. All these agents are gonna help me clean, cause I can't do it on my own. We'll compress it for better breathing and performance, but oh my god, I gotta go and clean that data. Folks, it's time for our next speaker, because this data's real time and I am really over time on the data pipelines, ingestions, the migrations. We are all enjoying some dirty data today. That's right, at the OpenXdata Conference 2026. Boom. Boom. The best chat that I just saw in there was, I did not have host sings about data pipelines in my bingo card for the day. Thank you all for appeasing my little cosplaying as a musician right there. We are going to keep this rocking and rolling, because if I sing any longer, we're not going to have anybody to give a talk to. I think about 300 people just dropped off in that very moment, but that is all right. We can handle it. Kyle, I'm going to bring you to the stage. This is hilarious. Hey, what's up? Look at we've got some very funny things happening in the chat right
Oh
here.
yeah,
This
I'm
is
loving it, man. Why I have to come right after your song, man? You got everybody warmed up. The 300. You said if 300 dropped, we didn't need those 300 because they weren't ready for the next session to come.
they were not ready. They were not ready for what we were about to bring. That was if you can't handle the heat, get out the kitchen, I guess. That is there. What's your instrument, my man? I'm guessing it is PowerPoint slides. That is your instrument of choice. You
PowerPoint and slides and a little microphone on the headphones. I guess that'll have to be my instrument for today. But nothing to top a ukulele.
well, I'll sing about your talk after you go. I'm gonna hand it over to you. Is the spark you knew is dead is a very provocative title and talk. So I'll leave it up to you, man. I'll see you in a bit.
Thanks, D. All right, I'm very excited to be here with all of you. Thanks for coming to OpenXdata. This is the, I think, second time we've run OpenXdata, and it's really brought together an incredible community of people that are contributors, builders, leaders in open source across a wide, diverse range of open source projects. So excited to keep the sparks flying, hopefully, with this kind of a talk here about the spark you knew is dead. I want to talk about a quiet lakehouse revolution that I see happening behind the scenes, and I hope that everyone can tune into it so that they can stay ahead of where things are moving and how things are changing. A little bit of introduction for me. I am Kyle. I run product and our technical field team at OneHouse. I've been with the company since we started the company. And yeah, I've been building data lakes and data products for about 13 years. And so I've been a large user of Apache Spark. I also, while I was at Microsoft, I helped partner with Databricks, and we created and launched the first version of Azure Databricks. So it's quite a fun time right before I decided to jump ship and build the new future of the Lakehouse with Vinod, who you heard at the keynote here at OneHouse. So today, yes, I'm trying to throw a little bit of sparks, a little bit of provocative statements up front. But before we get into that, if I'm going to tell you about how something you knew about before is potentially dead, let's talk about the history of it. Let's look at the original rise of Apache Spark. This is an article that I found that's dated 2014. The internet's a beautiful place. We are now collecting history. And so this, for the speed in which data moves. This is a historic relic at this time, at this stage. This should be in a museum somewhere, 2014. You can see even the Databricks logo, what maybe their original logo looked like back in 2014. But this article talks about how Spark has surpassed Hadoop in popularity. And you can see the little chart that they drew on this article. And so this is a very exciting time for the data community. At this time, I was actually at Microsoft. I was building a hundreds of terabytes, even petabyte scale data platform for Microsoft Office products. They just launched O365, the online web applications, those kind of things. We had incredible amounts of data and telemetry that we were dealing with and wrangling with. I wasn't using Spark yet. I was still on some Hadoop and other internal tools, but I was watching this firsthand, this rise of Hadoop in 2014, or of Spark in 2014, and as it started to grow into the incredible community that it now is today. And how is that relevant still holding up today? This is a poll and research that was done in 2025, so it's very recent here. And this was an analysis of job postings for data engineers, and it started to tally up the required skills that were listed for all job postings across data engineers that they analyzed. The number one tool that was listed as required for jobs in 2025 for data engineers was Apache Spark. You can see that listed there on top, followed by Snowflake, Kafka, Hadoop, Databricks, other things that you're familiar with. But Apache Spark is something that is in hot demand even still today in 2025, 2026. Now, another research article, and you can message me for the links to all of this research, was analyzing, like, if you're using Spark, what's the flavor of Spark, or how are you deploying Spark? How are you using it today? Of course, majority of folks were found using Databricks, which they're original creators of Apache Spark, and they have an incredible product as well. Close behind that, is actually folks running is Apache Spark in open source, leveraging Kubernetes and running this on their own, leveraging the open source version, handling deployments and management, configurations, tuning, and they're happy to build their platforms this way. Now, as we look at the relevance and the growth and where Spark is today, let's talk about two things that are changing. Let's look at what I see as maybe the largest change in the last close to decade, about 8-year span here. And then I want to tell you what I think is next for the next probably just about 2 years until the next wave gets finalized. But here, 2016 to 2024, one thing that was really impactful, Spark's not idempotent. And if you like this funny meme on the side, this can happen to your data in real life while using Spark. You can have partial writes. The job can fail midway. It has eventual consistency. The compute by nature is distributed. And so there's multiple nodes that are doing tasks across, and it doesn't have like an all or nothing transactional definition for how it's writing data into your file system. And so because of that, there were some interesting technologies born in this era, 2016 to 2024. The first of those was Apache Hudi, who our founder and CEO of our company, also the one who gave the keynote today earlier. He's the original creator of this technology. He created the world's first lakehouse when he was an engineer at Uber, and Uber was going through their massive growth period for data and their business as a whole. And so Apache Hudi Iceberg was also created in about 2019 from Netflix. And Apache Hudi, Iceberg, Delta Lake I didn't list here, but they're all three very similar in nature. Each of them has a specialization in certain ways where Hudi, for example, is amazing and great for fast, near real-time, fast-moving data. That's something that you just saw in the last talk from Andre at Conductor after they had evaluated that way. But all these projects are great, and there's something common across them that was solved in the last kind of era, 2016 to 2024, that was really important, that idempotency. We were able to bring ACID transactional guarantees to the write operations that happened with Apache Spark. So now we've got a compute framework that is massive and distributed, that is able to handle large scale of data, and it can process it quite fast. And now it can also process it in a safe ACID transactional way. That's one thing that the formats opened up. Other things that it opened up, of course, you've got additional metadata layers on there that can improve the performance of how you access and continue writing and mutating that data. It allows you to then express things like schema evolution or different ways that you can define the partitions of that data as it's being written. So these lakehouse table formats really cemented that position for Apache Spark and made the lakehouse style architectural pattern become like the first and foremost thing. I like the poll that you had up there, Demetrios. It did show interesting results that many people were lakehouse first data platforms in their companies. There was a large portion, if I remember, it was 20 something percent of warehouse only. And then the largest was 38% or so. I could be remembering wrong, go check the poll, were hybrid, some warehouse, some lakehouse. And so pretty much everyone's got a data lake today. And if you have a data lake, you are very highly likely to use a technology like Apache Spark. But let's talk about what's changing right now. What's changing out from underneath us? It started to change just and maybe in about last year. And I predict that this would take only about till 2027 to kind of fully operationalize, get through the community and have some new things that are really solid and adopted and have many success stories from others. So the thing that has been changing recently, I've got this sad picture of this cup of coffee here, and you might reference and follow me here with the link of coffee to Java, Java to JVM, JVM to Apache Spark. Apache Spark is all based off of the compute that's being processed and managed inside of these JVMs, Java virtual environments. And now inside of their hardware has been evolving much faster than the programming language has been evolving. And so hardware, we're talking like when you're in the cloud on EC2 instances or and you're picking different types, the physical hardware has evolved faster. It's created new even instruction sets and operations that are available at the lowest layers of the hardware to accelerate different types of operations. For example, there's a operation called a SIMD operation, and it allows you to process multiple values at the same time and parallelize this. Something that Java, when your process is in a JVM, it's not able to take advantage of. And so something that's been quietly changing for the last year or so is how Apache Spark, it's maintaining its position as the incredible compute orchestrator, and the really hardened and battle-tested APIs that it delivers for allowing people to write complex ETL jobs, even generative AI applications, machine learning. It is a well battle-tested, well-oiled machine for being compute orchestration, and how it federates that plan out into multiple distributed nodes for execution. But the core of the engine, if you were to say, is being now created into a portable layer. And so you see a list of different types of companies that are working on initiatives in this world. Databricks was one of the first to get in there with what they call the Photon engine. And so they did a rewrite in C++ of some of the execution parts and how they execute Spark jobs. One House, we're a new player here in the market. We have created an engine that we call Quanton. And Quanton, in a similar nature, it allows you to have vectorized or native execution for your Spark jobs. Similarly, I won't read them all, but NVIDIA, Intel, Meta, all these companies are building out native execution engines that can run as a component inside of or attached to or as part of Apache Spark. So what the beauty of what happens here, like I'm most familiar with Quantum, of course, because this is what we've built and launched what we're running here inside One House. But this diagram, this kind of sandwich, if you will, on the right-hand side, you keep the Apache Spark APIs the same, 100% compatibility, no tweaks, no changes. The code that you've written to write your Spark job stays the same, no impact. On the bottom of the sandwich, you have the open table formats, leveraging Apache Hudi, Apache Iceberg, Delta Lake. Don't make any changes for how you're accessing that data inside there, but change in the middle, how the execution runtime operates, and what I would call the storage engine. The storage engine is then how you talk to and communicate with and leverage advanced statistics and metadata around the open table formats. So these are the two components that, at least here with the Quanton, we've been working very hard and diligently to accelerate so that your Apache Spark jobs can go much faster. To give you a view into this, we've done countless benchmarks. You can scan the QR code on the bottom right. This is only one TPCDS benchmark, but we've ran TPCDI, TPCXBB, Lake Loader, so many different benchmarks that we've documented in depth, and you can scan that QR code for a blog that goes into the details. But you can see us side by side with Databricks with their Photon engine, Snowflake, even EMR, where they've added some compute accelerations, adopting some open source technologies. You can see where Quantum from One House stacks in a price performance competition with these types of engines. So Quantum's faster because some of these things I mentioned, like SIMD, vectorized execution, these are techniques that might be a little bit similar to open source projects. You might be following things like Gluten, Velox, Data Fusion. We also add in there aggressive query plan optimizations, high throughput data scanning. Our Spark runtime is now very aware of the storage optimizations that need to be done. Because we come from a historical background of being the pioneers of open table formats and creating these, we know very well how to deeply leverage Hudi, Iceberg, and Delta Lake to accelerate your jobs. So we've created ways to amortize execution costs. We exploit repetitive patterns. There's so many ways. Scan the link on the chat window to make sure you can read about these details in depth. I'm trying to watch the clock as well. Demetrius, drop me a note in the speaker chat on what time I should wrap my talk. I want to time it right here too. Looking at one layer deeper, okay, how would you use something like Quanton? Of course, I'm not going to cover how you use all the others, but I'll give you an example here. And actually, this is something that I think is unique. and some exciting things that I want to announce and share with you today. So from a one-house perspective, we have two main ways that you can adopt or try to use the Quanton accelerated Apache Spark engine. We have a BYOC model. What I call this is bring your own cloud, where we deploy a serverless data plane inside of your VPC. So you're on AWS, you're on Azure, you're on Google Cloud, and thanks, Dee. And you are now deploying inside of your own VPC a data plane that has a serverless distributed compute inside there. Now, the other model that we have is what we call our Quanton Kubernetes operator. And this can be cloud or on-prem or in any hybrid environment, anywhere you have running Kubernetes. Where you have a Kubernetes, you actually can, in a very lightweight way, deploy our what we call Quanton Kubernetes operator. So let me accelerate. Oh, 1205. Good. Okay. We're solid. All right, so the steps to get started are very easy. You can download a YAML configuration file that we give you. You run a Helm upgrade, and you reference that configuration file, and then you just execute your Spark jobs. No changes to the code. This kubectl apply, and you have your CRD for your Spark application. You just run the same job, but now you've done a Helm upgrade and you've installed the operator inside of your K8 cluster. That's how you can take advantage of and use all of the accelerations from Quanton from OneHouse. Now, one thing I want to call out, there is a live workshop happening later today around about 3:35 p.m. with Sagar from our team here, who's going to give you a hands-on workshop. You can go step by step with him, and you can try this out later today if you want to go to that session. So yeah, now I want to talk just briefly about the platform, and then I'll show you a very fast speed demo. So OneHouse, I've talked about this engine and open table formats a lot. But on top of these building blocks, OneHouse as a platform offers fully managed ingestion, from ingesting your streams, your files, or your databases. Stream all that data into open table formats in your cloud storage buckets. And then we also have a full Spark and SQL ETL platform, where you can take your Spark jobs, no code changes to what you might have been running with EMR or Databricks or anything else. Now you can run those jobs on OneHouse and monitor and accelerate those jobs. We also just recently launched what we call Lakebase. It's an analytics and AI serving layer, which allows you to, it plugs in really well to Vinod's keynote, how he was talking about where there's differences in how now agentic workloads are coming to talk to your data. And so we have some very interesting support there. I won't go through all these details, but let me show you some speed run of the platform live. The first thing that I have loaded up in my OneHouse console is actually a flow, what we call a flow. This is the fully managed ingestion platform. This is ingesting data from, if I go to setup here, this is ingesting data from Kafka, and it's a Confluent Kafka connector. And I can see how much data has been ingested in near real time. I can see how much data was pending to write as it's building up in the queue. And I can see how fast the sync duration was on average for these commits and for the operations. So it's very easy to come in and set these things up. You see I have multiple that are running. I can say, let's add a new flow. This is as you would expect. I can add some sources, put in some details about configurations, choose, for example, tables or topics that I want to ingest, and then I choose a destination and a catalog to synchronize to. All of this runs on a cluster of your choice. So the next thing I'll show you is how you can manage virtual clusters. I come here to my clusters tab. I have a whole bunch of them in my little demo environment, some that are running. If I want to create one, I say, let's add a new cluster. I can now choose a type. We're able to run SQL workloads, Spark jobs, even open source engines if you want to deploy a different style of technology. You can deploy one with a Jupyter notebook fully loaded, ready to go, and even Lakebase itself. Inside here, you choose the scaling ranges, which catalog you're connected to by default. You hit go, your clusters are up and running. So let me show you perhaps one of these clusters. It's a Spark cluster. And I can monitor the usage of the cluster. I can see what jobs were submitted to this cluster. I can go into these jobs and see individual runs. And inside of the runs, I also can get access to the Spark logs. I can open the Spark UI, all of the things you might expect from a well-oiled Spark product machine. In addition, we also have, as your data is created, table services that run in the background, compaction, clustering, cleaning. Andre had mentioned some of those details about managing a data platform, and all of this runs for you as you have it. So that's just a little bit of a speed run here for OneHouse. The other thing that I want to show you is something brand new that we've launched today. I thought I had a slide. Yeah, I must have skipped this slide. The thing that we're announcing today is a new free tier for OneHouse. This is a completely new freemium model, no sales involved, no credit cards required. Go to quantum.dev or scan this QR code. And there is a website here that I actually vibe coded this website. No code was ever written. It was all just prompts and Claude. And tell me if you like the website or not. It's brand new. We're launching today. But you can come to there, create an account, and there's documentation and everything for how to get started in a very easy way. If you want to upgrade, you can talk to us later, but hopefully this gives you a really fast way, even from the start of this conference, to now get your hands on and try it. We'll be doing a live workshop on this later near 3:30, 3:40. Come to that as well. So with that, I just want to wrap up the session, and I should be watching the chat for questions. So start adding those in questions from in the chat or the QA window, and I'll be to those soon. And here, that's that QR code again to get access to quantum.dev. Or we also have a Slack community. If you've been loving the chat's on fire in here, Demetrios, for everyone that's having a good time talking on chat. If you want to continue conversations, we've got a Slack community for OneHouse that you can scan the QR code on the right. We'd be happy to chat. It's a new evolving community. So come talk about what you want to talk about, and we'll evolve the channels. Let's adapt. Let's make it something that the community can use for open source data.
Yes, sir. So I've got some questions while people are doing the cat meme and frantically typing away their questions.
All right. All right.
Recently, I actually did a podcast with some folks from Uber, and they were saying that they had all these resources to GPUs, right? Or they had all these GPU resources, I think better said. But the bottleneck wasn't the GPU, it was getting the data to the GPU. Because the way that he explained it to me was GPUs are very hungry, and they're just like, they're always, they eat the data really quickly. And so you have to think about all of the different stages before it gets to the GPU and recognize where the bottlenecks are a little more upstream. What you just presented, is that going to help in that regard?
Sure.
Like,
there's something that's similar in nature to what you're describing. I actually studied electrical and computer engineering, so I really love that analogy of the GPUs being hungry and how like the CPU architecture can then come and because oftentimes, and that's the bottleneck, is how you give data fast enough to the GPU. Because the GPU is revved up, ready to go, and it's got a great architecture for parallel processing, but the speed at which you send it to there. So what I've shared today with Quanton and the accelerations that we've driven inside here, it isn't about how to spread data or serve data across things like CPUs and GPUs. Something I would recommend for folks that are interested in that topic to read more about is actually Ray. There is a presenter from Anyscale on the agenda list. Look, or Control F on OpenXdata.ai for Anyscale or Ray, and you'll see a great session. Go to that session. It talks a lot about how you can accelerate data and get it faster to GPUs as well. What I'm talking about inside here, these types of accelerations are a little bit closer to just the CPU architecture and how you can plug into different instruction sets inside of the CPU when you go from writing and having processes run in a JVM to now closer to hardware production, things like C++, Rust, these other types of programming languages that let you tap in, wire in a little bit deeper. That's what I'm talking about here.
Nice, nice. All right. Question from Loic. I probably butchered that name, and I'm sorry if I did. Okay, since Java is the core technology for most of the scalable services we are using, in your opinion, what is the likelihood that the JIT compilers are going to leverage better the advancements made in the past couple of years in CPU and GPU?
Yeah, I think they have to. If the community cannot make the compilers leverage these advancements faster, like it's not sustainable for that community or technology to continue being dominant and being the first and foremost choice. Like Java's de facto standard basically for data and data processing today because of many reasons. You know, Hadoop or Spark or some of these things could be a part of it, but I am not plugged in deeply into the communities to watch that progress or see what the discussions are. I haven't followed it myself personally, but it's got to happen. The JIT compilers have got to be able to leverage this stuff better. Hopefully it happens. So it'll be the best for all of us.
All right. We are going to ask one more, and then we got to keep it moving. It's about security. How do you plan to implement data security with the complexities of the platform?
Yeah, awesome. So data security, this is actually something very interesting. There's so many layers when it comes to data security. I'm going to zoom in and maybe answer the question from a perspective of, I saw in your song as you were singing, you talked about RBAC. RBAC controls and data policies that are written for access controls. One thing that I see really a problem across the data world today is your permissions are created and authored. These policies are generated in different systems. You're using AWS Lake Formation perhaps, but you also are using Databricks and they want those policies written in Unity Catalog. You're also using Snowflake and they want the policies natively written in that platform. Across the board, every single system, you have to re-author your policies. One thing that's very exciting, we announced maybe it's last month, alongside with Microsoft, is actually what we call OneSync, and it has a data policy translation mechanism that allows you to take all of the RBAC policies that you've written in, for example, Lake Formation. You can extract, translate to them to Unity Catalog and commit them to Unity Catalog. So now your Unity Catalog can have an exact mirror of what you had inside Lake Formation and vice versa. It's actually an omnidirectional sync that we could do between Databricks, Snowflake, Lake Formation, Glue, HMS, just in general. And I think we have a couple other catalogs, if not now, then in the works. So yeah, it's something that makes that governance a lot easier. Hopefully that helps.
Excellent, dude. Well, I think it is time to kick you off the stage.
All right. Good
Say
to be
adios.
here. Thank you.
I
right,
bid
adios.
adieu. Now we're going to keep moving. We're going to keep this rocking and rolling for the next speaker. A friend of mine, Mr. Will Angel, is going to come up. But I'm wondering, let's see, where is he? I'm going to bring him onto the stage now. Will, there he is. Okay. So, what's going on, man?
Oh, things are good. Nice weather here in Washington, D.C.
Lucky you. Lucky you. I like it. All right. So we've got some fun stuff happening in the chat, as you know. What's your instrument of choice, Will?
Ooh, well, I've got a bass and guitar that I don't play as often as I'd like, but I've gotten, Claude Code to generate some MIDI music and stuff like that.
That helps. That helps a lot. All right. Well, I know that you were enjoying the music earlier. Can I play a random video for you before we get to your awesome talk?
Let's do it.
Let's see if I can bust this out real fast. I'm going to try to grab it and hold on one sec. I'm going to pull it up here. Fair warning to everyone. This is not going to be your normal video that you see in tech conferences. Here we go. Can you hear it? Yeah, pH is a little high. I think it's going to rain in about 2 hours.
So that's been up there since about 1992. I installed it, and we've seen a few finches that have taken root there. It's also been home to some sparrows.
Nice.
That's it. PSA, everyone. There you go. Will, the stage is yours.
All right. Well, let me bring up my slides then. And I will actually have some birds as well, because images, photos, and videos of birds was actually one of the primary reasons why I started this project.
Oh, I knew it. I could feel it. I could sense it. All right, here we go. I'll see you in 10 minutes.
Cool. Thanks, Demetrius. All right. So my name is Will Angel, and I'm going to be talking about building a personal data lakehouse. So I'm going to give you all the summary up front. I built personal data lakehouse. I call it P-Lake. It's got a command line interface as well as a front end that you can see a screenshot up here. It's built with Python, SQLite, and Parquet. SQLite serves as the data catalog and the query engine. Data is stored primarily in Parquet with some native file format storage as well for images and video, and some links in place for larger external videos. It all runs locally or on my local network attached storage device, so that's sort of dual client mode there. And it's primarily a rich-based command line interface and then fast API HTML front end. The data lake also does enrichment on ingested data, specifically uses Whisper for transcribing audio and video, and then does OCR on images that have text, and then does some cool stuff with machine learning to detect animals and tag those animals, which, like I said, was the primary impetus for actually doing this talk. And the big thing is it gives me integrated search across all my data. I'll show you some examples of that, but this is super useful and is done primarily with BM25 and SQLite's full text search. So, and I'm going to give you the key takeaways that you should think about for building data systems before I dive into them more. I've also got a screenshot of the front end showing search and an OCR image. So my key takeaways, got two primary ones. One is be mindful of your data access patterns. Data creation and the way that you access your data really drives all the architectural decisions. And consider your data, because the variety, volume, and velocity of that data is really going to influence what you actually need and build. Consider your non-data requirements as well. Things like security, RBAC, like we just heard, compliance, and then reliability and robustness. So now that I've given you the bottom line up front, I'm going to give you the overview. I'm going to answer the question, what is the data lakehouse? Why would I build one? Some of the considerations there of building it. I'm going to talk a little bit about the differences between an enterprise TM system and what I've ended up building. And then I'll talk a little bit about actually building the personal lakehouse. So what is a data lakehouse? The data lakehouse combines the best features of a data lake, like decoupling storage and compute, which makes it cheaper to scale, open storage formats for flexibility and lock-in, or less lock-in, with the best features of a data warehouse, which gives you more powerful and ergonomic abilities to query and aggregate data. Nice things around governance and structured schemas, and then less file management, because having to manage all the files yourself is kind of a huge pain. So why build a personal data lakehouse? And there you got to ask the question, why build any data lakehouse? And that's because we have data and want to manage it. I've got a screenshot of the management view here that I have for P-Lake, and you'll note it's got a bunch of different data sets and things, and I've got about 1.5 terabytes of data, of which most of that is actually photos. And yeah, I've had this on a bunch of different hard drives, a bunch of different computers, in the cloud, some local, and data it's only useful if you can actually use it. And the less managed it is, the harder it is to use. So by bringing this all together, a data lakehouse, personal or not, is actually very useful. And just to give you a sense of the scale, I have over 250,000 photos from years of doing amateur wildlife photography. So that's quite a lot of photos to manage. And I also have a lot of other siloed data. I've got documents, emails, chats, browser history, photos, memes, wildlife photography in addition to the regular photos, wildlife videos, some regular videos, some movies, all that good stuff. So a lot of data in different places that you can kind of search through it in the like file system and all that, but that gets not very ergonomic, not very useful. It's like if you've ever had SharePoint or Google Drive with just a billion things in it, you can't really use that. I've got a screenshot here of the statistics view that has some things around like activity over time as far as when records were created and some fun things around email analytics. So let's talk architecture. When you build a data lakehouse, this is an Australian boo-boo owl, by the way. When you build a data lakehouse, or a data system of any kind, you have a couple of architectural considerations, and the data is the most important part. And you've got the 5 V's of data, which are velocity, how quickly you get new data, volume, how much data you have, variety, the different formats and types of data. And these 3, I think, determine your data system complexity, where the more volume, velocity, and variety you have, the harder and more complicated your system is going to be. And then you have veracity, how trustworthy or correct is your data. And then last, and I think the most important one actually, is value. How useful is your data? Because all these things, these considerations that go into building a cool system, they don't actually matter unless the system is useful to someone. And in an enterprise setting, that means like it helps people make money or sleep better at night. You also have some non-data architectural considerations, things like user access patterns. Are your users going to want a GUI and auxiliary tooling? Here you can see on the right, I've got a catalog view that I made. If this looks a lot like Databricks and some other things like that, it would be inspired by that. Also, questions like, are your users going to do a lot of interactive querying? Are you going to need compute for that? And if you have a lot of them at once, what's that going to do to performance and reliability? If you have a lot of people doing a lot of querying, what does that do for your availability and latency? And so you need to think about how you're budgeting both cost-wise and overall observability and monitoring for that. You've got maintenance considerations around how much time do you actually spend maintaining your system and your data. Backups and recovery mechanisms. If something happens, where's your data? Is it backed up? How do you recover from that? And then security. It's important to have secure access and RBAC, which are role-based access controls. That's what's mentioned in the last talk. Things that enables you to do field row and column masking, which, if you have enough people and enough data, is a very cool and important capability. You've got compliance. If someone changes something, can you see what happened with audit logs, SOC 2, HIPAA, et cetera? And then cost. How much does it cost to actually run the whole thing, and does that meet your budget? Because if you have a lot of money, I used to be a consultant, I'm happy to build you something that will use as much or as little money as you want. The more the better. So, I've done a bunch of enterprise TM work in my career, and that's not always appropriate for either a company. Maybe you don't have the same requirements everywhere, and for a personal project where there's only one user, me, you don't need a whole lot of stuff. So I'm just going to say, the system I built is not enterprise grade. I've built enterprise grade systems, and this is not that, and it doesn't need to be. I've got a screenshot of the query interface here, so I can actually go into the system and write SQL in the HTML front end, and that's pretty cool to be able to actually look at photos. You'll note that the actual query there is calculating the area of pixels, and that top size is my nice Sony mirrorless camera. So to talk about the data differences between my system and enterprise system, you've got the volume, the velocity, the variety, veracity and governance, and enterprise is a pretty wide distribution depending on what the enterprise is. Sometimes you have enterprise systems with small amounts of data, sometimes huge amounts of data. I think one of the other talks today is on building an exabyte scale data lake, which is pretty cool. My data is annoyingly medium, definitely won't fit in Excel, but it doesn't quite fit in memory, and but fits on a hard drive, big hard drive. But for velocity, mostly I'm doing weekly batches. In enterprise, I've seen quarterly data jobs that are super valuable, and I've seen sub-second real time. For variety, I unfortunately have lots of photos, which are an annoying data format alongside audio and video. So I think in most enterprise data lakes, generally you're using structured tabular data, and that makes things usually a little bit easier to manage. But then on the governance side, for me, I was focusing mostly on ingestion integrity, making sure that when I brought data in, it was good. That's important for an enterprise, but in an enterprise, it's not just is the data correct, is it coming in right, but also where did it come from, who knows what it does, how do you understand that, lineage, governance, discoverability. Those are a lot more important when the data doesn't mostly fit in my head. So I'm gonna share a little bit of experience about actually building it. So I started with the core data catalog, implemented that, and then added the first data source and iteratively added features and additional data sources. This is the way that you should build every data system, because if you do it all at once, you're never going to finish. I will say, agentic coding, there's still a lot of places where it leaves room to be desired, but for greenfield projects, it's fantastic. Cloud Code, Cursor, and Kilocode got me to do way more than I was originally expecting feature-wise. That said, testing is essential because I had places where, the agents implemented something and broke something else, so that's important. And I will say, you can do a lot more with agentic coding, but even frontier models need to be steered and prodded to do pipelines correctly, because things like idempotence, backfill and sync logic, they're getting that all to work, not just on the happy path, but on the unhappy paths. That still requires a lot of prodding and expertise. And overall, the hardest part was deciding, how much did I want this to be more like a data lake or a data warehouse? And data lake house is the sweet spot because you get the best of both worlds most of the time. But that's sort of the inherent tension and was part of what was hardest about this. And got just a few more points before moving to the Q&A. Being able to search through all my photos with metadata ML generated tags is super cool. Local ML models are getting really good, not just for LMs and coding, but for actually doing image recognition. And the better your data is, the better you can actually use AI, because I wasn't able to do all this cool ML tagging until I brought all the data together. And then, open source tooling for all this stuff is really good, which is why we're having this conference. And with that, that's my talk. Thank you.
Yes. Will, awesome to see what you've built. I am so stoked on that. I have a few questions while people are typing away asking their questions. Number one, on that last slide to the last slide, most pertinent questions are, what models were you using? How big? What are we talking here?
Ooh, for the image recognition or the coding?
Yeah, both.
Both. For the coding, it was a lot of Cloud Code with like Opus 4.5, Opus 4.6. For Cursor, a lot of the actually Composer 2 is a remarkably capable model. And then for open code, usually either like the Kimi K2 or some of the Quen models. Those are quite good. For the local image recognition, for OCR, I was using just like conventional off-the-shelf non-machine learning Tesseract, which is very robust. And then I was using the variant of the iNaturalist model for doing animal tagging, and then using a model called Megadetector V5 for actually recognizing that there was an animal.
Nice. All right, very cool. And you had to give, like finger to the wind, how much of this whole project was vibe coded? What are you saying? 100%? 90%?
So vibe coded, like places where I didn't actually look at the code, I'd say 10%, maybe 20%, because making sure that this actually worked and moved my data around in the way that I wanted. I built this so that I have enough confidence where if I had to delete all other copies of the data, I'd still be a little nervous, but I'd be willing to do it.
Excellent, dude. It looks like, what do we got? Have you found ways to model relationships between items, or most of the meaning carried through tags and queries?
Ooh, yeah, that's a really good question. So there, if things are tagged the same, you can search that. With the search that I have, it is VM25, so you basically get a sort of score, and at some point you can add like vector search and semantic similarity search. But all of these things, they're all sort of modeled as generic data assets within sort of subcategories based on the actual source. And so there, all of that metadata, you can model it, you can connect it.
Yeah, that's a very fun one. Just thinking about, like I'm sure you've seen how popular it's getting. What is it? Now I'm blanking on it, but like LLM wiki stuff and their Obsidian, all of that, and how it's kind of in that same vein, but not quite.
And I now have all the data and metadata needed to put that together. This background photo here, which is a Weddell seal, by the way, I took this in Antarctica, and it's got the metadata, location, and time, and can probably put that together with the emails that I have about scheduling that trip, who I did it with. So we could put that all together into a nice knowledge graph.
Wow. All right, last one for you. Could you implement, or could this implementation replace the defunct personal desktop Google engine?
Ooh, so short answer is kind of. You could definitely use this. Like the whole point of this is that it is personal search for all the things, all the data that I have. There's no reason why I can't put other external data in this and do like federated search or bring other data in as assets. So you definitely could do that.
Cool. Will, man, thank you for this. We're going to keep it moving. It's been awesome having you on here, and I really appreciate you giving us a little peek into your personal data lakehouse.
Cool. Well, rock on.
See ya. So now, as I bring the next batch of folks onto the stage, and that's right, I did say batch because we have a panel coming up. I'm going to bring Vinod back to the stage. He gave the keynote earlier, and he's going to be leading this panel. I've also got David coming. I've got Alex and Melda. Hey, everybody. While you're all joining and getting situated, getting comfortable, I'm going to launch a poll for the chat to see what they think their current data platform challenges are and what their biggest challenge with their current data platform is. You can answer that in the poll, and I'll leave it open for this whole panel session. But for now, I'm going to hand it over to you all.
All right. Thanks, Demetrios. And it's good to be back, I think, and to pick up from where we left off. If you attended the morning keynote, there's a lot of talk about context, and we briefly touched upon context engineering and context infrastructure and all of these emerging terms and technologies and kind of like practices, right? So this is where we go deeper on this. I have an amazing panel with me, right? So I'll be brief in my intro. Founders here at OneHouse, been working with data engineers for over a decade, and also been part of data infrastructure teams at places like Uber and LinkedIn before. I'm very, very excited today to welcome our panel, who are all ML AI practitioners and I love to actually go deeper with them on this topic of context engineering and what does it really mean. So yeah, without further ado, let's maybe do like a quick round of intros for our panelists, starting with maybe David. Can you kick us off?
Hi everyone, I'm Dave Ronchek. I'm co-founder of Kubeflow, and I did work on Microsoft's open source machine learning strategy for several years. I now lead a company called Expanso, where we do distributed data pipelines, both ingesting and adding context from your data, no matter where you get it from, and then also running ML at the edge.
All right, amazing. Alex, do you want to go next?
Hey, I'm Alex. I'm the tech lead of the machine learning platform at Monzo. I've been at Monzo now for just over 2 years. And yeah, we work on everything from the whole like traditional ML to AI and kind of the whole end-to-end basically. And it's been a fun ride so far.
All right, amazing. Melda, do you want to introduce yourself as well?
Yeah, sure. So I'm Melda. I'm part of the Uber AI team. Been at Uber for 4.5 years, so a bit more than Alex has been at Monzo. Doing kind of everything from kind of our DevX reliability work to we're doing some cool stuff in the open source, which we'll share more about later in the year. And also a lot of kind of the EU AI Act compliance stuff, both for core machine learning and AI, which has been an adventure. All right, over to you.
All right, amazing. So, all right, so we have actually relatively a short amount of time for the mountain of depth that we need to cover here. But here is how we'll frame this, right? So OpenXdata, unsurprisingly, is attended by a lot of data engineers and people who are data practitioners building data platforms, right? So I'm going to basically play that role. I mean, channel that voice, and I'm trying to kind of for our audience, trying to unpack what is really going on and what is context engineering, data engineering, and kind of like hopefully the goal is to leave with some good understanding of all of these, and also potentially like some areas for data engineers to focus on as the world, the AI revolution unfolds, if you will, right? So awesome. So let's kick off. Alex, I want to like start with you. We have ML systems for over a decade, right? I mean, it's not the first time we build machine learning systems. So what really changes LLMs? Is it just better models, or did something shift fundamentally now this time?
Well, I guess from like a data engineering point of view, and interfacing with the kind of ML folk who are kind of doing the modeling, like almost all of the time was just spent in sort of creation of data sets, of building out training pipelines, and then like an awful lot of time was just spent on like kind of the evaluation of those models that you were kind of training. And that was all around like feature engineering, and it was all around making sure that you create these large data sets and making sure you have these nice clean labels and stitching all that stuff together to then train these models. And that whole part has just been completely replaced. So you no longer, well, I mean, especially if you're using providers, that whole chunk of where a lot of that kind of time and effort was actually spent has now just kind of disappeared into just an API call. But I want to kind of suffix that with like, and maybe we'll get onto this a bit later, but like the same paradigms that you have in machine learning to determine like, I've made a change, how much has this affected the output, is still relevant, very much relevant. So it's like similar skill sets, but it's just that the where you place your time has changed quite a lot when you're trying to productionize these systems.
Right. Interesting. From that, I want to go to you, Melda. Like, do you see this as a new stack, or it's a natural evolution of capabilities? What's like, in your opinion, fundamentally different?
That's a great question. So Uber, we actually have our own machine learning platform that we've been building for the past 10 years. So it's quite timely and I think appropriate that. So we've had a lot of the core or what like classical machine learning components, which are like, ML specific. And then there's more just simply platform components like pipelines, stores, APIs. Those parts and kind of the control plane, a lot of that is very extensible. So I mean, the specific machine learning model, how you do your data engineering. I think there's a lot now. We're going to talk about context engineering, so on and so forth. Those are kind of ML flavor specific. We use that terminology to determine, to distinguish between classic machine learning and kind of Gen AI, agentic AI. But a lot of the fundamentals are completely reusable. Like especially when it comes to compute resources, like managing CPU, GPU clusters, Spark, Cray, like all of that a lot of it is quite similar. So that's been kind of, great for our team. But then there is, of course, additional work that you have to do to make things work in the Gen AI world, which is just completely net new, both from kind of the data engineering perspective, but I'd say a lot more also from like the serving perspective, and kind of those two getting a bit more mixed than they ever did before.
Got it. So there's a good amount of like orchestration and like platform, like those parts you could reuse, while you need to pay attention to things that are fundamentally different about the models that we're dealing with, which are LLMs, right?
Yeah.
So I'm curious, is this the Michelangelo system that you were referring to?
Yes, it is Michelangelo, and that is the platform that we are starting to open source. And kind of a lot of what we actually just discussed is guiding our decisions on what should or should not be open sourced, right? It's like these reusable components. A lot of just taking a model to production, that challenge is a challenge everyone is facing, whether you're doing core machine learning or classic or kind of Gen AI or agentic AI. So those components are kind of leading our charge to open source. But yeah, it is Michelangelo, and there's a lot of companion blogs that explain what it is. Yeah.
Yeah, I asked because I'm ex-Uber alumni and I was there when we started it way back. It's great to see that progress. David, moving over to you. You deal with a lot of these like workloads in the flesh, right? So what is the hard part? Did the hard part previously used to be that you need to train a model, people spend a lot of time like fine-tuning the coefficients and things like that. Now with pretty much the large the LLMs and foundation models, did the hard part move from training models to just the getting feeding it with the right context, or what do you see the challenge shifting?
Yeah, I mean, I think that both Maida, sorry, and Alex, I hope I got that right, touch on really important elements, right? Like, make no mistake that the quality of the models has significantly improved, very significantly. But I remember in 2018 there were models that could beat I think every like Atari game, right? On its own. You could train it to figure out how to like learn new strategies and things like that all on its own. And AlphaGo was 2017. I mean, these are like groundbreaking, revolutionary models back then. That's not to say there haven't been advancements, but I would argue that a lot of the advancements are around the UI, right? And the actual interface, right? We're so far abstracted from understanding how to fine tune and what your final layer is and one hot encoding and yada, yada, yada. Like, nobody has to think about that in order to get good answers. Now, directly answering your question, I would say one of the biggest failures today is assuming you can ask a model something, which again are borderline, superhuman in their capabilities. You can ask a model anything, and it will have any kind of context around what you're asking it. One of the biggest challenges that we do in our data pipeline world, and I don't want to talk my book, but is just show people, hey, you know what, you put all this data into this warehouse. The model has access to that warehouse, but you in your head maintain this context, organizational context, business context, whatever, time, oh, you know what, no one would ever go shopping on Sunday in whatever France. I have no idea, right? Like, that's a context you have that the model just does not have awareness of for what you're asking it. And so you give it this question and it comes back with a generic answer or whatever. And so that, I think, is missing as much as anything. And we just help, we help people all the time just say like, hey, you're already moving this data here, just wrap it with a little bit more information and you're going to get better answers.
Got it. So that's interesting, and I think it's at the crux of the context engineering topic, right? So we know what data engineering is, right? We build the first part of what you said. We build pipelines. We've been like building pipelines and tables, and put it in front of analysts and data scientists for various reasons for a while, right? So, and when you say like when you're helping companies become AI ready, what is that extra bit of information that you actually add? Can you like make it super concrete for a like a data engineer to understand that here is how I ingest the data? Is it like extra information that I ingest? Is it a better catalog? Is it like better documentation that you semantically parse and associate with? Like what is it? What's this context?
Sorry, was that question to me, or I'm happy to?
Yeah. To you.
Yeah, it's incredibly boring, everyone. I'm really sorry. Like the most common thing. So I always give this example, and it's totally true, and it basically mimics. Actually, I'll give you a real world example, but with the names left off. We do a bunch of work for example, energy companies. Energy companies have giant wind turbines and on-site solar deployments, or wind turbines, or whatever. They have these wind turbines take months to go and install and ship over from wherever their original location is. The firmware in those wind turbines is often different. It's often specific to the wind turbine. And they might have different teams and things working on those various things. And so a lot of times you will get a situation where like they'll change the order of fields based on the firmware version, and the firmware isn't shared between each of them. And so like one looks like it's dying and the other one doesn't. And that's just pure schema and data cleanliness, right? That's like the most boring thing in the world. But you can't possibly ask an AI to figure it out when you as a human can't figure it out, right? And to give you even further context, so that's just cleanliness, and that's something we do help with a lot. But again, you can write this yourself. We just happen to write a platform that helps you do that. But it makes your models perform much, much better. But here's the second one, and even more subtle that I didn't even aware. So imagine you have a field of wind turbines. All the wind turbines, one wind turbine is working and it's working at whatever, 80 kilowatts per hour or whatever it is, right? Then the wind starts to pick up, so they decide to turn on other wind turbines. Well, it turns out that their first wind turbine actually will go down in production. It'll go from 80 to whatever, 60, because the nature of wind is such that you can't infinitely consume all the wind. You can only consume as much as necessary to push the blade through, but then it has to go through. So they have to balance all these simultaneously. So now, even though the wind has picked up, because you turned on these other turbines, the first one goes down. Now, if you're operating with no context whatsoever, a human being or an AI are both going to say, well, shit, this one is now performing worse, even though the wind is higher, we better go repair it, right? Because they don't have context. And that's such a fundamental thing that's missing. So, while we absolutely do like full ML and do RAG and do all sorts of like fancy things, the first thing that we usually implement with folks is just like, hey, what are you doing as far left as you can with your data to wrap it, to provide governance, to provide metadata, to do schema enforcement, to merge it together and land it in the right place with all the information that it had when it left.
Got it. That's pretty interesting, and thanks for taking us through like a concrete example of what that context could mean and what could be lost without that, right? Milda, could you maybe like you must have a lot of these challenges at like very large scale, right, within Uber yourself, right? So how do you guys manage context, or like how do you collect it? How do you curate it? How do you know, for example, the right things are captured from the right people in the business and can be fed to the AI system, right? So can you help us unpack the hard parts of doing this in real life?
Yeah, no, that's a great question. I think I just want to spend a second to explain maybe fundamentals between data engineering and context engineering, and like that will lead to the core challenges. So with data engineering, like I used to do a lot of machine learning before. You can really look at your data and know how good it is to an extent, right? We have like, it's a tried and tested field. You like clean up your nulls, you can like do some transformations, and you're like, okay, this is now healthy. It can get into a model, like I'll split, train test, run it, like do whatever evaluation you want to do. And it is somewhat objective. Like that whole pattern is very difficult to replicate, or it's not really possible to even replicate in a kind of more Gen AI, agentic AI world. Everything, if you're not building a foundational model from scratch and you're not fine tuning a model and you're trying to figure out a way to use a model in some production system, kind of everything needs to go in that context window. And it's not just about stuffing all the relevant information. So from a data engineer perspective, first, what is the relevant information? Making sure it's readable by the system, which is different than how it could be readable by a human. Like just simply, I think we all get a bit lazy at, making sure our column names, our feature names are nice and readable. Like if everyone can create data set at Uber, and at some point it just becomes abbreviations. I have no idea what it means. I know I can ask that data set owner, hey, please go and like clarify it. I usually don't need to. AI will not know. It will make some assumption if it's retrieving that data on like what this feature is. So there are all these like fundamentals that we never got around to, that we just need to think, how in this very limited context window Do we, fit the prompt? Do we get the right context that's needed, be it more kind of text, semantic data versus whatever the data is, but making sure it's correct. Like, how do we know it's correct? And it's hard to know until you've actually run it. And then, I mean, if you're doing it right, you have invested time into like a labeled golden data set where you can say, okay, I'm using this AI model or this like production system for a very specific use case. Like, I think we need to clarify it, right? If you're not building a foundational model, you're telling this thing you need to do one thing and one thing only. So you have something that you can evaluate against. Doesn't look good? Okay. Is it a data problem? Is it a retrieval problem? Like, are we retrieving the right data? Is it a chunking problem, right? What if it's like massive legal documents and like things, the chunks don't, like the chunk that's retrieved doesn't actually have the exception to rule number, whatever. What if documents disagree? You have two legal documents published by one an EMEA legal team, the other a US legal team, and they just contradict each other, right? Like, that case doesn't happen in classical machine learning. Here, this Gen AI model, based on the prompt you gave it, is trying to figure out, how do I reconcile these two and put it together? So when it comes to like data engineering in the Gen AI world, it's really about thinking about how you can write instructions in human language for a machine that will be confidently wrong if it is wrong, or confidently right. So it's just this whole setup is different. But just to wrap up here, a lot of the fundamentals of like data quality, all of that is the same, but just figuring out, how do you apply it to a world where it is a machine that is acting with extremely basic instructions, not like a human who looks at obvious things and will know this is the right data set, this is the right wrong data set, so on and so forth. So, I mean, just to wrap up for the answer at Uber, you have to invest in each production data set, figure out what is essential for that use case, make sure it had access to that knowledge. So again, not sexy work, but it does have to, you do have to do it.
Got it. Got
Yeah.
it. And the upside of the sexy work is that there's an AI agent that can probably make us a lot more efficient. So okay, all right. I like grounded answers. So it's super awesome. Alex, I want to shift to you a little bit, and Melda mentioned the all important context window, right? So maybe can you maybe just explain that a little bit from how you see from a data engineering versus context engineering angle? Do you feel so we used to just pre-compute data sets. From that, do you think the challenge is moved on to assembling the right data at query time, which means you need a lot more flexibility to assemble the context? Or can you talk about, maybe share with people what that looks like? Let's say I have a query, natural language query to an LLM, and then you want to assemble context to answer that query at runtime. What is involved in that process, do you think, that is different from regular database queries?
Yeah, I think it's a great question. And I'm going to go on to the similar theme, right? And I guess this is the whole point of this panel, which is typically we reach for the same tools that we're reaching for the sort of like traditional ML use cases, right? So like context and features are like somewhat quite similar context, like concepts, right? So, a model, when you're making a prediction, you're going to have some inputs to it. And those inputs, okay, it comes in a different form, but they're typically like aggregations over something, or maybe it's like the top K of something or the last X of something else. And typically it's like, these are the inputs and I want to then pass that in and put it into the right place at the right time. The place changes, right? Where like within model, when you're doing like traditional ML, it's like, these are the inputs to the models, where within context engineering, it's like within the prompt. So you're just going to like, structure these into the string prompt. But fundamentally, you're still having to do the same thing. So maybe if you're trying to say like, okay, yeah, what are the last X transactions you've done to a particular merchant in like Monzo's case? Well, that requires us to still be processing events off of Kafka. It still requires us to be doing aggregations on those events. It still requires us to be doing that efficiently, using the sort of like with low latency and all the kind of good stuff we normally expect. And then also, like when evaluating these systems, again, going back to the same idea that actually we can reuse a lot of the same tool sets, like creating like if you have to assemble context in real time, well, in order to evaluate how well your model would have behaved at a particular point in time in the past, so you can try and understand, like, if I make change X, then this is how my model would have performed, or my system would have performed with the context it had at that moment in time. Well, we have to do that same problem when we're training like ML models, right? Which is, we have to take the historic data we have to create the context, or in ML case, the features with the correct point in time, so you can kind of replay those back through your agents to say, and then sort of take away some of the non-determinism that you have in this sort of in using these providers or Gen AI models, and try and kind of like harness some of that into using your historical data to push through some of those pain points.
Got it. Quick follow up. Do you think the non-deterministic kind of nature of what an LLM might do would increase the need for an underlying data platform or a Kafka or something to be a lot more flexible in terms of these context queries that it may receive at runtime, or
Yeah, and I
compared to a
think
traditional model?
in a way, but like so within Monzo, we've put a bunch of investment into this tool set that we call the feature transformation framework. But basically, it's the open source framework called Chronon, and that's actually quite and we have that kind of like put through our system. So in terms of the tool sets we use, it's pretty easy to describe quite complex aggregations of inputs and outputs to models, and then also have those backfilled, so you can kind of back test your changes against historical data. So again, coming back to the point of like, does the tool sets fundamentally change? I think probably not from our point of view with us at Monzo. Like the things that actually fundamentally are changing is more around like less on the data engineering side and more around like, okay, we have this external provider that we're going to be like pushing data to, and it's they're unreliable, or we want to have failovers to different models, and we want that to be transparent to our users. But from a data point of view and evaluation, like offline, the tool sets are very, very similar.
Got it. Awesome. So, David, circling back to you a little bit, just to have this some closure to this part. If I'm a strong data engineer today, and then I'm tasked with, hey, the data that you're building, the pipelines that you're building are going to feed AI agents and feed to be potentially used as context for AI agents. What's one or two things that I should be learning in the next few months to be effective in this world? Like my consumer is no longer a human being. Like, I mean, it's a human, but it's also like I'm building data for queries that are automatically generated from LLM. So what should I upskill myself?
I mean, again, I'm just going to steal from smarter people on the panel than me. It's going to be the same old like initial data engineering stuff. The cleaner you can get your data, again, just in the same way you would appreciate clean data, your model will as well. Having the right context, having the right provenance and lineage, making sure you know where the data came from. Even after it gets tossed into the term I've been using is data goulash, because it is totally non-introspectable once it's in there and it's been trained on, is critical. But also, like, a lot of these things are the same old tools. Use the things that are battle tested, because there's so much history and lineage around them that like there's nothing preventing that. What I will say, as an extension to everything that you heard earlier, is these things are AI agents. Even if you wrap them with a rich memory system, at least the first query, if not more, are going to be stateless, right? So the more that you can put in there, you want to put exactly as much as it needs to answer the question and not more, because you'll blow out your context window. So like, how you walk that fine line is up to you and your business. Think about that. Think about all the things that it needs to have access to in order to make these good decisions, and make sure you make it available. But also think really, really hard about what you're losing as data flows through your system, right? So if you have a point of sale system in some location, or you have a user that interacted with a website in some location. You pass it through. As it goes from there to your, Google Analytics, to your, user reference data endpoint, which you then resolve into a, user ID and so on and so forth. And now at the end, they're trying to make a decision on this user, but they didn't realize that this user was accessing from, I don't know, Bangladesh. Like, that data is going to be lost along the way. So the more that you can ensure that data is encapsulated and carried along so that you can make a decision at the end, I think that's just incredibly important. And those are the kind of decisions that once they're, if you don't start doing it now, it's lost forever. You will never be able to go back and get it. Sorry, go ahead.
Got it. Awesome. That's actually very, very actionable. And I know we're like running super low on time. Maybe Demetrius, we'll have a couple of minutes for Melda and Alex to share some closing thoughts.
For you guys, anything.
All right. I'd love to hear any problems that you guys feel like, oh, these are interesting problems I think will be solved in the next few years. Anything worth highlighting, that'll be awesome to hear. Melda, do you want to go first?
I feel like you need to think about that for a second, but I'll think while I talk and say that I think that the data engineers are uniquely positioned compared to a lot of other folks in the ML ops world. Like AI has been so democratized that you're just like, everyone's vibe coding these days and doing whatever. I think data engineers have this rigor, know how to think about data quality, data lineage, things like that. And those are real issues in kind of Gen AI and production. So bring that mindset into these spaces and like voice your opinions to solve the hard problems that need to be solved.
Right, Alex.
Nice. Yeah, I'll keep mine short. But I think it's all around this idea that the sort of promise is that you have all of these, you can use Gen AI and you have agents and there's this idea of context. But I still think, like, especially like people I've been speaking to and what we have in Monzo, there's still this idea of like, there's just not enough context available and not enough like things for these agents to be able to do. And there's still just a lot of just work to get to that point where we can like let these things kind of, well, maybe roam free is a little sort of over the top, but I still think there's a gap there. And so it's, yes, the models will keep getting better, but I still think that, like, companies have just got a long way to go until they've reached that kind of utopia of just all context and all actions available all the time.
Yeah, context is the bottleneck. All right. Back to you, D.
Well, thank you all. This was very insightful, and I love every minute of it. I also want to call out David. I think you're blurring your background, but there might be some instruments back there, huh? If I see correctly.
No, the exact reverse. It's like a podcasting thing. I do a lot of live what do you call it? So could not be less cool. There you go. Right?
Oh no! You should have just kept it blurred. And kept
I play guitar, but it's in another room, and I'm terrible. So that I'm glad I didn't show because
all right, get off the stage then. We'll see you later. This was awesome, folks. Thank you all. Alex, Vinod, and Melda, thanks for this. I'm going to keep us moving because I have to be the Ringo Starr of the day and keep time. While we are keeping time, and I'm bringing our next member to the stage. Where's Will? There he is. I'm going to remind you all, we've got a poll going right now, and there are how many folks right now on this call? There's over 400, there's over 350 folks on the call right now, and we got 44 votes. People, it takes one click. What's your data platform challenge? What's the biggest challenge? Go ahead and drop it in there so we can see what it is. Will, how you doing while we're waiting for people to vote?
Great. It's a sunny day in New York. Excited to talk about some data.
Those two things, yes, of course, they go perfectly together. That is right. Sunny days inspire you to talk about data. Let's do it. I'm going to keep this poll open for another few minutes and let people drop it in. Will, I'll hand it over to you in the meantime, and we will be seeing you. Hold on. Why are you all small? Let me change this view. There you are. Now
Hello.
No, we're
I was
equal.
sharing my screen backstage. I don't know if there's a way to move that or if to.
Hold
This
on,
is a
hold on.
classic
Is
AV
it this
problem.
one? Is it this one? Let me move
Aha!
it to the stage. There we go. I have the power to do that kind of stuff.
Cool. Magical. All
All
right.
right.
Well, thanks for having me. I guess I'll get started. So, hi, I'm Will. I, amongst other things, I started a company called Spiral, but today we're talking about actually open source project called Vortex, which I'm also the sort of TSC or PMC chair of. So I'm going to talk about building GPU native columnar storage. A little bit about me. Well, I've dabbled in lots of stuff. I guess kind of like what you would call AI research really long ago. I was a derivatives quant. The big thing is actually this is not my first exabyte scale data system. I sort of helped create Foundry and scale it at Palantir, and that was sort of like did basically everything that read or wrote bytes while I was there. I like to back up a little bit, which is like, let's start at the bare metal, because I think everything in data systems is actually a bit downstream of hardware. So if you go to sort of, the early 2010s or even go further back, like 2000s, it's like individual CPU cores stopped getting faster. And so Moore's law sort of happened by scaling out lots of CPUs. And the 2010s were all about like have this big homogeneous pool of CPUs and RAM and, oftentimes spinning hard drive disks, and you network them together. And there was a speed hierarchy of like RAM is always faster than disk, which is faster than network. I think, the stuff that's happening now is like a lot of those assumptions are sort of no longer valid because of shifts in the hardware. Like the most obvious thing is AI workloads have really driven the explosion of accelerators, especially like GPUs and sort of GPU compute, I think is here to stay. Just as a percentage of wafers of silicon being produced, it's going to keep going up. And then I think that speed hierarchy still holds for latency, but there are sort of different things where network cards now have more bandwidth than the PCIe bus. So like you can actually copy more data over a network card to a GPU than you can from RAM on the same machine or from NVMe, like local disk on the same machine. And then I think storage has really bifurcated. Spinning disks are no longer really directly used in the same way, except as a backend for object storage. And then, there's sort of this remote infinite storage that usually looks like an object store. And then there's NVMe, which is local and extremely fast and is almost an extension of memory. I think of database systems like we had sort of the original human scale data in, human scale data out. That was from the pre-2006 era of Dennard scaling when CPU cores just got faster, but there was only one of them on a machine. It's like Postgres is archetypal of this thing. And then there's sort of big data that was downstream of like, we're going to scale out CPUs. But that was all about aggregating. It was like, cool, a human is still going to consume it as a dashboard or a chart. So even the Lakehouse, it's like, cool, you collect enormous amounts of data and then produce something very small for a human to look at. And I think we're now in this like sort of data systems have to deal with machine consumers. So enormous outputs, whether it's a single output set or huge QPS. Like I even think of GitHub falling over as like, well, it turns out that when you have these sort of autonomous agents running workloads against a data system, like it scales and breaks in like sort of new and interesting ways. And then obviously there's like this heterogeneous hardware, so stuff like training. I think the other thing, just to contextualize, there's been a big move towards composability. So Apache Arrow gave a framework for sharing in memory across frameworks and across languages, and also for inter-process communication. The Arrow file format is effectively uncompressed, so it's not ideal for at least certainly all storage use cases. Like you can use it sometimes, but it's not ideal. And then there was a big move towards table formats, Iceberg, Hoodie, Delta being the most prominent, but there are also others, and Parquet, because I think as a complement to the in-memory sharing that Arrow gave you, you had sort of like, I can share files in S3, and that's effectively, it's a near infinite bandwidth way to share between systems. Like these are two different ways of sharing data between systems. And they're quite complementary. And Iceberg and other table formats sort of wrap up the metadata around files, like usually Parquet, so they could be a table. But file formats like Parquet define how the bytes are actually stored. I usually think like looking at all these shifts in hardware, it's like, is Parquet good enough? And this is a debate I have quite often with different people, and reasonable people disagree. But I think, the things about it are it's widely supported, it's mature, it has good community governance. And as Julien Ledem likes to say, that Parquet is the consensus mechanism more than it is the technical implementation. As Hannes Melissen says, the format is great. Of course, Hannes is comparing it to CSV. I think the problem is it's borderline impossible to evolve. Like if you look at the default Iceberg writers now in Spark in the year of our Lord 2026, they're still writing Parquet v1. Like the Parquet v2 feature set of like optional extensions is like basically 10 years old and still not the default. Adding variant has been Herculean. It's optimized for sequential access. Like it was quite reasonable, again, for building in HDFS against like local hard disks, but it's not great for object storage. Like especially the metadata is sort of not ideal when you have to do multiple like long network requests to get parts of a file. And then the heavyweight block compression is CPU hungry and it's slow. For context, why do I care about this? I put myself in building a data system for machine consumers. And so especially for GPUs, I think about like a lot of what I think about is GPU data loading and sort of data warehousing and like, optimizing for throughput. Analytics, lookups, but like, again, especially like some of these like GPU native workloads are pretty weird. But as I said, sharing files in S3 is an infinite bandwidth way to share between systems. I think in general, if you want to maximize throughput, the most practical way is to stream bytes straight from object storage over the network, because as I said, the network cards have more bandwidth than any of the local resources on like a lot of modern servers. And then, Parquet, for better or for worse, is like the prevailing standard that defines how bytes are stored. And so if you're sending it straight over the network, especially straight from storage, you're going to get bytes defined by the file format. This is why we created Vortex. It's next-gen, composable, free and open source forever. It's Apache 2 licensed, but more importantly, we donated it to the Linux Foundation, so it has sort of neutral, multi-party governance. We can't rug pull the license. I like this quote from Wes McKinney, who's actually a member of the sort of project management committee, which is, we tried to take the cutting edge in research combine it with industrial scale engineering, and then like actually for this sort of composable data systems era, it's like, can we make something that sort of actually like is composable data systems, like Arrow native for this like next gen of computing. And in general, the thesis of the project was technically advanced organizations just keep building Parquet alternatives because Parquet is too slow, and bleeding edge open source projects don't use Parquet by default because it's too slow. So could we obviate the need for all these proprietary file formats with an open source alternative? Vortex basically extensible and future proof, special emphasis on sort of the GPU computing, and we'll talk about why that's important, but also just in general, like how do we avoid calcification? So as much as we can, sharing an implementation rather than having a huge, and language bindings rather than having many other ones. What in Pareto optimal performance? So there's a thing here, which is like, what is the most extreme performance upside that we can get? Because file formats actually tend to be quite high inertia and last for a long time. And so we wanted to push that early. So I think, scanning decompression on a CPU, it can be 15 to 20x faster. On a GPU, up to 100 times faster. Like talking terabytes per second of decompression throughput. And then can you do fast random access while preserving compression? So like, can you be comparable size? And then again, can we get faster write throughput, especially on a CPU? And then finally, maximally error native interoperability. Design goal, actually the biggest thing was moving stuff from the spec writer to the file writer. So it allows for more evolution over time, optimizing the metadata. And then the thing we're really talking about today is, I think one of our key insights in the project was if you design for GPUs, like SIMT programming, actually has the tightest constraints. Like if you design for SIMT programming, you can't have data dependencies. And you also need to know the output size. If you don't have data dependencies, it's a lot easier to do vectorization, so SIMD. And then also to support random access, as in like maybe decompress just a single value, or don't have to decompress like large blocks, megabytes of data to get a single value. And so we pair that with cascaded lightweight encodings to get a good compression ratio. So, we pulled lots of the state-of-the-art research. It's also one of the things I'm really proud of is Vortex is starting to be used in more research, including the best paper last year. And then I think it sits at this interesting space in the ecosystem where it's sort of like cutting edge industrial strength and has sort of proper open source foundation, big foundation governance. It's like the intersection of all these. Going back to, sort of what we ended up with, if you look at Vortex, the file format, it's actually designed to be extremely extensible. We're not going to go into the per byte layout of the file format today. We don't have time. But, encodings, the compressor, which is sort of the encoding selection strategy, expressions on encodings, the data types, the layouts. So literally, do you have row groups? Do you have packs? Do you have all column written one at a time? Like how those are, the sort of byte buffers are laid out in the file are all extension points. And the files themselves are self-describing, which moves decisions about if you want row groups or not, for example, from the spec writer to the file writer. And then, having a shared implementation from an engineering point of view purely means that you can ship features to all the languages and all the frameworks simultaneously and immediately, instead of having to implement it once in one and then go through the long exercise of implementing it in all the others. So a way to think about it is that Vortex is in some ways like an LLVM for file formats. It provides an IR, has extreme extensibility with batteries included defaults. In this sense, I think we took a lot of inspiration from Apache Data Fusion. And then there's an aggressive move towards sort of the spec is so flexible to give us sort of future proofing for new workloads in the future. The other big thing, like I mentioned a minute ago, is this processor portable performance. So no data dependencies gives us all of these things. It gives us fast random access, SIMD friendly, so on vectorization on a CPU, and SIMT friendly on a GPU. And then the trick after that is, can you still get the file size to be small? Can you get good compression while sort of like preserving that, which means actually applying all those constraints and not relaxing those constraints? And so the cascaded lightweight encodings, a lot of that has been pulled from, as I said, sort of state-of-the-art research, plus some research that we've done ourselves. And then, the key idea was that designing for the tightest constraint, which is GPUs, gave us all the other ones essentially for free. The other thing is, in Vortex, like another way to think about Vortex actually is, because the file format, there's real work there, but it's so extensible and so meant to be so flexible and so future-proof that actually, if you look at the code by like lines of code, the majority of the Vortex library is actually an extensible state-of-the-art compressor for arrow data, and also a framework for late materialization, which is another way of saying sort of compute on compressed data. My example for late materialization, and this here is what I call sort of expression pushdown, is if I've compressed a column and say I know that that column is constant, it's the constant value like 42, and then I want the sum of that column, I can just turn that into multiplication. And so there's lots of stuff you can do actually taking advantage of these lightweight encodings. It opens up a huge number of optimizations. So the Vortex library actually tries to ship as many of those optimizations as possible and across different notions of compute. So, we can actually ship backends for a bunch of these across, for example, NVIDIA GPUs, like a CUDA implementation, as well as sort of vectorized ones for CPUs and like future backends. And so you can actually hook this into a query engine and get support across different sort of, it's like native support for GPUs or whatever it may be. But more importantly, again, the file format, I actually think a lot of these optimizations are file format specific. They're not engine specific. And so at least the ones that are file format specific are worth implementing in the file format library once optimally, instead of implementing it n times in the engines. And so that lets us then add a new support in a new engine and get immediately phenomenal performance without too much work. Going back to sort of examples of extensibility, for those of you who follow the space, like TurboQuant made a big splash about a month ago. Crashed memory stocks briefly. We actually merged it as a Vortex extension about a week later. The cool thing about TurboQuant is actually it's a serialized scalar function for rotation, and then we have some stuff on the tensor data type, and then but it basically was a strategy rather than a full encoding. And so you can get, for things that support it, you can get state-of-the-art, near lossless quantized vector embeddings stored in stuff like iceberg tables with Vortex, and you don't need a vector database, you don't need another table format. That's actually, I think, a file format concern around how do you compress and push down data on things like embeddings. Places where Vortex is out in the wild, there's a bunch of ongoing work. I gave a talk at Iceberg Summit a couple weeks ago around there's a proposal to add Vortex to Iceberg. I'm very hopeful that happens because I think it would actually be good for the ecosystem and the project. As I said, it was used in the AnyBlocks paper, which won best paper at BLDB last year. Turns out, I summarize this paper as the best way to make Parquet fast is to embed a WASM build of Vortex in Parquet. And if you do that, then all of a sudden Parquet is fast. This was pretty cool, like Liquid Cache by Shangpeng Hao over at Wisconsin. He found actually that having it cached in memory would still sometimes be slower than just reading Vortex from disk or from S3, which is kind of crazy. There's some recent work on Iceberg indexes related to the Iceberg work. It turns out if you have Vortex and you want to filter to primary key indexes, this is an example of a very selective sort of SQL query. Doing it in Parquet for one key was 116 milliseconds. Vortex was about 1 millisecond. For 90 keys, Parquet was 135 and Vortex was 6. This was someone else ran this and just posted it in our channel a week or two ago. For stuff like data loading, we plugged it into Mosaic data streaming, which has its own custom row-oriented format, and out of the box with no tuning, Vortex was about 2x faster in terms of GPU throughput. And this was months ago. Actually, I think it's probably better now that we have native GPU scans. Polar Signals is an observability startup. They forked Delta Lake and replaced the Parquet data files with Vortex and the JSON Delta log with Vortex, and it dropped query times by about 70%, which is pretty cool. Benchmarks we've done. So the GPU scans, like I said, if this is for mostly numeric data, but Parquet reading, this is actually in-memory Parquet on a GPU, in-memory Vortex on a GPU. Parquet would get 90 gigabytes a second on a B200, and Vortex gets 5.7 terabytes a second with kind of comparable, roughly 5x compression ratios. And so it's like quite a bit, something like 60x faster. For direct, this is a little more subtle. So this is reading from a single disk to GPU. So this is on a modern NVMe with 8 gigabytes a second of bandwidth. And so the compression ratio for both Parquet and Vortex was about 4x. And scanning it from the NVMe onto an H100, we're measuring throughput of uncompressed data on the GPU, and Vortex got basically 32 gigabytes a second, which was, we fully saturated the disk. And you just cannot do better than this from a compression ratio point of view. For random access, I think in general, this one's a little out of date. Vortex and Lance are probably like roughly in the space the fastest for random access. They tend to be pretty comparable, which is to say hundreds of times faster than Parquet. For compression, writes are about 2.5 times faster. Scans, that's full decompression on our benchmark set, is 18 times faster. And it's about the same size. So sometimes it's half the size of Parquet, sometimes it's 50% larger. It's data dependent. I think on average, it's maybe 10% larger. For analytics, this is my favorite. So it turns out that the fastest file format for running ClickBench with DuckDB is not DuckDB native. It is Vortex, which is kind of fun by like a pretty wide margin. For normal sort of analytics queries against various backends, Vortex generally wins across query engines. Same against local NVMe. this is from my Iceberg talk a couple weeks ago. So plugging Vortex into a Spark Iceberg Vortex workload reduced query time pretty significantly. So dropped. I mean, Spark is harder from a percentage sense to optimize because it has so much overhead. Again, for selective filters, you see like we end up to being somewhere between 2 and often 4, sometimes much more faster. So the more selective the filter is, the faster Vortex is as a multiple of the Parquet performance. And this is my short summary. It's like basically, if anyone doesn't remember, this was before Kanye was canceled, but from his 2005 Grammy speech, like my general summary of performances for Vortex, like it's Pareto optimal. So we kind of cover all the bases. You want to learn more? This is a quick overview. I gave a long talk to CMUDB back in the fall that's up to date enough. It's an hour long, and I go into like really, really in the weeds on like byte by byte the file format and encodings. And in general, if you're interested in the space, love to collaborate both in research and in open source. Whether it's already used in a bunch of open source projects like Milvus, Paymon, as I mentioned, trying to get into Iceberg, and then doing a lot of work with researchers. It's in DuckDB, we test for data fusion, but it's like in general, how do we build on this and collaborate on making it better? Cool. Q&A.
All right. So while people are getting their questions out and ready, I think now would be a good time to revisit this poll and see where we're at. And also, by the way, on that talk, dude, I'm just blown away by how fast those benchmarks are and everything that you showed. Good Lord.
Yeah, I'm very proud of the benchmarks, but it's also, we spent like 3 years really, really, really deep on this one thing.
Yeah.
Just like how do you design the optimal file format, columnar file format?
Yeah. What was the impotence for this? What was like the pain that you were like, oh my God, I can't live with this anymore. I need to go and spend 3 years of my life dedicated to making a file format?
It was in general. I mean, I actually rolled Parquet out at Palantir in 2014, and had spent enough years building lakehouse shaped systems to get the sense that like it was a problem that everyone was avoiding, but it was holding back the types of data systems that you could build. And then especially over the last few years, it just became clear to me that like the types of data systems that need to be built are very different than the ones we built before. Yeah. And so you have to change the constraint.
Yeah.
So what's the drawback?
Yeah, that's the question. It was all freaking rainbows and roses in your talk, but I'm sure there's something.
I'd say the main drawbacks are like breadth. The biggest one is breadth of support. It's like cool. We have bindings in Python and in C++ and in Java and obviously in Rust and a handful of other sort of languages and frameworks. Parquet and others, existing things just have been around longer and have like ambient, deep support everywhere. So your framework may not support it yet. I'd say the other one is the Rust project. If you use it, is like the file format is quite stable. It has extremely good back compat and extremely good performance. The API like breaks all the time if you link against the sort of Rust library directly. But I think those are mostly project maturity things that should get better and better over time. It just takes time.
Yeah. Well, shoot, man, I just looked at the time. I gotta get you off of this stage and keep us. I'm already over, and I had one job. That was it. Will, thank you. We're going to push you out now and move on to our next speaker. Mr. Tosh is going to be moved to the stage. Where is he at? There he is.
Hello.
How you doing, man?
Doing good. How are you?
I'm great. I'm excited for your talk. Welcome to the stage. You have 20 minutes on the clock. Feel free to share your screen. No, sorry. Wait. Yeah, you have 20 minutes. All right.
I can share my screen.
I got scared real fast thinking that you only had 10 minutes and I just gave you over 20. And then I was going to fear that I made a mistake, but I didn't. All right. 20 minutes. I'll be back. I'll see you.
All right. Hey everyone. So before I start, I mean, it's a long title, right? What happens to your data architecture when a query layer starts making decisions? And I kind of want to be honest about why I'm framing it this way. My initial thoughts were, okay, let me call this talk something like building agentic analytics, or maybe like future of semantic layer. And then I decided to kind of scrap them both and go with this long title. Um, I think I want you to leave the room thinking, hey, it's not agents or it's not analytics per se, but rather it's this whole architectural shift that we're kind of having underneath. Um, you'll see this here stated as a subtitle, right? Which is the query layer used to be a function. It's becoming a policy. And I think that single sentence, I would say, is the whole talk. Everything I'm going to say is basically unpacking, what changes when that kind of becomes true. So let's kind of hold on to that subtitle. So let me pull up the slide. So the picture I want you to have in your head is what's on the left, right? There's a SQL query. And you have some data at some moment, and you kind of press go, and you get a number. We've done this same query, same data, same number, right? And this is like the most boring property of a database, right? It's so boring that maybe there's not even a name for it, right? But it turns out almost everything we've built on top of databases for the past 2 decades, right? Um, I would say even DBT or Iceberg or any of the audit systems, all of these things are basically, in a sense, silently kind of leaning on this whole property, right? And then shift to the right? You now have an agent. What's going on is natural language goes in, and a model is going to emit a tool call, and then we have a query that runs, and the result kind of comes back. Your model kind of thinks about it, and this emits another tool call. Eventually, you get a number, right? So if we run that loop maybe 10 times with the same input, you're not going to get the same SQL, right? Typically, you'll see, depending on the model and schema, maybe 2 to 7 different queries, right? And I think this is kind of fine if you happen to get the same number to different paths, but it's not fine if you get different numbers, right? Because actually, maybe the scary case is where you actually get the right number 9 times and the wrong number on the 10th, because by the 10th call, you actually were able to calibrate your trust on this thing, and you put this in production or evals, and you actually have the worst outcome, right? So let's kind of, we know this typical thing, right? Which is the result of any query at a time t is basically a function of query, a schema, a data, and your time, right? So that's our function. It's one number, 4 arguments in, one number out, and it's pretty deterministic, right? And the moment you kind of write it like this, you basically see it everywhere. Warehouses are gonna assume this. My lakehouse assumes this. DBT tests assume this. Even Iceberg snapshots or everything. Maybe your incident run book also kind of like assumes this. And every governance policy that we've ever shipped, all of these kind of implicitly, given some sort of an authorized caller, the answer is a function of these 4 things, right? It's not a feature, but it's you might call it as a load-bearing assumption underneath this whole stack, right? Or rather, the entire stack, right? So when this assumption kind of changes, when the answer actually becomes a sample instead of a function, then every layer above it gets a little wobbly, and most of those layers, they probably don't know that yet, right? So the picture on the picture here is DBT Labs benchmark from earlier this year, right? There were 11 questions, and they did 20 runs each, and there were frontier models, insurance data set, and there was one question, the same question, same data, and you get this whole fan out, right? The thing I want to point out, and it's kind of subtle, is this text to SQL. It doesn't fail the way we would kind of hope it would, right? Normally, I would kind of hope it would fail pretty loud, in a sense like, hey, your parser was blowing up, or there was a big red error, and yeah, I mean, those are the ways I would hope it would fail. But it actually fails as a long tail, right? So the average accuracy that you have on your leaderboard might look fine, or you can say it may look great as well, but the variance that you have across different runs, that's what is going to kill you in production, right? Because in production, the user does not see 10 runs. Maybe the user just sees one run, and they don't get to average over 20 or 10. So here's the thesis that I'm kind of like mentioning as flatly as I can. The query layer used to be a function, but it's becoming a policy, right? And the reason this matters is because every architectural assumption of downstream queries have been deterministic. And now we have to re-examine, right? Let's take governance or observability or cost attribution, testing, like all of it, right? So I think what's important is determinism actually breaks, right? And there's also, we may have to make some architectural decisions here. And hopefully not a lot of frameworks, and I'm not going to make any vendor pitch here, right? So, okay, first section. So where does determinism actually fail, right? I think the naive failure mode, where maybe everyone reaches for the first, is my LLM basically writes a batch SQL, right? And yeah, I mean that's I would still say that's a boring case, right? I can catch a batch SQL with a parser, or maybe I can have a query plan inspector uh, with my Cloud Code, right? And that's actually solved. That's maybe end of 2024, early 2025 problem, right? The interesting failure mode is the one I want you to take seriously, which is when an LLM actually writes a plausible SQL that kind of returns subtly different numbers across different runs, right? And this is a one where your current stack gives you basically zero signal on, right? And so let's take this question, right? Maybe we're trying to answer this question: what was Q1 revenue? It's one sentence. It's 6 words, right? Including the question mark, maybe. And the way I want you to think about this is look at how many decisions the agent has to make before it actually writes a single token of SQL, right? When you think about calendar, which calendar is it, right? Is it fiscal? Is it actual? Depending on region as well, right? And your finance team's fiscal Q1 might end, I don't know, end of Feb, and your product team's Q1 might end of March. And if you're now counting regions, different regions, your fiscal years end differently, right? So both of them real, both are in your system somewhere. And it depends on who's asking and for what purpose, right? Similarly, revenue, right? What do you mean by revenue, right? Is it booked? Is it billed, right? If you take a look at a SaaS company, right, these can differ by maybe 10 to 20% at the end of any quarter, right? So similarly, right, if you think about customers, right, is it paying customers at the end of the period or paying customers right now? I think you get the scene, right? So when you actually multiply this out, it's actually something like 128 interpretations to the minimum, right? And the way a senior analyst would handle is they would Slack a finance person, and the finance person has a sheet, and they're going to give you exactly how they computed it, and then you're going to use that to write a query, and that's how you get your answer. Pretty deterministic, right? Now the way an LLM handles it is you sample it from a distribution that's kind of conditions on whatever happens to be in that prompt at that moment, right? So that's exactly what's happening. It's actually a sample, right? So now, I mean, moving to the subtle part, right? I think the part of this room is going to recognize, with your own systems, if you go look, is, these are two SQL queries, right? Both of them are kind of like about Q1 revenue, and both run by an agent, right? And two different numbers, right? None of this actually shows up in your existing tooling or your query log, right? They're two valid SQLs, and they both parse, they both run. Your warehouse cost dashboard, they're two valid bills. Even if you think about your DBT tests, they all pass because both reference kind of like real columns and both kind of produce real numbers, right? So every signal in your stack is going to say everything's fine, and the only person who would have caught it is this analyst who you could have spoken to, or maybe a deterministic pipeline, right? And now that we're relying on agent, kind of like we've removed that sensor and the system is not able to call it, right? Now, this is what I kind of mean when I say governance, right? The way we've kind of practiced governance for the past 2 decades, it doesn't really account for something like this, right? Governance is a question about who can read what, or who can write what, or who can grant what, right? That's the, I mean, I can go on about the vocabulary, but agents basically makes access necessary, right? Kind of important, not sufficient, right? I think the new question we should be asking ourselves is interpretation, right? The two callers with identical access, and they're kind of producing different answers from similar data or identical data, right? So I think the access control just gives you no purchase on that, right? It's not the wrong tool. It's just a tool for a different problem that you have. And the three failure modes that I wanted to mention, and the reason I'm kind of being a little careful about this is, one is there's a generational drift, right? We just saw different prompt context, different sample, different SQL. That's very easy to think about, right? And then the second one is plan drift, right? It's much more subtle. The agent is not going to write a query. It writes a plan, multi-step, and on retry, maybe step 3 becomes a different operation than what step 3 was in first attempt, right? If you're logging at the query level, you won't see this, right? You see two queries. You don't see they belong to two different plans, right? And the last one is what I would call something like a silent contamination of context, right? And I think this is the worst one, because the model is going to pick a filter early in the session. It was wrong. And now every subsequent answer in the session basically carries that filter forward, right? So every answer is basically consistently wrong in the same way. From a user perspective, I think this can be indistinguishable from being right. So, and I might say that 0 of these are detectable by our current stack, right? And it's not a model quality problem, right? Models are going to get better. I think this is an architectural problem. Now, I think this is the part I think there's something to do where we can have maybe 3 decisions for each one. So decision, reasoning, and a pattern. I think we can make things that can work in production, right? So let's go to decision 1, right? Can we move the contract and not this warehouse, right? The default thing, the thing everyone reaches for first is you give the agent execute SQL, right? Describe schema or list tables. And then the agent goes and reads the schema, writes the query, and runs it, right? This is a text to SQL with extra step, right? I would suggest not doing this. Right? The pattern I see working is to make the contract between this whole probabilistic system and the deterministic system explicit, right? Which is mm, maybe this comes to how we think about agent's primary tool surface, right? So that's governed by a metric API and not a raw SQL. So once you have a model that picks a metric, the SQL is generated by a compiler, not a model, right? I think you have metric flow, you have Cortex Analyst, at scale. They're all converging on the same idea. And the way to think about this is, agent's choice space basically stops being something like, any SQL string the model can possibly emit to which metric, which dimensions, and which filters, right? I think the picking is probabilistic. That's fine. The SQL it produces is going to be deterministic in this case, and that's like the whole game, right? And for DBT benchmark, right? I think the questions that are going to basically fall on the model scope. I think text to SQL had that long tail, right? So now you can actually pose a very obvious objection. Is, hey, no, the semantic layer can only answer questions inside its scope, right? So what do you do for everything else? And the answer I see working is a tiered tool surface, right? Let's say we take a tier 1 where there's a semantic layer over MCP. So 3 tools, like maybe in this case we can list metric, describe a metric, query metric, right? And then the model is strongly steered to kind of prefer this. So this hits like about 85% kind of a regime in production. And for tier 2, there's a constrained SQL executor you can have in a read-only sandbox, right? And this can be against a subset of tables that are kind of curated. This is exactly the tables an analyst would actually use for this domain. So you have some bounded blast radius. And then coming to tier 3, you have the full warehouse. It's used very rarely. It's gated behind a human approval, and it's kind of like logged pretty loudly, right? The model sees all these 3, and the system prompt tells it, when to use each one of them. So now it's a routing problem, and the nice thing about routing problems is you can evaluate them. You can measure tier 1 hit rate. I think maybe there's some things there, like let's not expose query metric as a single tool. Let's not instead we can expose like maybe a list or describe and query as like 3 different tools, and basically put this whole metric definitions and any business meaning in like your plain English, because the model is going to retrieve on the description, right? Skimping on any kind of descriptions is like number one reason I've seen an agent kind of picking the wrong metric. And yeah, moving on to a second decision you can kind of make. So we want to make agent traces primary data and not telemetry. I think the natural instinct is when an agent is answering a question, it needs a bunch of context, schema, right, freshness, all of that. And the natural instinct is library. Even I've seen the libraries also push you toward is, let's kind of throw a vector store at your data dictionary, right? And kind of maybe back 6 months ago, you would rag all over it and you would call it a day, right? So a vector store does not kind of give you this unstructured retrieval. It also doesn't give you joins as well, right? And think about freshness. Do you get that with it, right? I think the thing that really matters is, so does it let you reconstruct even after the fact that the context that the agent saw at the moment, it made a decision, right? Because that reconstruction is basically a non-negotiable, right? So if you can't answer that, you can't debug, you can't audit, and you can't improve as well. So the pattern is a metadata lakehouse, right? You can have open table format, iceberg, or hoodie. It doesn't matter for the argument, right? 3 layers on the same storage. I think the governance layer, for example, and the question I always get is why a lakehouse and why not a graph database? Because this kind of looks graph shaped, right? And the answer is the shape of your workload as well. Because agents at any meaningful scale produce hundreds of millions of metadata events per day. Now, I think we're kind of running out of time, so I'll just say I'll make it a little more shorter. So the third decision, right? So I think this is probably the deepest one. So every agentic system has a determinism boundary, right? And above this line is the probabilistic stuff. The LLMs, agent loops, retrieval, ranking, all of that. And below, there's a function, and above sample, right? So now where do you kind of draw this line? And I've seen that, the probabilistic system basically picks the metrics, then you emit any kind of a structured request, and the model never retouches this result except to format it, right? Now, each bleed here is like a sampling decision, and by the time a user kind of sees this answer, your model, the number has basically been touched by the model many times. So yeah, so how do you know if you've basically drawn the line in the right place? I would say maybe do a cheap test, take the same agent request, the same context, and run it twice. Yeah, I'll share this deck, but yeah, I mean, here are some patterns based on what I just mentioned to kind of draw the line correctly. Yeah, finally, let me kind of skip over the synthesis, but yeah, 3 takeaways, right? One, run the replay test, pick the questions your agent answers in production, right? Ask each one 10 times maybe, and compare those numbers. The variance you find is a problem. And if you don't find variance, maybe there may be a blind spot there, right? And 3, look at your trace storage. I think is it your primary data? Is it lakehouse? And think about it and move it. Yeah, I think MCP is your wire, right? It does not define determinism. It does not define governance. Use it, but don't confuse a wire with architecture. Yeah, and I think the architectural job is how do we keep the boundary in the right place as that shape kind of shifts. So yeah, that's a talk. Thank you.
Well done, my man. I have to tell you a little secret. I've been quoting the last time I saw you give a talk. I've been recycling and parroting what you said on the multivariant runs of coding agents and then seeing which one passes the most tests. Thought that was brilliant. Again, now I've got more stuff to steal from you, so thank you. I am a much more, I at least appear to be much smarter after watching a few of your talks.
Thank you.
We've got a question coming through here that I want to ask, and then we're going to have a little AirPod giveaways. Or did I just say iPod? What are we in 2003? No, AirPod giveaways in the break next. But before we hit that, Tosh, we got some questions for you, man. How do you
All right.
ensure that your agent traces, being primary data, are not going to push your agent to go deeper into its mistakes?
Yeah, I think those are good questions. So one thing I would like to say is when you have your agent traces basically being your primary data, right? I think it's you're kind of thinking about let's just say most teams kind of when they start logging agent traces, right? they're trying to do the obvious things, right? And let's say, the agent kind of asked a question and you got an answer and you kind of make that available. Now, the problem is these traces are kind of like a record of what the agent did, not a record of what the agent should have done, right? So if an agent kind of picked, in this case, maybe status is not refunded on Tuesday, then you kind of, the correct filter probably was maybe, I have my status not in refunded or chargeback, both. Then you feed the trace back into context, right? So that's a positive feedback loop on mistakes. So a couple of things I would kind of think about doing is don't feed raw traces into your retrieval context without having some sort of a quality signal, right? And maybe another thing is, how do we separate observation from interpretation, right? When you have a trace, that should record like, hey, the agent emitted the SQL and the warehouse returned this result. That's an observation, right? It should not record, this is how you answer Q1 revenue questions, right? That's an interpretation. And maybe finally, I kind of wanted to touch on this topic, but can we actually use semantic layer as a ground truth anchor, right? Then, when it disagrees, you kind of mark it for review. So yeah, so I would say, treat traces like medical record, maybe not as a prescription. Yeah.
I like that semantic layer as ground truth. That was something I had heard a few other people talk about that. So we've got one last question for you coming through. And it's basically, no matter how much of this determinism layers we add, we always need a human in the loop, right? Or
Yeah. Yes. I mean, I guess hopefully AGI is going to help solve that. But yes, I think most likely we'll have humans in the loop. I can speak for the next 5 years.
excellent. Well, Tosh, dude, this has been great. Folks are asking for the deck. So if you can drop it in the chat, we also are going to be sending it out an email to everyone. And all of the decks that we have and we've gotten the approval to share, we're going to share with folks. So sit tight after the event. But look, Tosh is just one step ahead of me. What was that noise? Oh my gosh. So there it is, folks. If you want it, you've got it right here. Grab it, click on it. There we go. Now, Tosh, I'm going to kick you off. We're going to have this little break because somebody needs to win some AirPods. We got to do that. I'm going to move you backstage. And here's how it's going to work, folks. Here's what we're going to do. Before I bring on the video that is going to be how you do it, in the chat, not the Q&A, in the chat, I would love for you to tell me how many of these seconds am I going to be able to hang on to this cliff. So I'm going to play this video. Whoever guesses how long I hang on to this cliff for without going over, all right, without going over, whoever is the closest in the chat that thinks I can hang on for how long, you win the AirPods. All right. So does that make sense? Go ahead and guess how long you think I'm going to be able to hang on to a cliff. And if you don't go over, then, and you're the closest when we finally figure out how long, right? Then we are going to deem you the winner. Is everyone ready? Put your bets in now. Good Lord, somebody said 6 minutes. Uh-oh. You can only bet once. All right. You're only getting you're only getting one. That's it. How long can I hang on to this cliff? Let's set it off and let's go. Let's see what we got. The winner who doesn't go over gets a whopping new pair of the AirPod Pros. I almost said iPod again. All right, let's start it. Let's go. Press play. There I am. There I am. What are we seeing? 57 seconds. 1 minute, 32. Okay. Okay, we got 40 seconds, 55. I like your confidence in me. I like this. 5 seconds, you already lost. 6 seconds, 3, 6, 9 seconds. I don't know. 75, 2 minutes. Huh? Wow, impressive. Okay. While we're waiting, look at those forearms. Look at that forearm strength. Huh? Hopefully, if that doesn't tell you what you've got, then boom. Whoa. Oh, no. 38. Somebody tried to put it in there. You got eaten by the sound. 60 seconds? 60? Can I get 50? 55. Oh my God. Who's going to win? 55? No. You lost. Get out of here. 75? You lost. Oh my God. Oh! There we go. What is that? That is 66 seconds right there. That was what it was. All right. Now let's see. Who was the first person to say either 66 or 67 or 68? What do we got? I'm siphoning through this Slack or this chat right now. Oh my God. I see a 72. That's close. I see a 69. Uh-oh. Tim, let's bookmark you. 69, you might have been the winner there. Oh, I see a 68. Jason. Uh-oh, Jason. No, I can't see any more in the chat. It only goes to, uh-oh, Jason had 78. Why can't I see more chat? What's going on? I can't scroll back. Oh no, you all were too noisy. I think it was Jason with 68. Let's give it to him. Jason, if it wasn't you, then whatever. That is the winner right there. Jason, congratulations. Reach out to me, send me a DM, and I'm going to ask you for your address, and I will be sending you some AirPod Pros. That's just how we're doing it around here. All right, folks? That is congratulations, everybody. Give a nice little round of applause for Jason. Well done. Well done. Somebody said 66. John's saying, I don't believe you, John. Show me, reply to that, and let's go. There's a 65. At 65, it went over. All right. Let's clarify how this works. I thought I made it clear. We said it's 66. You can't go over, otherwise you don't win. All right. Somebody did 66. Leonard. Oh boy, am I gonna have to give out 2 freaking. All right, show me if you can find your original one, 66. Then I will give 2 AirPods again. Mohan gave. Oh God, I'm gonna have to give 3. Somebody got 66 too. Oh man. Well, send me a screenshot of your 66, and that will be it. All right. I hope I'm not having to give out like 3 or 4 pairs of these damn headphones. I was hoping to just give out 1. That's all we've got for now, because we got to keep the edutainment happening. So I'm going to bring our next speakers onto the stage. A huge shout out to all the winners there. If you can find a way to screenshot it, send it to me, and we will get that happening. Now, I've got Vamshi and Finley coming to the stage. Let's bring them up right now. Where are you all at? Hopefully did you guys vote on how long I could stay on that? You guys weren't participating, huh? That was good. So, guys, I'm gonna let you share your screens. Vamsi, you're on mute still, just as a heads up. While you're sharing your screen and you're figuring all that out, let me publish this next poll. Let me show this on the stage. We've got a poll, and in the meantime, guys, share your screen, figure that out, because I don't see it yet. Figure out how to share your screen, yeah? And everyone else, what are we talking about here with cost sensitivity? Do you even care? Do you care? Is it critical? Is it important? Or is it not a major concern? Let's see what kind of companies you all work for. And Vamsi, still waiting for screen share? You got it?
Yeah, so it seems I cannot share the screen while the poll is running.
No. Get
Yeah.
out. Oh, well, I was clogging up the pipes. There we go. Everybody, you can still reach those polls in the right-hand sidebar on the poll tab. So we want to hear from you. We've only got 37 people that voted. We want to hear more. We want to see what you got. And I think we're still looking for a screen share.
Yeah, just give me a second.
All right, then I will bring it up
do-
back on stage. Let's get it
Yeah.
just for a second. You got it? You got it? He left. Oh, shoot. He was. Uh-oh. Sealy, it's all up to you now, man.
Yeah.
Your partner in crime took off. He didn't want to share his screen. He said, I got to get out of here. All right. Well, in the meantime, how's this for you? How are we talking cost sensitivity?
Yeah, definitely critical.
Critical. That's a
Yeah.
critical one. You guys are at a certain scale where you can't afford to have it not be in critical shape, huh?
Yeah, definitely.
All right. Uh-oh.
Right.
We got him back. He's back. See, I'm gonna.
Yeah, looks like I need to kind of restart the system or something. So that took some time. Yeah. Hopefully you can see my screen now.
There we go. Yes, we got it. We did it.
Yeah. So we have, I think, Zinli is also co-presenting with me. He will kickstart the conversation and I'll take over in the middle.
Perfect.
Should we
I'll see you
start?
guys in a bit.
Okay. Yeah, let's get started. Hello, everyone. I'm Xinli. My colleague Vamsi and myself will talk about when you run a data lake with transactional data format like a hoodie, how do we make the operations minimized, reliable, and more efficient? Next slide. Again, I'm Xinli. I'm a senior staff engineer at Uber. I contribute to Hoodie, Parquet, Presto, and I really enjoy working with the open source community. Vamsi, he's a staff engineer. He has done a lot of work on the table service, Hoodie development, and recently worked on the Hoodie as a service to fully automate the table onboarding and management. So our our data lake house team has spent many years deeply in the guts of how large-scale data lakes actually work in the production in terms of reliability, security, performance, and the cost efficiency. So we periodically publish our NG blog for the interesting work we have done. So highly encourage to check out. So before we talk about the solution, let's establish this problem space. So every day you can see the number. So we get 6 trillion records, about 13 petabytes data come in to our data lake, and they need to be written to about 20,000 data as a Hoodie format, serving about 4 million queries every day. So at this scale, even a small problem that even looks boring on your whiteboard becomes super hard to solve because of scale. Example, even 1% of inefficient either file out, it could cause thousands of degraded queries. So scale is not just make things bigger, but also change the nature of the problem. Next slide. Let's landscape the Uber data architecture. Kafka feeds the raw event into the data lake. So we use Spark and Flink process their data and also transform the data. We have BI tools, machine learning models, dashboards, they all consume from the lake. So Hoodie is a table format at the center, holding all of this together, handling upserts, deletes, incremental reads, time travel, etc. But here's the thing, Hoodie give you the primitives. It doesn't operate itself. Somebody or something has to run compaction, manage file size, enforce retention, handle encryption. For us, it's at 20,000 table scale, so that somebody cannot be a human. So that gap is exactly we set out to close. Next slide. Let me pin you the picture of what the life looks like before we fix this. So Flink ingestion checkpoints every 10 minutes. That is great for freshness, but thousands of small files per table. That causes the listing overhead. And second, the TTL enforcement is needed because we can't let the storage size just grow. And for the security and the cost efficiency purpose, we also have pipelines that sanitize the data, make the data secure, remove some unused column for the cost efficiency to save money. So all of these operations together, we need a managed solution, otherwise which we cannot scale. And that's exactly we built Hoodie as a table service, which Vamsi will talk about it. Vamsi, over to you.
Thanks, Andy. Thank you for the overview. I think in the rest of the slides, I'll cover what table services are, and then the main challenges that we have in running these at scale at Uber, and then there'll be some takeaways in terms of like what are the common challenges that we solved. Hopefully, that'll be useful for community. So broadly, table services consists of three things at Uber. One is the table maintenance itself, which is a mandatory operation for all the tables. This includes clean and archival, compaction for main table, compaction for metadata table if you have it separately. These operations enable the table to be bounded in size and will ensure that your table doesn't grow forever, right? And compaction ensures that your query and tagging performance essentially remains in check. Otherwise, you have a continuously growing log files, which will cause both write overhead and read overhead for merge on read queries. Then comes archival and clean. These operations seem simple for everyday usage, but the moment you have any failures in these jobs, they cause sort of avalanche effect in production. Imagine you're recovering from an outage, or your job has some spikes in incoming traffic. One of the clean failures may not self-recover, and it will cause a series of failures for the system, only to be overwhelming the on-call at the end. So we'll talk more about how we solve these problems. Now we have also rewriters that thinly explain. These are things like secondary ingestion writers, removing some columns from tables, or performing some TTL operations like enforcing some 1 year or 2 year detention period, or also doing some encryption. These rewriters also use the same interface as our primary ingestion API, and it will help us manage these tables at scale. And then finally, the elephant in the room, which is the efficiency aspect of it, is how do we lay this data out in the disk so that the readers who are reading this data can perform or can read as few files as possible. Because what happens here is there is an alignment problem. While ingestion writes the data in a timestamp based fashion, the users necessarily don't process the data in the same way. So we talk more about some of the issues and optimizations that we found out there, and the amount of runtime impact it has on the queries. Okay, so let's jump into the high level principles we had in mind when we designed this platform, and we'll talk more about it at each level. And first of all, the platform is like an event driven architecture, meaning we don't have a fixed set of workloads. We basically scale with data sets and then get more capacity as needed. And all of our systems are tier based. So we have dedicated infrastructure running high tier workloads, low tier workloads, and we have isolation among all the services. So if there were to be a problematic service running, right, it will not impact rest of the table services. Uber is also heavily multi-region. So we are not completely on the cloud, completely on on-prem. We have a mixed set of infrastructure, and that brings elasticity, but it also brings us problems around where you have to deal data along multiple regions. But we expose this platform in such a way the users don't have to worry or burden about where their table is living on. So that abstraction is through platform. So once they come to the control plane, we take care of dealing with all the things behind the scenes. And I think all of these are only possible if you don't have any locking or need to turn off ingestion. So we ensure that the primary ingestion can continue running while we perform these operations, and this is possible due to OCC. This is an open source hoodie feature that we heavily use at Uber. And lastly, we have both Spark and Flink producing the data, and we try to abstract it to our downstream customers so that they don't have to know configuration specific behavior between two engines. So these are some of the high level design principles that we followed in designing the platform that we think makes the overall maintenance simpler. So here I present the architecture diagram at a very simple high level, removing all the bells and whistles, right? We have on the left side different writers like ingestion, rewriter, and then query engines like Velox, Spark, etc. These are either writing the data or reading the data from data lake, which is on the right end of the things. And then we have a data mesh, which is like an interface to access all of this data. And in the middle, we have the table service platform, which is the main component. And what we have there is like a control plane to begin with. This control plane is like the API layer that interacts with the datasets, allows onboarding, customization of the requests. The customer has a configuration control here that can say how often should the service be run, or what should be the trigger for running the service, etc. We also provide mechanisms where users can provide insights around table optimizations. For example, if they want to sort the data or cluster the data, they could provide some list of columns that they do with. And then we have data plane, which is basically our scheduling and Spark layer. Like essentially, this is where we control all of these data sets that are onboarded into a specific set of workflows. Today we use Spark for majority of all the workloads, and Flink for maybe a little bit of experimentation mode, but most of the production is on Spark side. Once we execute these Sparks in job, we collect what we call the runtime statistics. These go back to Tuner. Tuner is basically, think of it like a long living service that can remember what is happening to all of your services that you're launching. So it has a state construct, and the state essentially consists of a data set, table service, and the list of executions that happened with it, along with statistics like, for example, number of file groups that we're trying to operate on, or the number of partitions, number of files. There are a lot of statistics here, but think of these as the constructs that can tell you how to control the behavior over several runs. We also have observability auditing, which is essentially to ensure that our customers have a way to monitor what's happening with these data sets and table services. Now we'll talk more about these each components in the next slides. But at a high level, the platform mainly provides like one interface for monitoring, and then auditing and an observability interface to monitor the services. And then behind the scenes has a state store to pretty much store everything else. All right. So yeah, like we initially emphasized, we have 20,000 data sets. So even if you get 0.1% of the failures in the system, you're looking around 20 to 30 failures each day. And now failures around on calls, like failures around these systems typically are resolvable by human, but they still need to be get acknowledged and followed up through. And when we carefully looked at for most of these things, we realized that if we have a system tracking the failures and semantics of each operation, we can design a reactive system that can respond and fix the system automatically. For example, for cleans, right? If you know that there is a secondary operation that, like imagine a scenario where you have a DLM operation happening on a table. Now DLM operation naturally deletes all of the files from from an older partition. Now, when cleaner comes into the place, it will realize that there are more than certain set of files that need to be cleaned up, but the resource configuration it may be configured doesn't have the right set of parallelism to run the job. So it would fail with an out of memory or things like that. Now, because of the state store, we can remediate this in the next retry, launch the job with a higher set of resources based on the number of file mappings it is targeting. So the system pretty much recovers within few attempts and doesn't throw an on-call alert or cause an SLA violation. And we were able to, like, from our experience, I think we were able to recover 99% of the failures using the solution. The barring 1% or 0.1% of the problems constitute to a different set of systems, but cannot be automated at the moment. Now, we extended this logic similar to clustering, which is the file stitching problem we have. We are also extending this to compaction to similarly solve the same problem around resourcing. So this system is built at a platform level, and we're trying to expand this to all the verticals in the system. For the table rewriters, our goal is not around optimization or automation, but our goal is around reducing the friction between the APIs these platforms are using versus what Hoodie is providing. With table rewriters using a single API, our main goal, our main win comes from the upgrade velocity. At Uber Hoodie, we try to be pretty fast in terms of upgrade cycle. We try to follow an annual upgrade cycle to migrate to the latest open source version. But if there are like so many of these consumers start using unsupported APIs in different ways, it becomes harder to migrate or test during the upgrade flow. So we introduced a common API flow that they can use, which is consistent across all Hoodie versions. So the contractors are not bound to rewrite or update their APIs. At the same time, Hoodie team has the control layer to determine when to upgrade what service. Okay, let's briefly talk about storage optimization. I think this will be a slide most of you may be interested in. So we will tell you from our experience at our end. So like I initially said, the data that we lay out in the timestamp based order is not necessarily the data most optimal layout for data. Think about a case where you have a driver table, and then you have a driver ID. And then if you have a query that is scanning these tables, usually what happens is you need to go to the Parquet footers and then collect statistics and then see whether your data could be part of the potential file or not. But you're still incurring all of the expenses associated with listing and opening up the file footers. And if you're on cloud, all of this constitute to some amount of cost as well. But the primary aspect, at least at Uber side, is not necessarily cost, but the performance aspect of it. These queries take a lot of time because they're using a point lookup queries. And the way we solve this problem is we introduced a secondary writer, like let ingestion write it in the timestamp format. But then we have a secondary writer, which is coming in, like, let's say maybe a day later, and then reorganizing the data based on certain set of columns. For these columns, like for, let's say we don't want to like just do sorting because sorting is computationally very expensive. So we devised a strategy, what is called range partitioning. And what range partitioning does it at the very least is, instead of sorting the data around, strictly sorting the data around a specific column, it will divide the data into a group of buckets, and it will ensure that among these buckets the data is sorted, but within the bucket the data may be unsorted. So with this, we were able to get the time complexity down to linear complexity with respect to the number of rows we have. And then we observed almost like a 20x performance improvement in read performance with this. I think, I mean, among many things we tried, we felt like this was giving the most ROI in terms of read performance and computations. So we'll be happy to answer and share any learnings with the community as well after this. Another optimization that we did is the clustering. Not to get confused with other clustering concepts in Hoodie, but what I'm referring to here is merging the small files into larger ones. Our Flink checkpoint runs every 10 minutes. So sometimes we have partitions having more than 100,000 files within the same partition. And this will cause impact to our listing and query performance layer. So what we did is we basically rolled these all small files into a target cell, like we take 10 of these 100 MB files and roll it into 1 gigabyte file. This is a standard feature from open source, and we just rolled it out into Uber. We're also working on a Parquet row level merging feature, which is a novel feature that doesn't deserialize the data in order to merge. It uses Parquet level APIs to process the data. I think that's something we'll be rolling out in 2026-27 from Uber side. Last optimization that we'll probably talk about is indexing. Hoodie supports column statistics natively out of the box. And at Uber, we try to leverage this feature extensively. This feature is primarily useful if you have workloads like AI workloads that are targeting datasets with point lookup queries. You don't know which column the user is going to reference on, so sorting won't help. But you do know that their queries can benefit from column statistics, like for example, min, max, and null. These statistics already exist in our Parquet layer. What Hoodie does is bring them up to the metadata layer. So you don't need to hit the disk or do any file system to correct the statistics. All you need to do is enable Hoodie metadata, and then Hoodie will internally, during the read time, reference this column statistics and then prune your search space. Instead of scanning like 1,000 Parquet files, based on the statistics, it will only target 10 or 12 Parquet files. And then within these Parquet files, it will read up all data. Maybe some of them will be matching the data. So overall, like the number of footers that this will open will significantly reduce with column statistics. We found that there were some missing optimizations here at Uber side that we contributed to in terms of nested columns. But other than that, I think the open source column stats is in a pretty good shape. All right. Maybe briefly going back, right, a little bit. I think some of the like we built this platform like roughly in a year and a half or two, and what we learned is that automation plays a key role at Uber scale. Without automation, we started seeing majority of the on-call overhead, which is not great because the on-call can focus on other things if not for these ones. So we tried to pretty much automate a lot of these jobs. I think right now we are dealing with a different set of issues than what we were dealing with like in a year or year and a half ago. So this completely helped our team in terms of removing the main bottleneck. And I think the other thing that we learned is the configuration, right? And if we expose too much configurations to our customers, they end up cloning or copying this configuration across. And then during the upgrade cycles, it becomes very hard for us to go back and change anything. So I think abstraction is a key principle that we should we followed, and glad that we did. I think we should try to expose as minimal configurations to our customers possible, and then ensure that systems can make this opaque. And I think the other thing is event-driven architecture. Like just having them schedule-driven architecture won't cut for majority of the systems, because oftentimes you'll have spiky traffic in your system. So if you were to configure your resourcing or scheduling to a fixed nature, it would break as soon as you have this spiky traffic coming in. So I think it needs to be like event-driven. For example, compaction needs to run more often if there is more data in your metadata table or data table. Similarly, you deal with other aspects as well. All right. In terms of future work, I think our main focus is on enabling AI usage for the tables. So we have a lot of point lookup queries coming up. These queries are very slow on data lake. And this will compound, like AI systems need immediate responses as opposed to what we had before. So we are working on having some vector index support and also having more of these column statistics available for different queries. We also want to do improved clustering policies to evaluate our runtimes and speed up our queries. And then right now, Flink is only a minority for data lake, but we want to be doing some sort of a real-time table services in the future as well, depending on the business requirements and SLA requirements. That will be, I think, some of what we want to do at Uber, along with, I think, upgrading to Hoodie 1.x and then bringing in more of the open source features into Uber.
Excellent.
Yeah, that's
That
it.
is
I think these are our emails. You can shoot us an email if you have any questions.
great, man. I appreciate you. I appreciate both giving this talk and sharing what you've learned, what you did. Oh, hopefully somebody took a screenshot. Hold on, put that up again, just in case somebody wants to grab your email and chat with you more. I know there's been some awesome questions in the chat. We're a little bit over time, so I'm going to have to keep you guys moving. I appreciate that there's two of you and you were very active in the chat answering the questions, so that's awesome. But yeah, if anyone wants to chat, there was your chance to get that screenshot. All right, fellas, appreciate you. I'll kick you off now, and we're going to keep moving to the next speaker. Thank you. Adios. Next up, where is my man Revanthe? Where you at, Revanthe? There he is. What's going on, dude? So we've got a little lightning talk from you. Before you start talking, yeah, you need to share your screen. You did one thing. You also need to unmute yourself. That's the second piece. I had a feeling you were going to do
All right.
that.
Hey guys, hello.
There he is. There he is. All right. Cool. Well, 10 minutes on the clock. I'll see you in just a sec.
Good to go?
You're good to go. We see your screen and everything. Yep.
All right. Hey, hello everyone. Today I'm going to talk about building multi-tenant, multi-cloud streaming engines at trillion event scale. This is a story about platform evolution mostly and lessons learned during that evolution. Uh, so the mission of this platform is simple: allow teams to write streaming applications without bothering about infrastructure. Something which can manage different workloads with various shapes, few messages per hour to millions of messages per second. Simple ingestion, transformations, complex processing, minimal enough so teams can choose a right engine for the use case. We start with the use cases, what kind of ask the company has, ad tech, customer experience, supply chain, transactions, fraud detection, etc. Then assess whether each team is building their own silos, solving the use cases. Standardize it so that it becomes a force multiplier. For streaming use cases, there are multiple great open source alternatives available. Each requires areas of expertise on how to integrate, secure, scale, and save money for the company. For very large scale companies, like biggest retailer on the planet scale, where data sources, sinks are geolocated in different countries, clouds, hundreds of teams, most solutions fall short or need extensive plumbing to fit into the company ecosystem. Which is why we end up building something that can solve shared problems for the teams, a cohesive ecosystem by layering the open source engines with existing tech layers within the company. A vision for the platform is based on a set of design principles that we have. Keep it operable, enable self-service, keep it secure, reliable, and trusted from a data quality perspective. It should align with your own company's building principles. Every team benefits from them automatically. Now, let's look at the ecosystem. Like I said before, there are so many great open source alternatives available for us. For this talk, we'll focus on three of them: Kafka Connect, Spark, Flink. This is based on what your company really needs: different users, personas, sources, sinks, etc. In general, engine should have broad adoption and community support. It should help us solve very broad set of use cases and be able to make it work on similar operating model. Now, what architectural choices enables us to create such complex real-time platforms, right? For building a serverless platform, users should specify the intent. Platform takes care of the operability, observability, keeps it reliable, and provides data quality integration. We chose Kubernetes, which is excellent choice for building such platforms. It allows us to extend the cloud native principles. Most of the engines have strong first class support for it, allows us to easily abstract cloud vendor specific quirks, and it also has excellent semantics for extensibility using controllers and operators, which makes platforms easier and predictable. It's easier said than done, and having layers help companies. Most of the company providers have different Kubernetes operating. Pretty good open source fleet managers are available too. Using them pays off pretty well, especially if you have a very large fleet spanning multi-terabytes or petabyte scale compute. Below that, you have the streaming engine product layer and how they complement each other. This is where Kafka Connect, Flink, and Spark are exposed as self-service products. Now, they're all excellent in their own ways. They have their core strength and business use cases determine which are used by which customers. Platform control plane on Kubernetes helps with the shared abstraction needed for us. Customers don't really care about it, won't even know if the K8's layer is completely replaced by an alternative compute engine in the future. Now, let's start building the plumbing that is needed. First step is to provision the compute clusters, install the same tooling across clusters. And once tooling is installed, we open it to the customers. They identify their teams, resources, reserve the resources that they need, and let us know what they want to run. We take it from there and ensure it runs in their desired cloud or region, and ensure that it is always running without hiccups. Let's start with going deeper into the products itself. So Kafka Connect as a service, the platform support standard connector patterns like JDBC sourcing, Kafka to Kafka replicating, cloud storage syncs, Debezium CDC, custom connectors, etc. It's a distributed engine suitable for simple transformations and filtering. Customer specifies which provider and region they would like to deploy their app in. They reserve the necessary memory CPU needed for all their apps. They will then have to specify you know, whether they want a metric-based auto scaling, min-max settings, and other configs needed through GitOps or API. After that, the platform takes it from there, provisions it, enables golden signals for the customers, and right-sizing recommendations that are needed for future. Spark and Flink are pretty similar too. The customer defines what they want to run. They declare their intent and say, hey, run this Spark job for me. These are my configs. These are my secrets. Call me on this number if anything happens, right? So platform then builds the jar, finalizes the intent, then decides where to run. For example, Google, Prod, Central, Azure, non-prod, South Central, like that. So it abstracts all these things from the user. For them, changing a cloud or a provider is pretty much like changing a configuration, and it takes care of taking that intent, splitting it into multiple intents, for example, Spark job, certificates, secrets, etc., and submits all of them to selected cluster. So we use a concept of controllers to enable that across the control plane level. Now, this is where the intent becomes the actuals, right? Each of the intent has a corresponding operator, which then takes a definition and creates corresponding resource. Spark, Flink operators, infra operators for taking care of observability, cluster, apps, secret management operators, log shipping to central repo, all are provided within each Kubernetes cluster. It's a cellular architecture. We try to keep a balance between the scale versus sharing the resources so that there's no single point of failure. Now, K8's extensibility using operators and controllers are what makes this stable and operational for us. For many functions, there are excellent open source operators that are available. The platform composes these operators into an ecosystem. It also extends Kubernetes using custom controllers, operators where needed. Uh, it's kind of like a 75-25% need right now. Now let's look at some of the controllers that are needed in detail. The placement engine, which is kind of like the controller that is required to deploy the different shapes of apps that we get, right? It could depend on the size, latency requirements, different hard constraints. Like some people want only in a particular provider, region, etc., depending on their sourcings, etc. So we use a custom scoring function that decides which cluster is best suited during the deployment time based on various multivariate bin packing algorithms. This can easily make the decision between spending $10 million, $20 million versus like $100 million. So the easy part is out of the way. Now, streaming apps run all the time. Disruption happens in multiple fault domains. So the infra, app logic, data, everything needs to be automatically identified, mitigated, and recovered. For BCDR, we need custom controllers that can react to cluster issues, failures, and it should have quota-aware, data preservable decisions that it can take in moving all these jobs to their respective intent specification. We also use custom controllers for upgrading all our fleet. The upgrade cycles, they can create disruption as they're not aware of the behavior of these underlying workloads. So we employ a different node pool blue-green pattern where the control spins up a new K8s node pool on the newer version and then moves these workloads gracefully in a coordinated way and scale down the older version. It helps us with the partial rollback too. Security patches, vulnerabilities, they take a chunk of time for us. So, so we need to use like golden images, cluster-wide policies that can be auto-updated, which is how we do it. Now, so the observability forms a key to the entire platform. Now, if a customer wants to know what is going on with their job, is it running fine, etc., and we want to alert the customer, we employ the different pillars at different layers, uh, Prometheus operators, log collection, eBPF-based profilers that continuously track the network data. So, and everything is fed to the AI to summarize it and be able to troubleshoot quickly to identify the patterns and tell the customer what is happening. Anything that runs on the platform would be tagged with the corresponding labels. There are Kivana policies that automatically do it for us. They make sure that we are able to charge back the customer exactly for what they use. So by making these hard parts predictable, the platform wins by helping customers be able to, take their applications faster. We enable workload isolation at the platform level, all the upgrades, etc. We try to take care of it in the backend. At the infra layer, runtime upgrades, we provide the customer with runtimes so that they can update it whenever they have the need for it. We eliminate the operational blind spots, each team having to solve it, and also reduce the cost by providing elastic compute uh, through these products. This helps us save a lot of developer time, improves the overall efficiency within the Walmart ecosystem, within our company's ecosystem, and also saves a lot of cost for the company. The key takeaways here. So by providing these serverless platforms, we ensure that customer does not need the minimal knowledge that is required. They're more worried about their business use cases and the product that they have to use. We try to keep it as a single platform for multiple streaming engines so that pretty much everything is covered for. Deep observability is built in from day one, so that customer is aware of what is happening within their applications and how to mitigate them. Costs are kept to a minimal. All the right sizing recommendations we take care of at each product level. We kind of determine what it is using, what are the query patterns, what are the shuffle things that it is utilizing, and we bubble that information up to the customer so that they can use it to minimize their resources. And we also put the appropriate guardrails for all kinds of production incidents at multiple fault domains so that we try to take away that burden from the customer.
Nice.
Yeah.
Well played, Revanth. I appreciate this, man. Thank you so much. I am going to, let's see. Let's get this out of here, and I will get to say thank you. If anyone has any questions for you, I'm going to direct them to the chat because I've managed to not do my one job, which is keep us on time. So that means we're going to swap you out for our next speaker. For folks with questions, you're going to hang around and answer them in the chat if you got them. But for now, thank you, and I bid you farewell.
Thank you.
Next up, we have Max to the stage. Where is Mr. Maxime?
Hey, how you doing?
So I've been horrible at keeping time today, and that's because I do stuff like I'm about to do for you right now, which is I heard you liked Frank Zappa.
Oh yeah, I'm a big fan. Oh yeah, on a uke.
How about a ukulele rendition of "We Were Jamming in Joe's Garage"? We didn't have no dope or LSD, just a couple of quarts of beer to make it so the intonation would not offend your ear. And the song went over and over and sounded good to me. Now one more time. It's all yours.
You have a little bit of Frank Zappa in you. I can tell.
I
You
do.
know, the little mustache, the hair. You know.
It is. It's the mustache. It brings it out. It brings it out. Except when I try to play the guitar like he does, I fall flat on my face. So I wish I had more of that in me. Sadly, it stops at the mustache. That's as far as we
Yeah,
get.
the audience is gonna be glad I don't have my guitar with me. I'm traveling. I'm in Boston at some conference out here, so I found a little corner in my Airbnb. Excuse the decor, but here
We were
I am.
jamming in Max's Airbnb. We didn't have no dope or LSD, just a couple of data pipelines to make it so the. All right, man. I'm see how we get off of the track. This is what happens. I'm gonna put your stuff on the stage, and I'm gonna get out of your way. All right. Let me add your screen, and I will. Boom, boom, boom. All right. There we go.
How are we looking over there? Because I've got a single screen here. Everyone's seeing my slides. So
Yep. We see it. We see it.
Sweet. I thought I had a half hour. I've got 20 minutes. I might have to speed run some of this, but I've got a lot to talk about. Yeah, and I've got a lot to. I've got a bit of a demo too, so I'm hoping I've got enough time for the demo. I'm gonna try to keep an eye on the clock too. All right. So today I'm going to talk about the anatomy, anatomy lesson of our data agent. So we built an internal analytics agent internally at Preset, and I'm going to talk about how to build one. I think I'm going to try to go meta. I'm trying to make it practical and try to encourage people to go and build like a super data agent for themselves and for people in their company to help self-service, people, work with data in all sorts of ways. So that's what I'm talking about today. Just for context, about a year ago, I wrote this blog post. So last year was kind of the rise of MCP and like the agent, the models got kind of good. And then last year, I was like, soon we're going to be able to compose all these MCPs and skills and contexts and do amazing things. And at the time, it was not really possible to do that because the MCP servers were kind of shitty and early, and they would blow up your context window. So it was not practical. But here we are a year later, and we can actually do it. I'm going to do a quick self intro, but I've got this deep passion for building data tools, like interactive things, super into AI. I started Apache Airflow, Apache Superset a while ago. And today I started something new too. I'm going to try to demo today. So I got a speed run so I can get to the demo. So hold on to your seat, maybe get a coffee. There should be a demo as part of this. Something kind of interesting too. So I've always been like super full stack, front end, back end, data engineering, playing analyst. I'm a little bit ADHD too, and those character traits tend to be super rewarding in the AI age. So like I've been really into agent orchestration, AI enablement, like trying to push people to do better work with AI. So this is what this talk is about in some way. So I'm going to do a little bit of a rebase. It's a little dizzying to follow exactly where we're at right now with AI. There's been so much stuff going on. So I'll do my read on what happened over the past year and what's happening, what's ahead of us. I'll be talking about analytics agents, like in a more conceptual, like what do they need to be deeply useful. And then I'll talk about the data agent that we built internally at Preset, and I might give you some ideas of doing similar things. And then I'll do an Agor demo. Agor is kind of a team command center for everything agentic, and that's what we use for all the mechanics of the analytics agent that I'll be talking about today. Rebasing. So what happened in 2025? I'm going to go quickly through this, but a lot happened last year. MCP dropped early in the year, or right around then. Claude Code dropped last year, so I'm pretty sure everyone has had their kind of Claude Code moment this year. They're realizing like nothing will ever be the same in the best way. Like they don't need to write code anymore, which is kind of a crazy shift when that's what you've been doing all your career. Then the models got real good, and then OpenClaw dropped and got covered in an interesting way by the news cycle. But I think the real thing is that's really interesting is the arrival like persisted agents, like agents that are not just an ephemeral session, that can build context, that have a memory system, that got skills, that can be driven to, they can it's agents with agency. These agents can actually be proactive too. It's a pretty big shift last year. And then some of the stuff that I see ahead that's coming up, and I don't know if other people share these views, but I think this year is the year where people really start to do MCP and skills, the skill composition. So like bring couple like 3, 4, 5, 6 skills together, and a bunch of like MCP servers, provide the right context. So that's a big shift. Agent orchestration. So more and more people are parallelizing work with multiple agents. That's a big shift. Maybe like being able to collaborate with other people in your teams at managing your agents. That might be a trend this year. We've seen a pretty important rewrite of the PDLC. So the product development lifecycle and agile, like a lot of these methodologies don't make as much sense anymore. So I think we're completely changing the way we work together and with agents. The roles are collapsing. We're going to get some better models again, which is crazy. They keep getting better and potentially cheaper. And this is maybe the year where agents start to get access to everything, and we might need to start thinking about Okta for agents. I think a lot of people right now are passing their credentials to their agents, but like we might have more agent identity. And then maybe the end of subsidies. So we've all been enjoying the subsidized subscriptions to our AIs, but that might not last forever. So as much as I enjoy a nice VC money bonfire, like this, there's probably an end to it at some point. The economics or the tokenomics might change quite a bit. Cool. So this is the shock slide, maybe saying that your agents are limited to their interfaces, right? So if your agent is blindfolded and has no arms, you have to be the eyes and the arms of your agent, and that is not practical. So, this encourages you to provide the right tools to your agent so they can help you best. Now, since I'll be talking about analytics agent, I wanted to show our high-level data flow diagram at Preset. So we're a small startup. We're not like a gigantic company yet. We have a pretty intricate data platform, and you all have one. I'm sure you all have like very intricate data platforms. And the point around this is that for you to do any data work, you're going to need access to a multitude of systems, right? And so do your agent. So, just at Preset, we got BigQuery, we got dbt, Airflow, we got Superset as our main data consumption. We do ETL, reverse ETL, we connect to all sorts of systems. So, it's quite a bit of complexity here and quite a bit of systems to access for your agents to help you with all of your data work. So now I'm going to get like more meta, like at a high level, without talking about our agent, but like what is your data agent going to need to serve you, right? To help you do your work every day, help like support the roles in the data team, but support your whole organization. And I'm going to try to go like somewhat by order of importance. So, your agent maybe first need access to your data through your BI tool, right? Maybe through a skill, an API, an MCP tool. But it needs probably a viz engine. It needs to know what, all the semantics that are in the BI tool. What are the metrics, the charts, the popular dashboards, and the most popular data sets, and how do they work? So all this metadata, super useful. Then I would say your data pipeline source code. So maybe historically we've had data catalogs and things like that or things like open lineage to get your lineage, but your data pipeline source code has tons of semantics, right? It's like the recipe book of how your data warehouse got made. So it's really important for your data, or if your agent's got access to this stuff, it can really achieve a lot around lineage and understanding how metrics get made and how your data is laid out and all of that good stuff. Then your agent needs SQL access, like probably to some sort of data access layer. In our case, we do it through our BI tool because Apache Superset has a really solid API to run SQL internally. But your agent's going to need to run SQL, right? And to look at sample data and perform queries and answer your questions. Relevant docs. So most organizations probably have a lot of documentation around their data warehouse beyond the code. Maybe some business metrics, definitions, and all this good stuff. So your agent needs access to that. It probably needs access to your orchestrator. You want to know if a job is late or hasn't run. But there's tons of important like data ops, metadata that lives in these systems, and probably a way to submit PR. So we got coding agents now too. So if your agent's has got access to file system and it's something like Cloud Code or the Cloud Agent SDK or Codex SDK, your agent is going to be able to fix up your pipeline, right? Maybe you're like, I want to break down this metric by a dimension that does not exist. Your agent can offer you to thread this, this dimension through your data pipelines. A few other things too that are also useful, and I put like on the maybe, but I think that these things are super useful. But with OpenClaw and the rise of like more modern agents, now agents have memory system. They've got skills. They can maintain your docs, in external systems and in your wikis or wherever your docs sit. You might also need for your data agent to have access to your source and destination systems. By that, I'm thinking, say, you have a CRM, you load data from HubSpot and to HubSpot with reverse ETL. If your agent is able to, has got a skill to connect with these tools, it's going to be able to help you out. Maybe some data sync issues, and in some cases, be able to directly shortcut the data warehouse and get data straight from the source. Data dictionary, if you have them, plug them in. Semantic layers, if you use them, plug them in as well. And then something maybe the cherry on top, but we'll see on my demo, is that if your agent is available on Slack, then that's where people live, that's where people collaborate and do work. So our data agent is available on Slack, and that turns out to be extremely helpful. I'll talk just a little bit about what we've built at Preset. So at Preset, we built like a managed system, a managed service around Apache Superset. So we built Superset MCP, that's open source. So we're building on top of that. We've got an in-product chatbot too. So this in-product chatbot can answer a lot of questions, got direct access. It knows where you're at in the products. It's got a lot of context. It can also like show you or take actions directly in the product. And then we've got a CLI, the Superset CLI, that allows you to manage assets as code. So we wrapped a little skill around that CLI, and the agents can do all the things the CLI can do. That's also an alternative way for the agent to run SQL. I'll talk a little bit, I'll talk about our agent maybe. So I wanted to introduce DataGore. So like it's an agent that's built on the AGOR platform. That stands for Agent Orchestration. I'll demo a little bit of the tool today. So AGOR is the platform, DataGore is the name of the agent. And I would love to encourage people to build their own data agent today. So just the anatomy at a super high level. So our data agent that's available to everyone in the company through Slack or through other means has access to Preset MCP. So it's able to access data, run SQL, create charts and dashboard, and help you find things. It's got access to our data pipeline source code. So for us, that's a repo, a code repository called DataEng that has all of the data and engineering stuff. So Airflow scripts, DBT, Python script, all this good stuff. Then it's got some skills. So it's able to run DBT. So it's got a skill wrapping the DBT CLI, the sub CLI I just mentioned. It's able to talk with Airflow and Astronomer. Astronomer is the hosted service for the managed Airflow service that we have. It's got access to internal SaaS. So it's got access to our ticketing system, through our Notion, through Fellow, which is like the meeting. Fellow for us is like the meeting note taker. And it's got access to Slack, right? So it can go and scan a Slack channel to look for questions and answer and take actions. It's got access to our docs. And then it's got some agentic goodies of different kinds. So it has a memory system. As I mentioned, it's available on Slack, so you can just kind of ping it, and it can manage docs for us. So on top of that, it's got a little bit of personality. So when you create these agents, if you use an OpenXdata type framework, you can give it a soul and an identity, which makes it kind of interesting. You give your agents a little bit of personality. All right, now I'm going to talk about AGOR, and I'm going to try to keep an eye on the clock to see how much time I have. So back in the fall, I started building this agent orchestration platform called AGOR, and it's very much like a team command center for everything agentic. So the challenges I was dealing with is I wanted to orchestrate a lot of agents, right? Like since about this time last year, I started like figuring out how to manage like 2, 3, 5, 10 agents in parallel. So I wanted to like stay sane while doing that, not be stuck in all these terminal windows. And I was also upset that it's hard to collaborate with agents. We're also stuck like in our laptop, like Cloud Code and your AI sessions are very personal, but I wanted to enable, in some cases, to share sessions with my teammates. So here we go. So I'll show what I've built and what it looks like. And if I can get a time check, I don't know until when I have it. I know we're running late.
We've got until, I'll tell you exactly, we finished at 2:55 technically, which was 3 minutes ago, but let's say we got an extra, how long do you need?
I don't know. I've got, I can fill the time, but maybe I'll keep going, and you give me a signal, 2 minutes before I wrap up, and I'll show as much as I can show here. Yeah. All right. So, yeah. Cool.
Go for it.
All right, so welcome to Agor. So this is an agent orchestration platform, and there's a lot to explain. There's a lot to show. So like, get ready to get a lot of information. I'm going to try to explain exactly how this thing works and some of the things that it can do. So the first thing is that in Agor, you got boards, right? So a little bit like Figma. So if you're familiar with Figma, it's a very much like a Figma type interface. And what are all these black cards that you see in here? These cards are Git work trees. So Git work trees they're kind of Git branches that you can have checked out in parallel. So essentially you can see that pretty much everything on this board is a feature, right? So if you look at some of these that are done, they've got a PR attached to them. Some of them are a GitHub issue attached to them. And a work tree is where your sessions live. So if I click on this particular session, this happens to be a cloud code session. Here I have a codex session. I did code review for this session. But basically inside a work tree, which is a place in the file system, it's a Git branch where you can do work. You have one or many AI sessions. And here it's built on top of the Claude Agent SDK, the Codex SDK, the Gemini SDK, all the agentic coding SDK, including Copilot and Open Code. So you can pretty much, instead of going to Claude Code in your terminal, you can come here. And if you come here instead, you're able to work with others. So you can see there's someone else here in my instance that's connected. And you can see that everyone have presets. I've got tons of like various users, like a lot of people at preset have access to this tool. So that means that someone else can come, if I let them, they can come and prompt my session. They can come on my board and I'll see their cursor. I'll see their little presence indicator. And now, general idea, maybe like the light bulb moment is that you can collaborate with your team with agents. There's tons of cool features in here. I'll try to explain a few. One is environment management. So now that we're all in the same box together, right? So we have a Unix box. Everyone's got their Unix username and they execute, commands and their agents run code as them. So I have like my own Unix user behind my Agor user, and I can start an environment, right? So if I want to start an environment, that's simple, like clicking stop, clicking start. You can have different variants on your environments, but here this environment is available for me to use to run some tests. Maybe I want to run some headless browser, playwright, MCP unit tests. So the environment is there for the agent and it's there for someone in QA in my team or my PM wants to come and see this feature. They can come in here. They can click and open the environment that's in development environment. We can work together on that. So that's pretty groundbreaking. Like, it's been a lot of like Git push and pull when you try to collaborate with others, but your reviewer can come here and interact with your environment, your pull requests, and can create their own session or post prompt your sessions. So that's at a super high level. The board's got these work trees. They're typically features. And then you have these zones. So the zones are pretty interesting. The zones have template triggers. They have prompts attached to them. So that when I say drag and drop this card to this zone, it will offer me to act on this prompt. So you can attach prompts to zone. You don't have to. That's a mean to organize your projects, your workflows. So here you can see my workflows, got some coding task and a step to create a pull request and a step to trigger a codex review. So you can organize the stuff the way you see fit.
And so anybody who is on your team and has access to this board is able to see all these different sessions that you're showing on the right?
That's right. So they can go around and click around and read through the session and see what's happening, right? So they can look at the codex review, or they have full access to the board if I let them. So the boards can be private. I won't get too deep into how this works, but when you create a work tree, you can decide whether it's just you or other people should be able to create sessions, prompt your sessions, have access to the file system or not. So you can decide on a per work tree basis, if you want to share them with others or not. But I love to share everything. It's so cool to be able to like take a session link and say like, hey, this agent is saying something. I can take the URL, send it to a coworker. They can jump at the session. They can prompt too. So call it like multiplayer. Bring your team, bring your agents, and rock the boat. Make it happen. Work on the same live environment with agents and your team members. So what I wanted to show, so there's boards. I'll talk, just a little bit about the information architecture. So Agor keeps track of the repositories you work with. Those are the work trees. So like there's one row here for each card. There's assistants. So the assistants here are based a little bit on OpenClaw. So when you create an assistant, it's a different type of work tree. And this assistant is always born with a memory system, with a skill folder. So they come in like they don't know anything, but the first time you talk to them, they do like OpenClaw. They say like, who are you? Who am I? What do you want to work on? What are some of the workflow? How do you want to organize your board? This sort of thing. So these assistants super powerful. So it's kind of like, you can kind of think of it like OpenClaw for enterprises. If that makes sense, right? Or for OpenClaw for a team. So instead of having like your OpenClaw on your Mac Mini, now you have a place where you can build an agent. Maybe that's a legal expert, right? Or maybe that's a coding expert for a certain repo, or maybe that's the deal desk, go-to-market helper that has access to all of your contracts or something like that. Going down the list, so cards is a way for agents to put stuff that is not a work tree on a board. I'll get back to artifacts. This is like probably one of the coolest features. I'm going to save it for later. Here we register all of our MCP servers, so we use quite a few at preset. But when you start a new session, you can decide I want to use these MCPs in here, so that prevents from having to have everyone set up their MCP. So you have like these shared MCP servers. In our case, most of the SaaS tools we use internally. Then I'll show, I'm going to go to my Slack. Like earlier, I wanted to show how you can prompt. So DataGore is our data agent, and maybe I'll reuse the prompt because I don't want to type. But if I ask it, what have we all accomplished over the past month or so? So what happens when I do this, it's gateway channel. Going back to the gateway channel, they're registered over here. So they point, they configure a Slack actor or a GitHub actor to be connected to a specific agent. And in my case over here, so this one's getting to work. It creates an Agor session, but it will answer on Slack ultimately. So while this one works, I'll go to the prompt I did earlier. But this is the kind of things that we've been working on with DataGore over the past month or so, asking it what it has done. It's referencing some PRs that we work on. It's referencing a lot of questions that people have asked internally at preset. So these are, when you create an assistant in Agor, it's got a memory system, it's got skill, it's got MCP access. It's pretty cool stuff. I'll show the last thing that I think is super exciting. So you've seen agents being able to create these micro apps very quickly. So in Agor, if you ask an agent, well, so first the agent has access to Agor through the Agor MCP. So that means that I can ask an agent to ask another agent, or I can ask an agent to find 10 GitHub issues and start 10 work trees in parallel, right? So the agent is able to create work trees, put agents to work, ask questions to agents. And then these artifacts, they're these little React apps, basically. So the agent is able to create these React apps and to publish them on board, which is super cool. So I'll go to a board that I created. I think it's called Artifacts. So here, those are just like, I asked agents, like, hey, can we track the number of stars on GitHub for Agor, which is the product that I'm demoing now. So it's loading. So this is an artifact that an agent created. You've probably seen in Cloud Desktop, like the agents are able to create these apps and render them on the right panel. They also call it artifact, but here the agents are able to put them on a board. So I've got different apps here. This is how much token app burns. That burn over up, spend 10K worth of token on my Cloud Max Pro plan. So I've been very much enjoying the subsidies coming
This is
from the
impressive.
VCs.
This
Isn't that crazy?
Yeah, it's your own little dashboard that, wow. Yeah, I love that.
Yeah. Yeah, it's cool. You can ask your agent, like, let's say you're connected to the HubSpot MCP, which is your CRM, and you're able to ask your agent, like, hey, can you pull some data from the HubSpot API and, make a little chart or dashboard, or make a little app that allows me to, I don't know, close deals that are potentially, stale or something like that, right? So the agent is able to do this. You can see like different people here are coming in. So those are fellow presetters that don't know that I'm watching over them right now, but you can see their cursor move in places. I'm going to try to not show too much of what's happening internally, but very Figma-esque. So really excited about the tool. Like I think we got about 1,000 stars on GitHub, but you should definitely check it out. Play with it if you want to get involved, or just try it. Highly encourage people to take a look and engage. This is open source. Maybe I'll show the website. You can go to agor.live. So live as in very multiplayer. It's pretty good.
Very cool.
Documentation and a cool GitHub. So I'm gonna. This is most of the content I had. I went kind of deep in the demo. So I don't know if I'm gonna stick around, maybe answer questions on the chat.
Yeah, I'm sure there's a lot coming through in the chat. I'm going to give it a star right now, man. Thank you for doing this. Sadly, I got to kick you off. I would talk to you for hours, so let's do another podcast sometime in the future.
Yeah, let's get together. We can do a podcast or just catch up.
Play some music. We'll play some music. That's good.
With the lag of the Zoom, I don't know if that works.
Yeah, no. I'll see you, man. Thanks. That was awesome. All right, so we've got officially our last, this is our last speaker on this track, but then we've got a whole nother workshop session happening. Let me bring out Ruyang. Where are you? Hey, good to see you again, dude. How you doing?
Hi, Demetrius.